From relational to NoSQL databases, most applications use at least one. Many architectures in AWS employ multiple databases of various kinds. In this lesson, we will explore highly available relational databases on Amazon Relational Database Service, the NoSQL database, Amazon DynamoDB, data warehousing with Amazon Redshift, as well as services for in-memory cache and graph databases. Now let's take a look at an overview of AWS database options. So starting with Amazon Relational Database Service, or RDS, we get a fully managed relational database management system. And by fully managed, we mean that Amazon handles pretty much everything except writing SQL statements for you. And so we also get our choice of popular engines such as MySQL, SQL Server, Postgres, Oracle, and so on. Another great thing about the relational database service is that maintenance is fully automated. Things like operating system patches, the database engine patching, backups are all fully automated. And it's also highly customizable. We get access to options and parameters so that we can tune the database. Just because it's fully managed doesn't mean that we're locked out of those things. We do get access to parameters so that we can like I said, help tune that relational database to perform the way we want it to perform for a particular workload. Relational database service also supports high availability with automatic failover, and we will go into more details about this service later on and explain exactly how that happens. We also have Amazon Elasticache. Amazon Elasticache, very much like RDS, is also fully managed, but this gives us access to an in-memory cache, and we get our choice of Redis or Memcached. So with Memcached, we get a simple key value store. With Redis, we actually get much more of an in-memory database. We have the ability to use more advanced data structures like hashes and sorted sets and in-memory operations. Now with Amazon DynamoDB, we gain access to a fully managed NoSQL data store. And this is, of course, in the same family of data stores such as Cassandra and MongoDB. But with DynamoDB, there's no infrastructure whatsoever for us to manage. Amazon handles all of the underlying infrastructure as well as the database engine. One of the benefits of DynamoDB, one of the many benefits, is that it's highly scalable. Your data set can grow into the petabytes and beyond without any additional effort on your part. You just simply throw data at your table and it automatically grows. And it grows not only for the storage plane, but also for the infrastructure that's managing the actual throughput. DynamoDB, like most managed services within AWS, is also fault tolerant. It's inherently fault tolerant. All of those good things are built into that service, right? So the benefit of these managed services like RDS and Elasticache and DynamoDB is that we can offload operational burdens so that we as an organization, we don't have to worry about what it means to make that service fault tolerant. DynamoDB is also internally automatically replicated. Our data is written to numerous devices across numerous data centers. And again, we will go into more detail on this service later and talk about how that happens. DynamoDB is also event-driven, meaning that as data is being written or updated or deleted from a table, then we can tie into those events and analyze those things in near real time as those changes occur. With Amazon Redshift, we gain access to Amazon's petabyte scale data warehouse. And again, this is also fully managed. AWS takes care of everything from the infrastructure to the operating system to the database engine. And the largest cluster within Redshift gives us access to 1.6 petabytes of storage, and we can use this to run queries, SQL queries, across a vast data sets. And of course, Redshift being a fork of Postgres 8 means that it's fully SQL compliant. And again, just like other systems like DynamoDB, Redshift is also inherently fault tolerant, highly durable, and also replicated. It also supports server-side encryption and disk-based encryption. With Amazon Neptune, we gain access to a fully managed graph database. And with a graph database, we can use this to run queries and analytics based on relationships. This database is optimized for relationships between entities. So you think of things like a recommendation engine would be really well suited to run on a graph database such as Neptune. Again, also inherently internally replicated for durability. Neptune also performs continuous backups, whereas something like the relational database service performs backups every so often. With other services like Neptune, the backups are continuous. We also get the very easy ability to create read replicas with Neptune, so and RDS as well, so that we can offload our reads to one node and send our writes to another node. That can help increase performance of the system as a whole. Now, a couple of other databases that were released in November of 2018 during AWS reInvent were Amazon TimeStream and the Quantum Ledger database. So these are very new database services that were very recently released. So with Amazon TimeStream, we gain access to a fully managed time series database. So if you've been in the industry for more than a year or so, you've probably seen a scenario where you are recording time series data. Right? Time series data is very common, but it's also a very specific type of data that needs to be ingested and stored and accessed in a particular way. And if you've used relational databases long enough, you'll know that they're great for many things, but when you're recording many events based on the second or even sub-second, you can very quickly, over a relatively short period of time, end up with potentially billions of events. And then if you're wanting to access those quickly or perform time series specific types of analytics, then relational databases tend to fall down and tend to not perform very well for that specific type of workload. So the Amazon TimeStream database is specifically geared towards that time series type of data. And it's capable of recording trillions of events per day. So if you have scenarios where you are wanting to record events, in less than a second interval, then Amazon TimeStream may very well be the right solution for that problem. It also has built-in analytic functions, right? So you don't necessarily have to write your own code to perform analytics on that time series data. You could leverage the built-in analytic functions of Amazon TimeStream itself. And now, at the time of this video recording, Amazon TimeStream is currently in preview. So by the time you're watching this, it may or may not be out of preview. But keep an eye out for Amazon TimeStream if you are looking to do something with time series data. And lastly, that brings us to the Amazon Quantum Ledger Database, or QLDB. With QLDB, we gain access to a fully managed ledger database. Now, when I say ledger database, what I mean is when you think about a ledger is most typically used in something like financial transactions. If you want to record the history of debits and credits to and from an account, right? And you want that history to be accurate and immutable, right? So the Quantum Ledger Database uses an append-only immutable journal. So every transaction is simply added to the end of that ledger, and there's no ability to go back and modify a previous transaction. So the nice thing about a ledger is that it gives you a very accurate historical journal of transactions. They don't necessarily have to be financial, even though that's the most common. There are all kinds of use cases for recording the history of certain things. And so with the ledger, this takes a page from the blockchain network, such as Bitcoin or Ethereum or others. Whereas you have this, with those type of distributed ledgers, you're able to cryptographically prove that the history of that ledger was immutable, that it hasn't changed, right? And so here, we get the same ability, except that the quantum ledger database is centralized. And the benefit of it being centralized rather than distributed, like we see with Bitcoin or Ethereum or other networks like that, is that it's going to operate much faster. There's no need to transfer the entire ledger to all of these nodes all over the internet. It's all centralized in one place. And so again, we can validate the entire history of that ledger with a cryptographic hash, which means that if anyone were to somehow modify a previous transaction, then the ultimate hash would be invalidated. It wouldn't match, right? So again, we have the ability to verify an entire history of transactions with the quantum ledger database. And so those are our database options within AWS. You can see we have a number of really amazing options to choose from according to the types of data and the way that we're using that data. And so we will go into many more details on each one of these, or most of these services, as the course progresses. Now let's review an introduction to Amazon Relational Database Service, or RDS. Now, before we get into the details of RDS itself, let's first take a look at what it means to manage a relational database service. So as you can see, managing a relational database on premises requires a lot. There's a lot involved, and of course your DBAs are probably not doing all of these things. You're going to have different people at different levels, different levels of hardware and software. In fact, you probably have different teams of people, right? But you can see that on premises, you are responsible, your organization is responsible for providing, of course, the data center and the power and cooling that goes into that. You are responsible for building out, maintaining, and securing the network that allows, all of these systems to communicate. Of course, you have a rack and a chassis that need to be put in place. You have CPU, memory, hard disks that need to be purchased and maintained and upgraded over time. And then, of course, you have an operating system that needs to be installed and patched and maintained. You have a database engine that needs to be installed and maintained, right? There's a fair amount of work that goes into that to ensure that you are always operating in a secure environment. And then, of course, not only do you need to perform backups, it's also your responsibility to ensure that those backups are being written to a system that itself is highly durable, and that you have multiple copies of those backups, and that you have a reliable way of restoring from those backups. And then, of course, you can write your SQL query. So if your DBA is burdened by backups and database engine updates and operating system details, then they have a lot more on their plate. Now, if we were to compare this with running a database on EC2, then of course, AWS is managing the physical infrastructure. We offload the physical infrastructure burdens to AWS so that they are now managing power, cooling, network, chassis, CPU, and so on. It is still our responsibility, and this is true for other things that we'll talk about later. As far as the operating system goes, it is still your responsibility to ensure that that operating system remains patched. As new security updates come out, as new versions of an operating system come out, even though it's running on EC2 and even though it's Amazon's responsibility to install the operating system, it is your responsibility to keep it up to date. If you need to go from one version to a later version, then it's up to you to do that. And because EC2 is based on virtual machines and we have machine images, it becomes very easy for us to automate the process of updating an operating system. And considering that EC2 instances are ultimately disposable, we simply throw the instance away and replace it with a new instance. So the process of maintaining an operating system actually becomes much more efficient, much more fluid than it was on premises. We're not locked into a particular set of hardware. We have the ability to replace things much easier within EC2. And the same thing could apply to the database engine as well. If you want to go from one engine to another, you could do all of that work on some other machine, and then once all of that you're satisfied with that arrangement, then you could create a machine image and replace the existing machine very easily. Backups are also still your responsibility, but the benefit of having them on EC2, especially if you're using something like the Elastic Block Store, is that we can very easily take snapshots of those block store volumes and know that those snapshots are stored in S3, that we already have a very durable place to write those backups. And that place is not managed by us, right? And so we have far fewer responsibilities by running a relational database on EC2. Now let's compare all of this to running on RDS. With RDS, as you can see, we are offloading all of these operational burdens to Amazon. Amazon now takes over not only installing the operating system, but also patching and updating the operating system of that instance. Amazon also manages the upgrading of the database engine itself and performing backups. And so as an organization, we get to focus on our data. We get to focus on optimizing our schemas and optimizing our query statements and offloading the operational burdens to AWS. Okay, so the benefits of RDS would be that we have a reduced operational burden. As we've seen, we can offload a lot of those underlying physical and software burdens to AWS. We also get our choice of a number of popular engines, such as MySQL, SQL Server, Oracle, Postgres, MariaDB, and of course Amazon Aurora is a drop-in replacement for later versions of MySQL and Postgres. We also have a very easy ability to create read replicas. There are plenty of situations where perhaps you are doing a lot of reads, and those operations are maybe becoming a burden on the primary. And so by offloading reads to one or more servers and then allowing the primary to handle only writes, you can improve the performance of the entire system. So again, we have very easy creation of read replicas where AWS handles the creation, the maintenance of those actual servers, as well as ongoing synchronous replication. We also have a number of things that are automated by the RDS service, such as backups, operating system patches, database engine updates. So if you wanted to go from, for example, MySQL 5.5 to 5.6, minor version updates, then those things can be done automatically for you. And you get to control the window, the maintenance window in which those things happen. Of course, you may want that to happen at 1 a.m. or 5 a.m. or even noon, whenever you determine that you have, for example, lower levels of traffic. And then, of course, one last thing to talk about with RDS is that we also have a very easy ability to fail over. If you opt in to the right options, such as a multi-AZ deployment, then AWS can manage failover automatically. Whereas you would have not only just a primary, but you would also have a secondary that AWS is also managing with synchronous replication. And so if the primary fails, RDS can automatically fail over to that secondary. Right? So again, plenty of benefits by using the relational database service. Now, of course, there are plenty of times and plenty of environments, such as production, when you need a high degree of durability in your data, that you need not only backups, but also maybe even multiple copies of the data live and ready to go, so that in case one is unavailable, you can switch to another. So we have several options within RDS to help us with that. The first option would be multi-AZ deployments. With multi-AZ deployments, as you can see here, we would choose, of course, we would choose a region. In this example, we're using the Oregon region in US West 2. And for multi-AZ deployment, we need to choose or need to enable RDS to leverage multiple availability zones, right? So we are creating a VPC and creating subnets that allow us to use these two different availability zones, both US, in this example, US West 2B and 2C. And of course, you can see here that in order to do that, we've created two different subnets, right, each with their own range. And the benefit of multi-AZ deployments is that we get not only a primary, right, not just one instance, we also get a standby instance, right? And of course, AWS creates and manages both of those instances. And then AWS also manages the ongoing synchronous replication between them, right? So you can see here with multi-AZ deployments, we have multiple copies of the data that's live, that we can switch from one to the other very quickly and very easily. And so, again, with multi-AZ deployments, we gain access to not just high availability, but also fault tolerance, right? There is some built-in fault tolerance, so that if the primary fails, then we can switch over automatically or fail over to that secondary. And of course, that is Amazon handles the synchronous replication between those two, and those are built in not only on physically distinct servers, but also in physically distinct data centers. Remember, we just talked about the two different availability zones, right? And we know that those different availability zones are physically distinct centers. And so automatic failover can take place if there's a loss of a network, right? So if the primary is unreachable due to some issue with the network, if the primary is unreachable because there was an underlying compute failure or an underlying storage failure, then AWS will automatically promote the secondary to primary, switch us over, and then automatically replace the failed primary, and which then becomes the new secondary. And then, of course, this is considered a production best practice, right? So if you are running production workloads on RDS, Amazon does recommend that you opt into a multi-AZ deployment. Remember that that is not the default. If you need, that secondary instance live, if you need the ability to automatically fail over, it is up to you to choose a multi-AZ deployment. Now, another option that we have in order to help us with data durability are backups. And of course, RDS performs these backups automatically, and we know that because RDS is essentially built on top of EC2 and EBS, that those snapshots will go to S3. And we know that S3 is inherently replicated across numerous availability zones, right? So there's an even higher degree of durability when the data is stored in S3, right? And so we get to choose the window of time. When does the backup happen, right? Perhaps when you have the lowest amount of traffic or the lowest amount of work being done by the database, right? Who knows? That could be 1 a.m., 5 a.m., whenever that window is for you, you get to determine when that backup actually happens. And that is performed, the automated backups are performed once per day. And like I said, those are essentially the same thing as an EBS snapshot, right? They're taken from the volume and written to S3. And those automated backups are retained for up to 35 days. So you do get a pretty decent period of time to which you can roll back. Right? You can very easily restore an entire database from a backup. We can also perform a point-in-time restore up to a 5-minute window. And you can also copy those backups to another region, right? So if you wanted to gain an even greater degree of durability, to have, if you wanted to have 2 copies of the data live with multi-AZ deployments, you have backups in that same region, and then to take it a step further, by copying those backups to another region, now you have yet another, not just 1 copy, but ultimately, because it's NS3, you have multiple copies in that other region, thousands of miles apart. So if there is some kind of a disaster, you know that that data is still available in another region, right? So that we have, between multi-AZ deployments and automated backups, we have plenty of tools that make it very easy for us to ensure a very high degree of durability in our data with RDS. All right, so now let's review a demo of launching an Amazon RDS instance. From the AWS Management Console dashboard, we'll go to RDS. And before we create a database, we need to do one very important thing, and we need to set up the networking for our database. And so before we don't really launch we don't just launch one. We have to launch it into a network. And we already have a VPC, but we can't just select subnets directly. We have to launch the database into a subnet group. So before we can launch the database, we need to create a subnet group. And so we'll go ahead and go over here to subnet groups. We'll then say create DB subnet group. And here we'll call this one fundamentals. You will choose a name that makes sense for your particular scenario. And we'll call this one the RDS subnets for AWS live lessons. And then we'll choose the data stores VPC. And then we will choose the particular subnets that we have. We can add all the subnets in that VPC. So I've taken the liberty of creating a couple of /28 subnets in the data stores VPC. And so now we don't really choose, those subnets directly. We tell AWS, hey, here's a group of subnets. Choose the one that works best for you. And so now, once we create that, now that we have a subnet group, now we have a place within our network into which we can deploy our RDS database. All right, so let's go back to, we can go here to databases, and we don't currently have any, so let's go ahead and create a database. That will bring us to the engine, and of course we have our choice of different options. We'll talk more about some of these options like Aurora later on, but for now it doesn't really matter. I'll just go ahead and choose Postgre, and then we'll go next, and then now it's asking our use case. Do you plan to use this for production? If we were to say yes, I'm using it for production, then that will deploy a multi-AZ deployment and provisioned IOPS storage. And so a multi-AZ deployment would give us 2 instances. It would give us a live primary and a live secondary with synchronous replication between the 2. The cost for that is twice as much because you have 2 instances running. And so it is a good idea for production so that you have fault tolerance, you have the ability to fail over to a standby instance without losing data. But for a development environment, I don't think that that's necessary, at least not for this example. So we'll just go with dev test and go with a single instance. All right, we'll go next. And then, of course, we can choose our license models. We can choose the DB engine, right? If you already have code written against an older version, then you can go all the way back to 9.4.7 if you wanted to. If this is a new application you haven't really started on yet, then perhaps you want to use the latest features in the latest version. And then, of course, we choose the instance class. How much memory and CPU do we really need? We can go all the way up. You can see in some cases, pretty large machines, 64 cores, 256 gigs of RAM, and maybe certain databases may very well need that. But for our particular case, a brand new development environment with very little data or traffic probably doesn't need much, right? So we could go with a T2 Micro. And the beautiful thing about cloud computing is that, if I'm proven wrong here, then that gives me the ability to, move closer to being right, much quicker. I don't have to wait. My decision for this is not set in stone. I don't have to wait 2 to 5 years to change my mind on that. I can, if I find within the next week that, 1 core, 1 gig of RAM is not enough, then I can very easily change my mind and try 2 cores, 4 gigs, right? And if that's not enough, I could very easily go up to 8 gigs. And so again, our decisions within the cloud are not set in stone. That's the beautiful thing. So I'm going to just choose what I think is the best for this particular environment and go from there. And if monitoring and experience tells us otherwise, well, then that's okay. We won't really lose any money by changing our mind. And then, of course, we can revisit this multi-AZ deployment. Again, if we chose multi-AZ, then it would create a live replica in a different AZ. We don't really need that. And then, of course, we get to choose our storage type. It's defaulting to a general purpose SSD, very similar to EBS, because ultimately RDS is built on top of EC2 and EBS. We have access to those EBS options, right? For a development environment, a general purpose SSD is probably fine. We might want more storage, so we can say, well, let's get 100 gigs. But, and of course, I could be proven wrong, and that's okay. Through experience using this, we might realize that we actually do need more performance. And so we could come back later and say, well, you know what? We might actually need a sustained IOPS of 1,000 or 2,000 or 3,000. And so we could base that based on monitoring and based on our experience using it. So for now, I always try to go with the cheapest option. And here I imagine that I could probably easily accrue 100 gigs worth of data, or maybe not. Maybe 50 is more appropriate. We start there and then see how it goes. We can always increase that storage later. So generally, I try to aim for the cheapest solution that I think will solve the problem in a performant and reliable way, and then run it, try it out. The truth is, we don't know anything until we actually run something, and then we can go from there. And then, of course, it's telling us, this is what we think it's going to cost you based on that size machine and that much storage. Whether or not you're using provisioned IOPS, then we have an estimated cost. And then, of course, we can name the DB instance, right? So the DB instance identifier is a unique name for, it says all DB instances owned by your AWS account in that region, right? So we're going to call this one, we might call this one fundamentals. And we might call it fundamentals dev. And then somewhere else, we might have fundamentals production, right? So I typically put that in the name to help clarify, the environment or the project that it's associated with. And then, of course, we need to specify a master username. Admin is pretty common, but you could obfuscate that if you wanted to and call it something else. And then we can also specify a master password. And then from there, we'll go ahead and say next. Then the last step here is to choose our place in the network. And of course, we want to choose our data stores VPC. And then you can see there's only one security group associated with that VPC, or subnet group, excuse me. There's only one subnet group associated with that VPC, which is fundamentals, exactly the one that we just created. And then we have the option of making this database publicly accessible. Now, if you were to choose yes, then the instances would receive a public IP address, and they would be reachable from the internet. I don't typically like to do that. There may be a time and a place, in your particular scenario that you feel okay doing that, but I typically don't. So I'm going to say no. I want them to remain private. And then, of course, we can say, as far as the security groups go, let's create a new VPC security group specifically for this database. Down here under database options, we could choose to put in a name of the database. If we were to do that, the RDS service would create a database on that instance for us. I don't really need to, because we know that our code will do that, right? Our code, as a part of bootstrapping the application, would probably check for the existence of a database. If it did not exist, go ahead and create the database, create tables, populate tables, and so on, right? So that kind of thing I will leave to my application or my DBAs to do. I don't really need RDS to create a database for me. As far as the port goes, we can change this to whatever we want, right? The default for Postgres is 5432, but I could obfuscate that, right? If I wanted to put it on a completely different obfuscated port, I could, right? Or I could leave it as the default. We also have access to the ability to modify parameter groups. Parameter groups allows us to modify parameters of the database engine and use that to tune the performance of the engine. We don't have any others besides the default, but we could come back and create, if we were to go over here to parameter groups, then we could create a new parameter group and again tune the engine and then apply that to the database, reboot the database, and go from there. We also have the ability down here to enable IAMDB authentication, which means that the database user credentials would be managed through IAM. If you're using federation, then that won't be an option because your users will not exist within IAM, right? In this particular case, I don't really need to do that. I'm perfectly happy using the database realm of authentication to manage users. As far as encryption, some databases do support that, but keep in mind that while the RDS service does support encryption, it's saying here, you'll notice that it's grayed out, the selected engine or DB instance class does not support encryption. So not every engine, not every instance type supports encryption. As far as backup goes, RDS will perform automated backups once a day, and we get to choose how long those backups are retained for, anywhere from 7 days all the way up to 35 days. And then we could also select a window, right? If we have a particular period of time during which we see a minimum load on the database, then we might want to choose that time as the window. And who knows, that could be 3 a.m. UTC. Whatever makes sense for your particular scenario. Now, as far as monitoring goes, enhanced monitoring would be very useful in production, but we probably don't need that in a development environment. We probably don't need performance insights in a development environment either. But those two things could be very helpful in production. Log exports probably would be helpful in development. If you're trying to work through some kind of complex query and trying to understand, what's going on between your application, the query, the result set, and so on, then who knows, these logs might very well be helpful. So we can choose to publish the PostgreSQL log to CloudWatch logs. As far as maintenance goes, very, very much like the update or the backup window, we do get to say, well, do backups for us and also do minor version updates for us and perform them during a particular window, right? And so if we opt into this, then new minor versions will be automatically applied once they are released. And again, we do get to select that window. So we might say, you know what, I want that to happen on a Saturday at 6 a.m. UTC or 1 p.m., right? It could be 1 p.m. UTC, whatever makes sense for your particular scenario. And you could say, well, I'll give you 2 hours to make that happen. Very similar to EC2 instances, where remember EC2 instances had that termination protection. We can also opt into a deletion protection on the RDS instance. And it's just that extra layer of security, that extra safety mechanism
to help ensure that your database can't be accidentally deleted. In order, before you can delete the database, you first have to remove that deletion protection. All right, so now that we've gone through all that, let's go ahead and say create database. And it's giving us an error here. Notice this, it says master username admin cannot be used as it is a reserved word used by the engine. I did not know that, but that's the beautiful thing about these kinds of errors, right? They help us learn. And so that's totally okay. Let's just go back. I believe we might have to go back one step. Previous to admin. We'll call this one fundamentals admin. Now that we've saved that, let's go change the password. Let's go back to make sure that nothing else has changed. It looks like some of these things have changed here. Let's just make sure that none of these things have changed. Backup. We wanted a particular window that was 1 UTC, and we wanted to disable those two things. Whoops, disable that. We wanted the Postgres log to go there. We wanted this one on Saturday at 1 p.m. UTC. All right, now let's try that again. All right, so your DB instance is being created. So let's go back to RDS. Let's go to databases, and there we have it. We have our fundamentals dev Postgres instance being created. It does take a little while, and you'll see multi-AZ is no. That's exactly what we wanted. It does show the VPC that it belongs to. And of course, once this is running and in use, we could get some quick information about the CPU and current activity as well. All right. So we'll give that a moment to finish creating, and then we can take a look at different details. So we can go ahead and drill into the details, and it's still creating. And so you can see here that we don't have our endpoint and port yet. Once it finishes creating, then we will be given an endpoint that we can use to connect to. All right, so we'll just give that a few minutes to create. And there we go. We have our EC2, our RDS instance is now available. And you can see we do get instant information about the CPU, current activity, 0 current connections. And down here, we get our endpoint and our port. So now we can use this endpoint. This is a DNS endpoint that we can add to our applications. We don't rely on the IP addresses because those can change, especially in the case of failover. And so failover occurs. If this were a multi-AZ deployment, failover would occur by just continuing to use this DNS endpoint, and the RDS service would change out the IP addresses. And then, of course, from here we can go to monitoring and see, CPU utilization, DB connections, freeable memory, all of those kinds of things. So these kinds of quick access to monitoring can be really helpful in doing any kind of performance debugging, of course, along with application logs and whatever else. So, just like that, in a few minutes, we've created an RDS instance.
Now let's talk about Amazon Aurora. With Amazon Aurora, we gain access to a database that is compatible with, that is essentially a drop-in replacement for MySQL 5.6 or Postgres 9.6. And so for most use cases, not all, but most use cases, you can see companies have seen 3 to 5 times performance increase with no changes to the schema and no changes to code. Now, one of the great things about Aurora, besides being a very performant replacement for MySQL or Postgres, is that we get a storage plane up to 64 terabytes that is auto-scaled and inherently replicated, right? Now, if you were to compare this to RDS, let's say running Postgres on RDS, with RDS, if you wanted a larger storage platform, you would have to create an entirely new database instance to gain access to a larger underlying storage. But with Amazon Aurora, the storage just grows automatically. and it grows in certain increments. As your data set grows, the underlying storage volume will automatically grow to accommodate that data set. There's nothing for you to do. You don't have to pre-provision a certain amount of storage. It just automatically grows up to 64 terabytes. And there's nothing we need to do with Aurora in order to ensure that we have multiple copies that are live. It automatically maintains numerous copies across numerous availability zones, right? So a lot of that, high availability, fault tolerance, and data durability is already built in to Amazon Aurora. We also get up to 15 read replicas, very easy read replica creation, and then we also gain access to what we call Aurora Multi-Master, where we can have multiple masters to which we can write to. Not only can we have those 15 read replicas, but we can also write to multiple masters. And those are also, the replication between those two is managed by Amazon, by the Aurora service. And lastly, we also have Aurora Serverless. Now with normal Aurora, even though Amazon is managing all of the underlying infrastructure, the storage plane, the compute service, and everything else, there's still something for us to manage. There's still an instance of Aurora that we need to create and modify options on. But with Aurora Serverless, there isn't. There's nothing there until we actually need it. So Aurora Serverless is more like on demand. When our application needs that database engine, it boots up, it makes itself available, we do our writes, we do our reads, and then when we don't need it anymore, it goes away. So we have a lot of really, and of course we'll take a closer look at Aurora Serverless in an upcoming section. But of course, remember that the key point here is that Amazon Aurora can be a very performant drop-in replacement for MySQL or Postgres. Now let's talk about Amazon Aurora Serverless. So Amazon Aurora Serverless provides us with on-demand, auto-scaled Aurora database. And so it's currently available for the MySQL compatible edition. The Postgres compatible edition is currently, as of the time of this recording, is in preview. But I suspect that will be over the next several months or maybe the next year, that will eventually become generally available. And so if we were to compare Aurora Serverless with standard Aurora or some other option within RDS, then we would see that within RDS or within standard Aurora, there is still an instance of something. There is still something running, a server running, an instance running within our environment that we are paying for on an hourly basis, even if we aren't using it, right? So there's the potential for us to be paying for a machine that is sitting idle. But with Aurora Serverless, as the name suggests, there is no server, there is no instance within our environment. And so again, just to clarify, yes, we know there has to be a server somewhere, but as far as our organization is concerned, there is no server for us to manage. That's why we call it serverless. And so the way that Aurora works is that when our application needs connectivity to a database, it appears. And so Aurora Serverless will automatically start that database. And then when our application needs more resources than is currently being provided, Aurora Serverless will automatically scale that database to accommodate the amount of traffic that we are sending it. And then when our application no longer needs that database, Aurora Serverless will shut it down. And so again, you can see it's an on-demand auto-scaling service. And so another beautiful thing about this is that we pay per second while it's active. And when it shuts down, we only pay for the storage. And so there's never a time when we are paying for idle CPU. Just like standard Amazon Aurora, we still gain access to that 6-way replication across multiple AZs. So we know that the data that we are writing to Aurora Serverless is still highly durable and highly available. And so Aurora Serverless is really ideal for a number of use cases, such as infrequent use. Perhaps you have an application that doesn't need constant access to a database. It needs access every so often. Or perhaps you have variable workloads, highly variable workloads, where perhaps you operate at some kind of low baseline, and then at certain times of day there are these short spikes. And so instead of having with RDS or standard Aurora, you would have to provision for peak and provision for those spikes. But with Aurora Serverless, you could count on the auto-scaling nature to scale out for those spikes and scale back down when your traffic comes back down to a normal level. You could also use Aurora Serverless for development environments. You know, perhaps you're developing and maybe there could be long periods of time where developers are writing code but not actually running anything. And so when they do need to run and test connectivity and test, you know, their code against that database, it appears when they need it, and it shuts down when they no longer need it. So as you can see, we have with Amazon Aurora and Amazon Aurora Serverless, we have some really great tools if we want to leverage MySQL or Postgres compatible database environments. Now let's review an introduction to Amazon DynamoDB. Now, of course, with DynamoDB, we gain access to a fully managed NoSQL data store. Again, like we talked about earlier, DynamoDB is in the same family as systems like Cassandra and MongoDB and others in that NoSQL type of database. Now, of course, DynamoDB is exclusively backed by SSDs. So we know that when we write any data written to this table is written to multiple nodes exclusively backed by SSD storage to help ensure that our reads and writes are as fast as they can be. And of course, DynamoDB is capable of single-digit millisecond response if we are using an indexed-based query. If we're doing a full table scan, then we can't expect a single-digit millisecond response, but we can if we are using an index-based query. And of course, DynamoDB, like most managed services, is inherently highly available and fault tolerant. Those kinds of things are already built in. Unlike RDS, where we have to opt in to multi-AZ deployments in order to gain fault tolerance, with DynamoDB, it's already built in. There's nothing for us to opt into. It's just a part of the service. And so one of the ways that DynamoDB achieves that is to replicate the data not only across numerous drives, but across numerous availability zones, or essentially numerous data centers. And so that the DynamoDB service is resilient not only to the loss of a device, but also to the loss of a data center. Now, with DynamoDB, we don't need to provision storage. Storage just grows automatically, but we do need to provision the throughput. And throughput is essentially measured in terms of reads per second and writes per second, right? So what is our workload? Some tables may be read heavy, some may be write heavy, some may be balanced, but every table will do a certain number of reads per second and writes per second. And that really is probably the greatest thing that contributes to our cost. Yes, we pay for storage, but we also pay for the provisioned throughput. Now, as far as data models in Amazon DynamoDB go, we have tables that are comprised of items that are comprised of attributes. And that's basically it. That's what we have. We don't have any foreign keys or anything like that. There are no joins and no relationships. Now, of course, you could, within your own application, you could pull data from two different tables and join that within your application. But again, DynamoDB will not do that for you. It inherently has no knowledge of any relationships or foreign keys. It's also a schemaless design, right? DynamoDB does not support any kind of a schema except for maybe the primary key, right? The primary key is the only thing that you have to specify what attribute for that item will be the primary key, and the data type for that attribute. But beyond that, if you wanted to, you could have every item in that table have a completely different set of attributes, right? If your application needs a schema, then your application would have to enforce that schema. But DynamoDB will not enforce any kind of a schema outside of the primary key or an index. And so, speaking of the primary key, every item does require a unique primary key, and that is indexed. And that's one of the ways that we can achieve that single-digit millisecond response is by querying based on the primary key. And then, of course, if we need to be able to query on some other attribute other than the primary key, we can create secondary indexes. We have local secondary indexes and global secondary indexes. And those give us a way, again, to query, to make fast single-digit millisecond queries based on an attribute other than the primary key. Another nice thing about DynamoDB is that there is no limit to the size of a table. You can just throw data at this table, and it can grow into the petabytes and beyond, and there's nothing you need to do. Amazon will not impose a limit on that, and there's nothing we need to do to go and provision more storage. It just happens automatically. There is a 400K limit per item, so that is something to keep in mind. You will not be storing blobs within DynamoDB. If you do have something larger than that, maybe a large document of some kind that's in the megs or gigs, then a common practice would be to store that large blob in something like S3 and then store metadata about that in DynamoDB so that you could perform your searches in DynamoDB, reference the key, and then download that blob from S3. DynamoDB, a recent addition to DynamoDB in late 2018, was the ability to support transactions, right? So DynamoDB can be, ACID compliant if you need transactions. So with DynamoDB transactions, this will allow you to write multiple updates or inserts across multiple tables, and then give you ability to roll back if any modification to any one table fails, right? So that's a very powerful feature that was released fairly recently, again here in late 2018. Now, taking a closer look at the data model within DynamoDB, again, like we talked about, we have a table. Now, in terms of data models in Amazon DynamoDB, taking a closer look here, again, we've talked about how we have tables, right? And here in this example, we have a users table. And of course, here, this would be an item. And then each one of these things, we would have an attribute, a zip attribute, a date of birth attribute, and a name attribute. Now, because DynamoDB is schemaless, it's possible that each item here could have a completely different set of attributes. That is probably not necessarily the best for our application if our application needs something predictable, but as far as DynamoDB is concerned, it doesn't care, right? If you want to do that, you can. The only thing in this example that we have to do would be to ensure that all of our items have the name attribute as in this example as a string value, right? Because that in this example we've set as the primary key. Now, we have different options when it comes to primary keys in DynamoDB. Now, here in this example where the primary key is a partition key, you'll notice that it's just one value. It's only the name attribute. But in another table, we could also create a primary key as a composite, right? Remember that a composite key is the combination of two different attributes or two different fields, and it's the unique combination of those two things that make that primary key unique. And so with DynamoDB, we have the ability to create a primary key that is the combination of a partition key and a sort key. So you'll see here in the top table, Jane Doe would have to be unique. But in this bottom table in relationships, Jane Doe is not unique, but the combination of Jane Doe and Amy and the combination of Jane Doe and Bob Smith are each unique, right? So that's a composite key. And so the ability to do this, or what this gives us, is the ability to query this table and say, well, show me all of the records where name equals Jane.Doe. So that would give me all of Jane Doe's friends. And then, of course, as the name suggests, the sort key here, as the sort key suggests, we could then use that friend attribute to sort that list in alphabetical order. And of course, we will take a closer look at some of these things as the course progresses, as we get into the demo and other things, right? So again, Amazon DynamoDB is Amazon's fully managed NoSQL data store, and we'll take a closer look at it as we move along.
Now let's review a demo of creating an Amazon DynamoDB table.
From the console dashboard, we will go to DynamoDB. And of course, we don't have any tables in this region yet. So before we create a table, I just want to show you in the documentation. Let me just switch tabs here. In the AWS documentation for DynamoDB, you can find example tables and example data. So if, being new to DynamoDB, if you want to, learn more about programming against that particular data store, then you can look at the documentation for example tables and data and example indexes and other kinds of things. So we will go ahead and use product catalog for our table name, and we will use ID as a number for the primary key. All right. So I'll go ahead and copy that, and then we'll say create table, and then we'll use product catalog for the table name, and then DynamoDB being schemaless does not require us to specify the columns. Every item that we add to that table could have completely different attributes or columns. That probably wouldn't work very well for our application, but as far as DynamoDB is concerned, it doesn't enforce any kind of schema except for the primary key. And so again, here in the documentation, the primary key is just a simple ID as a number. You could use other fields for the forum table. It would be name as a string. And then you could also make a composite key. And the composite key would be a combination of two different fields. And then, of course, if you define these as being a part of the primary key, then that is really the only part of any kind of schema that you might think of that is enforced, right? So every item would have to have an attribute with that particular name on it, and it would have to be unique, right? So let's go back here to the table and say ID as a number, and if we were to create one of those other tables that had a composite key, then the composite key, it would be a composite of the partition key plus a sort key. We won't worry about that for now. We'll just keep it simple. And then, of course, down here it says we could use default settings. And the default settings are no secondary indexes. We'll talk more about those in a later lesson. And then we're going to set provision capacity to 5 reads and 5 writes. For a demo, and if you were just creating like a dev environment, then that's probably fine. You could probably even go as low as, if we wanted to have more control over this, then we could go to probably even, well, it looks like they're not going to let us go lower than that, but even that is only going to cost us about $3 a month in capacity. We do have the option to turn on auto scaling so that DynamoDB can scale the capacity. Remember, what we're paying for is a combination of read capacity units and write capacity units. And so, if what's actually happening is greater than or less than what we're paying for, then we can use auto scaling to help match what is provisioned with what is actually happening, and that could save us money. So I'm going to turn those off. We don't really have a need for that in this demo, but in a production use case, you may very well want that. We also have the ability to encrypt our data at rest, right? So here, the default is to use a customer master, an AWS owned customer master key, or you can use KMS. And this is a customer master key using underneath the KMS service. And then, of course, we could go create the table. It says table is being created, so let's go ahead. It usually doesn't take very long. And again, we don't necessarily have to refresh the whole screen. Most services give us this little refresh button, and there we go, just like that, pretty quick. And so now we can review those table details. We have our table name, and then our primary key is ID number, and then we're using KMS to help with encryption at rest. Let's see here. And then we have provisioning, 5 reads, 5 writes with autoscaling disabled. And of course, this table is living in the Ohio region. And then again, I've mentioned this earlier, the Amazon resource name, the ARN, you may very well need to refer to this in your code, right? So this is an important attribute of this table, is the ARN. That's how we would identify in our code that that's the table we want to write to. Now, in terms of storage, you'll notice that we did not need to specify storage. And that's because we don't provision storage within DynamoDB. Storage just grows automatically. The storage plane just autoscales as we add more data. DynamoDB just adds more resources to hold that data. And you can see here that we don't have any items in this table yet. Right, so let's go ahead and do that real quick. I'm going to open up the console or open up my terminal and use this sample data. This developer guide also gives us some sample data here, and I'm going to open up the terminal and use the command line interface to quickly load a number of records into that table. All right, so with my terminal in place, now I'll show you that I have a folder here called sample data, and in there we have a few JSON files that Amazon gives us. Again, you can download that from the website, from the AWS documentation. You can generally download zip files of sample data, and then they show you exactly what to do in order to load that. And of course, you can use these kinds of things to automate the creation and population of tables. And you don't have to do it with the CLI. These are showing you how to do it with the CLI tools, but you could do it with the SDKs, and AWS, provides SDKs for most of the popular languages. So we'll go ahead and copy that, and we'll go back to our terminal, and we'll go ahead and try this. So we're saying, that we're going to use the AWS CLI tools, using the DynamoDB service to write a number of items. We're doing a batch write, and we're saying that we're using the product catalog JSON here. So let's go ahead and try that. There we go. And now it's telling us the fact that we saw this as opposed to an error means that data should have loaded. Had we gotten an error, we would, of course, seen that. So let's go back to our DynamoDB, and if we do a refresh here, then there we go. We have some records in there, and we will continue to explore this. We will take a look at scan and query operations. The ability to query this table for particular items. We will look at that here in an upcoming demo.
Now let's take a look at a demo of performing scan and query operations.
All right, so we're back here in DynamoDB, and here is the product catalog table that we created earlier. And so if we take a look at that, so we created this table, and we also loaded some data into that table. So we can explore that by going to the Items tab, and of course, we don't have a ton of data, but it's enough to allow us to take a look at these operations. And so with the two primary operations that we have are scan and query. So scan operations, as the name suggests, will perform a full table scan. And so, there may be a time to do that. And so if we were to, for example, do a scan and look for, let's say, the title of a book, right? Let's look for where title is greater than 18. Let's see if we can do that. So the attribute will be title. And the reason that we are doing a scan here is because we don't have an index on title. The only index that we have is ID. And so without an index, we can't do a query. And so we have to use a scan. And then we're scanning using a filter, right? So we're saying that we're scanning the table looking for items where the title attribute equals, and with a we can set it to, we're looking for these as string values, and then we can also say begins with 18. And so if we were to do that and start the search, there you go. Now we're getting all of the titles that begin with 18, and it appeared to come back fast. And technically it did. That's because we don't have a whole lot of records. But if you were into the millions of records, and in larger scale applications, it's very easy to get into the millions and millions of records, maybe even into the hundreds of millions or billions. And in those cases, doing a scan operation like that, where you're literally doing a full table scan, analyzing every single record in the table, and asking that question, does this begin with 18? Does this begin with 18? To do that a billion times will take a long time. And so, DynamoDB is capable of single-digit millisecond latency, but only when we use the query type of operation. So if we were to do a query, then you'll notice here the difference. Watch what happens, right? With a scan, we're able to basically say, well, I want to filter on just about any attribute. And you could also combine that. Let's just try this one more time before we move on. We could also say that brand is a string that equals or begins with, or let's just say contains mountain, right? And then if we start that search, then now we retrieve that one record. And so again, that's a full table scan. And so notice the difference here, that when we go from scan to query, now it's requiring us to enter the partition key, or the primary key. And it's saying, you can only do a query on an index. And in this particular case, the ID is the only index, the primary key being the only index. And so you'll also notice that we don't get any choice other than an equals. So the scan operations provide us with the ability to do a number of different kinds of comparison operators, right? Equals, not equals, less than, greater than, between, all those kinds of things. But you don't get that kind of flexibility with the partition key or the primary key. So here, if we were to remove these, and then we could say, well, I want to query based on the ID. So show me 203, start the search, and just like that, it comes back. That kind of operation where you are basing it on an index is going to be much, much faster. So that's the general recommended best practices, that we try our best to find a primary key that allows us to do that kind of query. And the other thing to keep in mind with DynamoDB, just based on the distributed nature of it, we talk a lot more about this in other videos, like the solutions architect video. You really need to give some thought to this ID. The kind of value that you're using there. If one of these products were to become much more popular, let's say that there's this particular product, ID 203 became so popular that millions and millions of people were looking at it, then the fact that this one ID is getting so much more traffic than the other IDs would mean that we would end up with a hot key, where one key is getting a lot of traffic, and then as a result we would end up with a hot partition. And we could see some performance degradation with that kind of thing. And so ideally, we have IDs that allow the demand, whatever that is, the reads and the writes, to be evenly spread across the cluster that is powering this DynamoDB table. Okay, so let's go back to our scan, and here we don't have any filters. Let's go ahead and do that, and then without any filters, it just gives us everything. So now we can see essentially, all the records or there in the table. It will paginate, and so we can create indexes after the fact, global indexes after the fact. There is a local secondary index and a global secondary indexes. Local secondary indexes can only be created at the time you create the table. Global secondary indexes can be created at any time. So if we were to, let's go back to the items real quick, and I'll show you. If we wanted to query this table, and if we find that we were regularly querying the table based on the title, then we would want to create an index for that. Right? We don't want to rely on the scan operation to return, fast results, because once this is big enough, it just won't. And so in this particular case, we could create a global secondary index for the title attribute, right? So let's see if we can do that real quick. Let's create an index, and in this particular case, let's just verify that title. Yep, so it's just title. All right, so indexes, create, title. And it is a string. And in terms of projected attributes, we can go ahead and say all. That way we don't, if we only projected the keys, then we would have to pull the key from the index and then use the key to pull the data from the table. But if we project all of the attributes into the index, then we can just get everything from the index rather than having to go and join it to the to the table in our application. And we do have the ability to change the capacity units. For a global index, the throughput capacity that we provisioned is separate from the table. So here I might say, well, you know what, let's just go with 2 and 2 for now for the sake of this demo. And then we'll go ahead and say create the index. And it will take a few minutes for that to create. So we'll go ahead and give that just a few minutes, and we'll fast forward to that creation. All right, and there we go. Now our global secondary index for the title is now active. That did take a few minutes. It took a little bit longer than it took to create the table. And again, just you can see here that it has one partition key. So you can think of, for those of us who might be, coming from a background in relational databases, you can think of a global secondary index as sort of a very similar to a materialized view. So as changes are made to the table, those changes are then reflected in the global secondary index. And so if we were to come back here to our items, and we refresh this, we don't really get the console. Let's just try to refresh this. I don't think the console gives us the ability to query based on, yeah, there we go. Okay, so it does. Now that we have our index active, and by refreshing the page here, now we have the ability to query based on the title index, right? So now if we do a query, now it's saying title as a string equals, and then of course we have to know the title of the book. So if we wanted to get information based on the exact title of a book, such as book 101 title, and we run that search, then very quickly, in single-digit milliseconds, we could get that result back. So that's an example of using queries. Again, queries can leverage some type of an index. So the primary key is an index, and then we created a secondary index on the title attribute. And so by using queries, we can get very fast single-digit millisecond response. Otherwise, maybe there's a time and a place when you need to, but just remember that scan operations are full table scans. And when you have a lot of items, it will add latency to those results.
Now let's review an introduction to Amazon Elasticache. So with Amazon Elasticache, we gain access to a fully managed in-memory cache. Now, with in-memory caching, a classic example of this type of use case would be, let's say that you had a relational database where certain queries were running slow. And by slow, I mean maybe upwards of 1 second. And even though you may have indexed them by the book and you're querying them by the book, there's nothing more that you can do. And I've seen this plenty of times where just the nature of the data means that the query is running slow. And so the idea there is that you take the result set from the database and you store that result set in memory. And when you have a fleet, let's say you have a fleet of web servers, maybe dozens or hundreds of web servers, you don't want each one of them storing those things in memory. You want the same result set available to all of them. And so you store that result set in memory someplace central, like an in-memory caching server specifically designed for in-memory cache. And so very much like RDS, Elasticache gives us that fully managed platform for running that in-memory cache. And so very much like RDS, we are offloading the operational burdens of the operating system and the cache engine to the Elasticache service. And so AWS then becomes responsible for doing patches to the operating system as well as performing updates to the actual engine. And with minor updates, those can be performed automatically. Most of the time, those can be done in place during a maintenance window. Elasticache also supports clustering so that you can add numerous nodes to an existing cluster in order to gain access to larger sets of memory, larger than any one server can actually handle. In the case of Elasticache, we can gain terabytes worth of in-memory storage. And now with Elasticache, we do get a couple of different options of software. We have the ability to run Redis or Memcached. With Redis is more of an in-memory database, right? Because we gain access to multiple data types like hashes, sets, sorted sets. We can also do atomic operations, right? So we can do in-place updates and increments and decrements. We can do in-memory sorting. And in a number of different operations that make Redis a really, really powerful in-memory cache. Well, in in-memory database, it's more than just a cache, right? And Redis is also back to disk. Every so often, and of course this is configurable, but every so often the contents of memory can be written to disk so that if there were some type of an issue or an error with that underlying host, then you could recover that by either replacing the host or rebooting it and allowing memory to be repopulated from disk. Redis also, because it is back to disk, it also gives us the ability to automate the backups of that disk and, like I mentioned before, automatically patching the operating system. Now we also have Memcached. Memcached is very popular, it's very performant, but it is more of a simple in-memory cache rather than, it doesn't have any kind of database functionality like Redis does. It's a simple key value store. Key equals value, that's all you get. You don't gain access to data types like hashes or sets or anything beyond simple key equals value. And of course, Memcache is not back to disk. So if a node were to fail, anything in its memory would be completely gone. There's no way to recover that from Memcache. But we still get automated patching of the operating system and automated minor updates to the engine itself. So again, keep that in mind that if you have scenarios in which you have certain types of data, and again, it could be a result set from a relational database query. It could be rendered HTML. Maybe there are pages within your web application that take longer to render, and you simply want whatever it is, whatever that data is, you can take that and store it in memory in order to make that or in order to deliver that to your end user much faster than waiting on the database to run the query or waiting on your web server to render that HTML. Now, in the case of something like Redis, where you have in-memory sorting, where you have atomic operations, there's also the ability to, instead of relying on a relational database or a NoSQL data store where everything is going to disk directly, the fact that with something like Redis, the fact that everything is happening directly in memory means that you could potentially see microsecond latency. So with something like Redis, even though you might not be caching, result sets, you could simply be storing a data set in memory so that the functionality is much, much faster than it would be with other data stores, right? So keep in mind Amazon Elasticache for doing things in memory. Now let's review an introduction to Amazon Redshift. With Amazon Redshift, we gain a fully managed data warehouse, a petabyte scale data warehouse, upwards of 2 petabytes can run in a single cluster within Amazon Redshift. And then, of course, Redshift is based on Postgres 8.02. And so AWS took a fork of Postgres 8.02 and made their own modifications in order to support certain types of technologies and allow us to run complex ad hoc queries against those petabyte-sized data sets. Now, because it is a fork of Postgres 8.02, it is SQL compliant. It supports all of the data types in the SQL language that was supported by Postgres 8.02. And of course, because of that, you can connect to a Redshift cluster using existing business intelligence tools that support JDBC and ODBC drivers. Now, one of the things that make Redshift really performant is that AWS took that fork of Postgres 8.02 and they added columnar storage. Columnar storage, as opposed to row-based storage, makes much more efficient use of the actual underlying storage, as well as more efficient use of input-output operations. So we can retrieve a similar amount of data from columnar storage with fewer I/O operations as opposed to using row-based storage, right? We can make more efficient use of memory by using columnar storage as well. And so along with columnar storage, Redshift also added parallel queries. So with Redshift, we can create clusters of nodes so that our queries are being run in parallel across all of those nodes. That is one of the ways that we can achieve very fast results across very large data sets. No one server is running the query. It's actually being run in parallel across those many nodes, each using columnar storage. And so with Amazon Redshift, keep in mind that Redshift is not meant for online transactional processing. It's ideal for online analytical processing. So many workloads, such as e-commerce, for example, where you do have transactional processing happening. For the transactional processing, you may want to use something like RDS or Aurora or even DynamoDB. But then when later you want to run analytics on that data, then you might look to Redshift because it's ideal for online analytical processing as opposed to transactional processing. So again, if you have a large, very large data set, and perhaps maybe you have smaller data sets that are spread out across numerous databases. Perhaps you have small data sets that are in NoSQL and relational and graph databases, and you want to pull all of that into one place so that you can run complex ad hoc queries across vast data sets. Take a look at Amazon Redshift. Now let's review an introduction to Amazon Neptune. Now with Amazon Neptune, we gain access to a fully managed graph database. And this graph database is optimized for storing relationships, potentially billions of relationships. Now, when we talk about relationships, it's important to understand that we're not necessarily talking about relational data. If we were to compare this to a relational database where we have relational data, if, for example, in a relational database, you may have a user record and then a list of orders, right? You may have a one-to-many, a list of orders that that user placed in an e-commerce kind of situation. And then each order may have a one-to-many with the list of items that were in that order, right? And so you would, in order to form relationships, in order to form a relationship between a user and a product that they purchased, you have to derive that from that relational data, right? So relational data is not quite the same thing as relationship data is in a graph database, right? And so a graph database is more easily allows us to form a direct relationship between a user and a product that they purchased, a direct relationship between a user and a movie that they watched, right? And so when you think about those kinds of data sets, right, you think about shopping on Amazon.com, there's a relationship between myself and the products that I've actually purchased. There's a relationship between myself and maybe my friends. And then there's a relationship between other people of the similar demographic and the products that they bought. If we take this kind of thinking to something like Netflix or a social graph, you can see that there's relationships between myself and my friends, between myself and the movies that I've watched, and then a relationship between my friends and the movies that they've watched, right? So we can take this kind of relationship data, and one of the classic use cases for it is creating recommendation engines, right? We can use relationships to see, well, if I have a relationship between this movie and a friend has a relationship between this movie, then perhaps I will like a movie that they like, and maybe they would like one that I like, right? That's just one classic example. And so with Amazon Neptune, when you have a use case for relationship type of data and you want to be able to transverse that graph of relationships and derive meaning from that, then of course we need a model for storing that data. And Amazon Neptune supports a number of different graph models, including property graph and RDF. It also supports a couple of different query languages, including Apache, Tinkerpop, Gremlin, and Sparkle. So when we actually want to program against that database and write a language that allows us to traverse the relationship graph, we could write that and express that in Tinkerpop, Gremlin, or Sparkle. And of course, like other services similar to DynamoDB and S3 and Aurora and so on, Amazon Neptune is also, the data that we write to these tables is also replicated across multiple AZs. So as you can see, durability, fault tolerance, high availability is already built in. Neptune also performs a continuous backup to S3. So unlike RDS, where we have to specify a maintenance window, backups are done continuously to S3. Neptune also supports, very much like Aurora, Neptune also supports up to 15 read replicas. So again, if we have a very read-heavy application that's constantly pulling and querying these relationships, then we can offload that to the read replicas and allow the master to focus on writes. And by doing that, we can increase the performance for the system as a whole. So again, when you think about performing or modeling and querying direct relationships between persons and products and persons and movies, or between different people, for example, in a social graph, think about Amazon Neptune. Now let's review a use case of using databases for e-commerce. So you'll see that there's a fair amount going on here in this diagram. We have a number of different types of databases for different types of data and different types of usage patterns. So first, over here in the top left corner, you'll see that we have our e-commerce application, which is a load-balanced application. We're using here perhaps an application load balancer. We could also use a network load balancer.
And then, of course, we would have an auto-scaled fleet of EC2 instances. And on those, we could run a monolithic application or a series of microservices. Now, just moving down and across, we can see that we're leveraging DynamoDB for a number of different things. First, we might be storing different campaign events. So your marketing team may be running different marketing campaigns to target different demographics. And we want to track all of the people that come in through those campaigns. So perhaps they land on a particular landing page, or they carry with them some information about that campaign as to where it actually came from. You know, where did they click on that ad? Or where did they click on some kind of a link in order to get them to our site, to that particular landing page? And so we can record that kind of information very quickly and very easily with DynamoDB. The same is true for something like affiliate tracking. So let's say that you have an affiliate program for your particular online store, and you have your affiliates out there are putting links on their website, on their blog, or what have you. And as someone clicks that link and follows that link through to your site and makes a purchase, the affiliate gets a commission. And so you have to track, you know, what users came in through what affiliate link, and then, of course, tie that purchase back to that affiliate and then be able to pay them that commission. And so again, DynamoDB is very well suited for very quickly ingesting that kind of information, that kind of data. And then we might also use DynamoDB to track user history. As they view different products, as they search for different products, we store that in DynamoDB so that we can perform a number of different things out of that. In the least, we could show them, hey, these are the products that you looked at, and make it easy for them to go back to the product that they were recently looking at, rather than them having to dig and find it all over again. So there's, for the user experience, there's just a matter of making shopping more convenient for them, sort of greasing the skids, as you will, making it easy for them to find that product and then actually buy it. And then, of course, there's also that kind of data could also tie into a recommendation engine. If you're searching for something, then maybe we want, you know, some days later, if you haven't purchased it, then maybe we want to send an email to say, hey, we saw that you were searching for this, it's on sale, the price has changed, or if you're searching for this, you might also like these other things that are related, right? And then, of course, as users are actually doing their shopping and placing things in their cart, we could record that information as well. So this is all very rich information that we can use to establish trends, to help recommend different products to users directly, or to perhaps users that are somehow related to each other. Now, other types of data, looking over here to RDS, we would be running RDS in production. We would run that in a multi-AZ deployment. Again, keep in mind that a multi-AZ deployment means that we are running both a primary and a secondary. These are two completely physically distinct servers in physically distinct data centers. And then, of course, AWS is handling the synchronous replication between those two. And so we have two copies of our data that are live. Now, it's not shown on this diagram, but we could also say that we are relying on those automated backups going to S3 for the sake of disaster recovery, giving us a greater degree of durability in that data. Now, in a relational database, that may be more well suited for data like user accounts and the product catalog and inventory, right? So that as users place their orders, then there's now this relationship between the order that they placed, the user, the order that was placed, and the inventory that is now available. And that type of thing, and then of course all of the billing that's related to that as well, that the actual financial transaction, all of that we may very well need to be ACID compliant, right? We may want to record all of that using a transaction with the ability to roll back. Now, of course, keep in mind that a later update to DynamoDB supports transactions, but your team may feel more comfortable using a relational database for that kind of thing. It's all up to you, right? Now, in this particular case, because we do have the product catalog there, we could assume that it would make sense that this application would be performing a lot of reads. So at least some tables would be very read heavy, such as the product catalog, if people are constantly querying that, looking for items. Now, we could potentially share the product catalog with DynamoDB so that we could read it from there, or we could create read replicas so that all of our application reads are performed by the read replicas. So as users are browsing the site, as they are searching for products, those reads are being pulled from the read replicas, and that would reduce the load on the primary. And then, of course, we could allow the primary to handle only writes, right? So by splitting reads off to read replicas, we could increase the performance for the entire system. Now, as far as a cache, we could have certain things. For example, we may have different types of pages or entire pages, HTML pages that are built out of both perhaps a slower query, a very complex query, and rendered HTML. We may also have parts of pages, right? Just related products that are only subcomponents of different pages, right? So the related products may also be either a SQL query and the result set of that, or the result set and the rendered HTML. So either way, if those kinds of things are running a little bit slower, then we can store that in memory. And our application would first look to the cache and say, hey, do you have this thing that I'm looking for? If it does, then we can return that very, very quickly, right? And maybe even in microsecond latency, depending on the engine that we're using and the nature of that particular data. If it doesn't, then we could, of course, go to the relational database and pull that, or we would pull it from the read replica, and then, of course, we would do our writes to the master, to the primary. And then, of course, we have Redshift. And Redshift, again, is Amazon's petabyte scale data warehouse. And so with Redshift, we want to be able to run analytical queries and analyze all of this data that we have in these various places, right? So we want to be able to pull in all of this information from DynamoDB, campaigns, affiliate tracking, product view history, search history, shopping carts. We pull all of that data in. We could use potentially data pipeline or Lambda or something else to help us extract, transform, and load between DynamoDB and Redshift. And then we could do the same thing, pull data in from our relational database, and now we have all of that data in one place, in one data warehouse. And now our data analytics team can use their existing whatever business intelligence tools they want to use from their local machines, on premises or at home, wherever they are. They can connect to Redshift using those ODBC or JDBC drivers and run whatever complex ad hoc queries that they can think of in order to derive meaning out of all of this data, right? So, of course, we didn't show it here in this particular diagram. We didn't really have room, but going back to some of the other databases that we've talked about, such as Neptune, for example, Neptune would have a very clear place here in terms of recording relationships between users and the products that they've purchased or products that they've searched for, and that would also help us create a recommendation engine. So, as you can see, we have a number of different great options within AWS to store our data. Many of them are fully managed services, allowing us to offload the operational burden. If you notice here in this diagram, there's very little operational burden. In fact, the only operational burden that we would have would be essentially the operating systems for our EC2 instances over here. And so you can see that we can run a fairly complex type of scenario, in this example, e-commerce, with a smaller team, right? By offloading all of those burdens to AWS, allowing AWS to manage many of these services for us.
Besides security, perhaps the most important requirement of any infrastructure is availability. After all, what good is an application that isn't running or can't scale to meet demand? In this lesson, we will explore Amazon Elastic Load Balancing and autoscaling and discuss concepts pertinent to achieving a superior degree of high availability and fault tolerance.
Now let's review an introduction to Elastic Load Balancing. Now before we get to the details of Elastic Load Balancing itself, let's first take a look at the challenges of running an application on a single instance. So in this example, you can see here that we have our VPC, we have a region, and in that region we've created our network, and that network is leveraging a single availability zone. And in that availability zone, we would launch an EC2 instance, and that instance would be running essentially everything. It would have our monolithic application, it would have our database, and it would also house static content. Our users would then come directly through our internet gateway and connect directly to our EC2 instance. Now, I don't really like speaking in terms of right and wrong. I'm not going to say that this is wrong. I suspect that there are thousands of websites, many WordPress and Drupal installations that are running exactly this way. And, you know, I think in terms of whether it works or it doesn't work, right? You can do this, but I also like to think about the consequences, and I encourage you to think about the consequences of running an application on one instance, right? So the consequences of running an application on one instance we have to ask ourselves, what happens when this EC2 instance fails? Remember, we talked about earlier that EC2 instances are ultimately disposable. Even if we don't think of them that way, even if we don't treat them that way, they are. There could be an underlying issue with the physical host. That physical host could have some kind of a problem, and that problem could come up at any time and is completely outside of our control. And so we cannot rely on any one instance living for any period of time. And I've been, as of the time of this video, in fact, recording here in February of 2019, it's actually 10 years this month that I started using AWS. And in that decade, I've seen instances live for 4 hours, 4 days, and 4 years, and everything in between. It can be totally unpredictable as to when an EC2 instance might fail. And so we're not trying to prevent failure. We're embracing the fact that it will happen at some point, and we are looking at ways to mitigate that failure. How do we allow our application to continue to operate, or how do we allow our application to get back up and running as quickly as possible, right? So back to this example, we have to assume that at some point this one instance will fail. And by running an application on one instance, there is no degree of fault tolerance whatsoever. You will experience downtime, right? You will experience downtime for as long as it takes you to recover that instance, to replace it with a new one, to install that application, to install the database and the static content, and then of course the question becomes, where is that data, right? And so there are ways that we could go about improving that time or shortening the time it takes to get that instance back up and running. But within the context of elastic load balancing, load balancers allow us to distribute traffic so that we do have fault tolerance. So taking a look at this diagram, we can see here that, again, we are leveraging a particular region, and we have a network that allows us to use multiple availability zones for the sake of being resilient, not only to the loss of any one individual EC2 instance, but also resilient to the loss of an entire data center, right? Very much like EC2 instances, it's also possible
highly unlikely, but possible that an entire data center could be offline due to some kind of a problem, be it natural disaster or something else, right? So we want to be resilient, again, not only to the loss of an instance, but also to the loss of a data center. So here, in this example, by running our application on 2 EC2 instances, you'll notice that they each have their own data volumes, right? And so now we could rely on, if we did need to store some type of data, we could store it on the EBS volume. That way, if the instance went away, then the volume would remain. And so now we have the ability to have both of these instances behind some type of a load balancer. We're going to talk about the options of those here in just a little bit. We have several different options to choose from. But the load balancer allows us to spread those requests. So as our users make requests, those requests then pass through the load balancer and they get distributed here among these backend instances. And so now we do have fault tolerance. If we were to lose one of these instances, we would still have another instance, right? So the load balancer gives us fault tolerance. It gives us the ability to continue accepting requests in the case of a failure. It allows our application to continue running even when something has failed, right? And then, of course, we could also combine that with other things like autoscaling to automatically replace that instance and create self-healing environments, which we will talk about as the course goes on, right? A load balancer, as many of us may already know, essentially distributes requests and traffic, right? So our users are sending us requests. We point all of our users, we point them to the load balancer, and the load balancer then distributes those requests among all of our backend instances. We could have 200 or 2,000 instances behind that load balancer, and it will continue to maintain as even a spread as possible according to the options that we've chosen. Any one elastic load balancer does exist in a single region. Keep that in mind, that a common misconception that I see in different classes that I teach is that it's often assumed that load balancers can span multiple regions, but that's not true. Load balancers exist in one region. If we wanted to load balance between different regions, we would have to use DNS or Route 53, right? So one load balancer exists in one region, but it does span every availability zone, or at least it can make use of every availability zone in that region. And so the load balancer, even though it appears to us as one device, we create one load balancer, and in the console or in the CLI tools, it may look like one device, but behind the scenes, it's actually comprised of numerous nodes. And as a result, what appears as one load balancer is inherently resilient. It's inherently fault tolerant and scalable. It's also inherently secure, right? So we've offloaded the operational burdens of managing our load balancer to AWS, and they handle all of the scaling and everything necessary to ensure that that load balancer remains in service. It also supports health checks. So the load balancer will regularly send a check, and that's configurable by us. We can determine what that check looks like, but it will perform a check across each instance behind that load balancer. And if any instance fails that health check, then the load balancer simply says, all right, you are not capable of receiving requests, so I'm going to stop sending traffic to you. Load balancer also integrates with autoscaling and Route 53. In the case of autoscaling, which we will talk about here in just a little bit, as autoscaling creates new instances, it can automatically register those instances with the load balancer. And conversely, if the load balancer determines that an instance is unhealthy, it can then relay that unhealthy status to autoscaling so that autoscaling can terminate it and replace it. With Route 53, keep in mind that with load balancers, each load balancer that we create gets its own DNS endpoint. And so we want to send all of our users to that load balancer, but we don't want to give them this crazy long random looking URL. We want to give them a custom URL or a custom domain name. And so we can use Route 53 to map our domain name with the domain name of the load balancer. Elastic load balancers come in 3 types. We have the classic load balancer, the application load balancer, and the network load balancer. And we'll talk about each of those 3 in more detail as we move along. Taking a look at the classic load balancer, of course, we have users out there on the internet, and they want to get to our application. So with the classic load balancer, we create one. Again, we create a classic load balancer as a single resource. It appears to us as a single resource. We treat it and manage it as a single resource. Behind the scenes, all of the various nodes that comprise that are all, it's opaque. We don't really need to worry about that because Amazon is managing everything behind the scenes that makes that single resource work. So after we've created that load balancer, we then register instances behind it. We could register 1, we could register 2, or 200, right? Just about any number of instances we could put behind that load balancer. Then we define a listener for the load balancer, perhaps on port 80 and or 443, right? We can configure multiple listeners. And so the load balancer has to listen on something in order to receive those requests. In a classic case of web applications, then it's probably 80 and 443. And so now our load balancer is capable of receiving requests from our users. We then configure that load balancer to forward those requests to our backend instances on some port. In this example, I'm using port 8080 simply because I prefer to run my application on a non-privileged port. But that port is totally up to you. You could forward on port 3000, whatever you want. And so now that we have a load balancer, we have instances behind the load balancer, we have a listener configured, we have forwarding configured. Now our users can send their requests, and the load balancer will start to distribute that traffic among those backend instances. And then of course, if any of those instances fail their health checks, the load balancer simply stops sending requests to it until it becomes healthy again. That is the introduction to load balancing, and we will continue to talk about this as we move forward, and we will go into more detail about the application load balancers and network load balancers in the upcoming lessons. Now let's review application load balancers. With an application load balancer, very similar to a classic load balancer, we would create that application load balancer as a resource within our account. And then we would define listeners, right? Those listeners could listen on just about any port we wanted. Typically, we might listen on port 80 or 443. And from there, one of the things that sets the application load balancer apart is the ability to route traffic to different groups of instances. And so we would then create what we call target groups. And these target groups, again, allow us to route different things to different groups of instances. And so once we have our target groups, we then place instances or IP addresses in those targets, right? So we register targets within the target groups. And again, those targets could be EC2 instance IDs, or they could be IP addresses. And so once we have those targets in place, we then need to configure a way for the application load balancer to route traffic according to some kind of rule to one target group or another group. And so with the application load balancer, we have the ability to route based on host name or path. And so here we might create a rule that says all URIs that begin with /users/ get routed to a particular target group. We might also create a rule that says all requests for api.example.com, some host name, get routed to another group. And so the great benefit of the application load balancer is the ability to do layer 7 content-based routing based on the path, the URI, or the host name. And then, of course, each target could actually listen on a completely different port. And so this is very helpful especially if we're running containers, where our targets are actually containers rather than EC2 instances. And the ability to listen on different ports, the ability for each target to listen on a different port, is known as dynamic host map or dynamic port mapping. And so with the classic load balancer, we only get static or fixed port mapping. If we forward to a particular port, that's what we're going to use across all the instances. But with the application load balancer, and as we will see later on, with the network load balancer as well, those support dynamic port mapping. And dynamic port mapping can allow us to make more efficient use of the resources of that instance by allowing us to route traffic to more than one instance of the same application running on that one server, right? So again, the thing to take away here from the application load balancer is that it supports path-based routing and host name-based routing, layer 7 content-based routing. Now let's talk about network load balancers. With the network load balancer, we have the ability to balance traffic at a much lower level, at a more raw network level. And so very similar to the other load balancers, we would create a network load balancer. We would also create listeners, just like we do for the classic and application load balancers. And just like the application load balancer, we also create target groups. That's so that if we needed to, each listener could forward its traffic to a different group of EC2 instances. We may want port 80 to be forwarded to one group, and we may want port 443 or some other port to be forwarded to another group. And just like the application load balancer, we also then register targets with those target groups. And so the network load balancer, the thing to keep in mind about this particular load balancer, what sets it apart from the application load balancer, is that we are limited to layer 4. Now, on one hand, we're limited to that, but on the other hand, because it's not doing any kind of content filtering, the network load balancer can in many cases, be much faster and provide us with better latency than the application load balancer. And so we're forwarding on layer 4 only. So again, we may say we want port 80 to forward to one target group. We may say that we want port 443 to forward to another target group. Now you could have both listeners forward to the same target group if you wanted to do that. That's possible. I'm just showing you in this example that we can only create one rule per listener, and that rule will forward to a particular target group. Now, another thing to keep in mind about the network load balancer is that as these connections are coming in, from the internet to the load balancer, the network load balancer, the network load balancer essentially exposes, at this point, when this connection is made here, the network load balancer exposes static IP addresses, and it relies on static IP addresses, one static IP per availability zone. Now, you could use elastic IPs. Elastic IPs are essentially static IPs that you have the ability, that are yours until you decide to give them up, right? And so the network load balancer exposing those static IPs means that those connections that are made to those IPs are then forwarded across instances in those target groups. And one of the benefits of that is that if you are working for an enterprise and you have your enterprise security requires you to embed IP addresses within DNS or as A records or within on-premises firewall rules, then the network load balancer can help in that regard in allowing you to always count on a particular set of IP addresses being available to that domain name. As opposed to the application and classic load balancers, those IP addresses are always transient. You can't really count on those IP addresses being the same at any point in time, but you can with the network load balancer. And so another thing to keep in mind with the network load balancer is that it's TCP or TLS only. Those are the only two protocols. With the classic and the application load balancers, you are balancing either TCP or HTTPS because they are content layer aware, but the network load balancer is layer 4 only, so it's either TCP or TLS. And of course, you can offload SSL. You can offload SSL to any one of these load balancers that we've talked about so far, and we will talk more about SSL and how they relate to load balancers in an upcoming lesson. Now let's review SSL certificates. Within AWS, we have the ability to import or create certificates with the AWS Certificate Manager. So the Certificate Manager does allow us to create free SSL certificates, including wildcards. Now, the certificates that are created within the Certificate Manager will automatically renew. And because Starfield is the root authority, Amazon is an intermediate authority, then these certificates are trusted in the major browsers and clients. Now, we can import existing certificates. If you already have certificates that you've purchased and created through something like VeriSign or Cognito, then you can import those. But it's important to keep in mind that the Certificate Manager will not be able to renew those. You can renew them at VeriSign or Cognito, wherever they are, and then re-import them and replace those certificates in the Certificate Manager. Either way, wherever your certificates come from, the Certificate Manager can automatically deploy those certificates to your Elastic load balancers, to your CloudFront distributions, to API gateways. And so the great benefit of that is that we no longer have to really be worried about the underlying drudgery of having to renew and rekey and redeploy those certificates to our various servers and applications. So, I have done plenty of that in my career, and it's not hard rekeying a certificate that expires and downloading a new certificate and then ensuring that that certificate is installed and Apache or Nginx or something is configured. It's not hard, but it is tedious, and it's one of those things that's fun the first time, then just quickly becomes a chore, right? And so we can get away from all of that by using something like the Certificate Manager. And so here you can see that we have several different components. We have a CloudFront up here. We have our CloudFront edge location, and we have our load balancer, we have an EC2 instance, and of course we have the API gateway. And so the Certificate Manager, like we've said, can deploy our certificates directly to CloudFront edge locations. It can deploy certificates to our load balancer and to API gateway. Now, in many times you need true end-to-end encryption. If your users are going through CloudFront, through your load balancer to your back-end instance, then we need, in many cases, like for PCI compliance or other types of legal or regulatory compliance, we need end-to-end encryption. It's important to keep in mind that the Certificate Manager cannot deploy certificates to EC2.
It's also worth noting that, of course, our users and their clients will require, for that connection between the users and CloudFront, browsers would require a trusted certificate. Between CloudFront and our EC2 instance, CloudFront would require, or between CloudFront and API Gateway, that connection would also require a trusted certificate. Between the load balancer and EC2, by default, the load balancer does not require a trusted certificate. It is possible to script as these EC2 instances come to life. If you're using something like auto-scaling, as these instances come to life, you could script them to create their own self-signed certificate. That way, you don't have to worry about getting your trusted certificate stored somewhere and then deployed to it. They could just create their own self-signed certificate. It would technically be untrusted, but again, this connection between the load balancer and the EC2 instance by default does not care. It will accept that untrusted certificate, right? So keep that in mind, that if you have a need to create and deploy SSL certificates, and you want to ensure that those are always renewed and always deployed to various locations, then keep the Amazon Certificate Manager in mind.
Okay, so now let's review a demo of creating an elastic load balancer.
All right, so elastic load balancers are found underneath EC2. So let's go there. And so now we're here on the EC2 dashboard. You can see we do have one load balancer. That's something from a previous project. So we'll just create a new one here. Let's go down to load balancing. We'll go to load balancers. And we'll go ahead and say create load balancer. And you can see here that AWS is giving us those three options that we've talked about: the classic load balancer, the network, and the application load balancers. And so you can also kind of see that AWS is, I guess, subtly trying to discourage us from using classic load balancers. They're pretty old by now. Classic load balancers were released way back in early 2009. And so you can see better performance and more options, more useful features by looking to the network or the application load balancers. So remember that with an application load balancer, you can do layer 7 content routing, and really helpful for microservices. And then of course with the network load balancer, you could achieve that as well, but you would need something else to do the content filtering. If you were doing content-based routing based on path or host name, then the network load balancer won't do that, but you could forward all of that traffic to some other kind of router. So let's just go with the application load balancer. We'll say create, and we'll give this a name. I'll just call this one fundamentals. And we'll say that it is internet facing. You can see here that we have the choice of making it public, internet facing, or internal. Functionally, they're identical. The only difference is that with internet facing, it will get a public IP address. With internal, it will get a private IP address. So if you are creating a load balancer that is meant to sit between two private systems, then you would use an internal. In this particular case, we want to be able to visit this from the internet, so I'm going to choose internet facing. And then we also will need to specify a listener. So a listener just says that the load balancer itself is listening for traffic coming in from the internet, and we already have port 80 set up for us. We could add port 443 if we wanted to. That would require an SSL certificate, which I have, but we don't really need to worry about that right now. We can always come back and add listeners or change them later. Then we need to select our availability zones. You'll see here that I have I took the liberty of creating an extra subnet. And so we created, earlier in our VPC examples, we created a subnet for load balancing in AZA, and then I took the liberty of creating an extra one in AZB, right? And so you have to choose at least two. At least for an application load balancer, you have to choose at least two availability zones. And so you'll see here that it's giving us the option to choose US East 2A and 2B because that's where we created subnets. And you'll notice that US East 2C is not available as an option because we don't have a subnet there. In production, I would probably do that, but I'm just trying to keep it simple for now. And so again, we choose our VPC being web apps, our subnets being the load balancing subnets that we created specifically for housing load balancers. And of course, like all resources, we want to be consistent with our tags. And then we'll go to security settings. And it says you're not using a secure listener, and that's okay. For now, listening on port 80 is perfectly fine. In production, you may very well want to listen on port 443. So we'll go to security groups. And earlier in a previous demo, we created the load balancer security group as well as the web app security group, right? So we'll go ahead and choose the load balancer security group, and then we'll configure routing. And so routing says that we're going to essentially, create a target group and then, route traffic to that target group. And so here we're going to create a new target group, and I will call this one, let's just call this one Apache, because I have an instance running Apache that we will put in here. And so you might have another application that you might want to be put into a different target group. You can have a number of different applications, and each one of them may get their own target group. Right, and so the target type is going to be, you can see here that it can be an EC2 instance, it could be an IP address, or it could even be a Lambda function. So we have a lot of really powerful features here that are not present in the classic load balancer. And then here, the protocol the load balancer uses when routing traffic to this target group. So in that particular case, HTTP, and then the port the load balancer uses when routing traffic to targets. So that's the default, but we can always change that on a target-by-target basis. I have Apache currently configured to listen on port 8080, which I prefer because it's a non-privileged port. And then, of course, the health checks. The health check says that the load balancer will essentially make a request to this every so often, expecting to get a particular type of result. And if we take a look at the advanced settings, we can override all of this. We can say, well, the health check happens on a different port if we wanted to. And then we'll say, how many times in a row does it take for the load balancer to consider this to be healthy? I generally like to put that at 1, the unhealthy at, I think you have to have more than 1. Yeah, and it has to be at least 2. And then the unhealthy threshold, how many failures does it take to become unhealthy? And then the interval would be here every 30 seconds. So then that would mean it would take at least 60 seconds for it to become healthy. And then you can specify multiple success codes, right? And it's really anything generally in the 200 range, right? So I'm just going to leave this as a 200. And then we'll say, all right, now that we've created a target group, let's register targets. You have to have, the load balancer doesn't really serve any content. You have to have some kind of content provider behind that, whether it's an instance, an IP address of something off, on premises, or a Lambda function. And so in this case, we're going to use the Apache. You'll see here that I created this instance running Apache specifically for this. And so I will choose that instance to be the target here. We'll go ahead and review that, and we'll go ahead and create that. All right, so let's go ahead and close that. And then you'll see here is our application load balancer. It is currently in a provisioning state, so it does take a few minutes for it to become available or ready for use. And you can see back here that it's an application load balancer. And as soon as it's provisioned, we should be able to start using that. We can also see our listeners that we have. Here's port, we're listening on port 80. And then, of course, we could come back later and add port 443. So while that is provisioning, let's just go ahead and do that real quick. We can say add a listener, and we'll say HTTPS, and we'll say how will this listener route traffic, right? And of course, we could forward on to Apache, and or we could, if we were to get rid of that, we could say return a fixed response. Right? We could just say, 403 or whatever, when we can have that just not even forward to a backend instance, just return a fixed response directly from the load balancer if we wanted to, right? So let's go ahead and get rid of that and go to forward to Apache. So that 80 and 443 basically go to the same place. And then we do get to choose our security policies. I'm a fan of going with TLS, the latest security policy around TLS. So this is essentially saying that only TLS is used, not SSL. And TLS 1.2, not TLS 1 or 1.1, right? And then we need to, because we're listening on 443, we need to specify an SSL certificate. We can import one. Right? If we had one that was managed outside of AWS, I actually have one here from the AWS Certificate Manager. Right? So I'm going to go ahead and choose my wildcard, Cerulean.systems, which is a free certificate. And we'll talk more about the Certificate Manager later on. So I'll go ahead and save that. And it created that listener, so we could then go back to our load balancer. There we go. Now it's active. And you can see here that we have our two listeners, port 80 and 443. And let's see here. If we go over to the left here under target groups, here is our Apache target group. And then underneath that, we should see registered. No targets registered in this target group. Those should have been. Let's just make sure. Let's go ahead and edit that and make sure that we have those. So Apache should be there. Let's go add to registered. There we go. Let's save that. Not sure why the wizard didn't make that happen. And so now you can see here, here's our instance. Apache is running. I already have shelled in and made sure that Apache is running and listening on port 8080. And this is the initial setup. So target registration is in progress. It takes it a minute or so for the load balancer to essentially recognize that there's an instance there, and then it will start to perform those health checks. And we can always refresh that. And there you go. Now it's gone to a healthy status. So healthy means that it has successfully registered. The load balancer is aware of it, and it has made a health check that has returned a 200 response. And so now that we have our load balancer and we know that we have healthy targets, all right, so let's see if we go back to load balancers, and if we go to monitoring, there's no monitoring yet. There's no data yet. So eventually there will be. There we go. And what we can look for back here is the number of healthy hosts. So if we were to go to CloudWatch, we could see metrics on that as well. And we can see that for our application load balancer, and if we want to see the healthy host count, then this number should, here we go, here's our number one healthy host count. So that's a really good, very useful metric to create monitoring on. So if you start to see that there's too few healthy hosts in any given period of time, then that may indicate that there is something seriously wrong. All right, so let's go back And now that we have created our application load balancer, we have our listeners in place, we have our targets in place. Let's go back to the description, and here is the DNS name. We don't rely on the IP addresses. We could do a host lookup and pull the IP addresses, but they are ultimately transient. The IP addresses that we see there today may not be there tomorrow. We may get a different set of IP addresses tomorrow. That's with the application load balancer. With the network load balancer, those would be static rather than transient, all right? So let me open up a new browser tab. I'm going to paste in that URL, the DNS endpoint for the load balancer, and here is our Apache page. So this page was delivered to us from our EC2 instance running Apache through the application load balancer. And so by seeing this, we know that everything, that the chain of things is working. And we should be able to see, well, that actually wouldn't work. If we were to try to go to HTTPS, the listener would most likely work, but of course, we would get an error in the certificate because the certificate belongs to cerulean.systems, not to the DNS name of the load balancer. So in order to make that work, I would have to go to Route 53 and create a DNS entry there. But I could, if I wanted to force it, I should be able to add an exception, confirm the exception, and now I can prove that my site is listening on port 443. So again, there in just a few minutes, we created an application load balancer. We added listeners for port 80 and 443, specifying our own custom SSL certificate, and we added targets to that target group, and then of course we verified that they passed their health check, and we took a quick look at monitoring for the number of healthy hosts. There it is right here as well, healthy hosts 1. All right, so that's how we can create elastic load balancers.
Now let's review an introduction to autoscaling. Now, autoscaling within EC2 does two very important things for our infrastructure. One is that it replaces unhealthy instances. EC2 instances could be marked as unhealthy by the hypervisor. There could be an issue within the hypervisor. There could be an issue with the underlying host. And so if those instances are marked as unhealthy, then autoscaling will simply terminate them and replace them with a new instance. Instances could also be marked as unhealthy by the load balancer. If you are using elastic load balancing in conjunction with autoscaling, then as the load balancer marks an instance unhealthy, autoscaling then does the same thing. It replaces it. You could also programmatically mark an instance as being unhealthy, right? You could have some other script that is looking at your fleet of EC2 instances and making its own determination as to whether or not that instance is healthy or unhealthy. But either way, somehow, some way, something would need to inform autoscaling that the instance is now considered to be unhealthy. And when that happens, it will terminate it and then replace it with a new one. And so you could use that to essentially do a couple of things. One, you could maintain what we call a fixed size fleet. There are plenty of instances where you may want to maintain one server. If it fails, replace it. Or maybe you want to maintain 2. If one fails, replace it. So another key thing with autoscaling is that it allows us to match our supply of resources with the current demand. And so as our demand grows, let's say that we're running an e-commerce application, some type of a web application. And now today we have more users, more visitors than we had yesterday. So as that demand rises, we may need to increase the number of EC2 instances behind our load balancer, right? If we're doing some type of back-end processing, maybe we have a fleet of EC2 instances that are doing, video transcoding or batch processing. When there's more work to be done, whatever that work is, we can scale out. And when there's less work to be done, we can scale in, right? So as the demand rises and falls, so too does our fleet scale out and scale back in, right? So we scale out to meet that demand, we scale in to save money when that demand is no longer there. Now, autoscaling does work with Amazon CloudWatch, and we will talk much more about CloudWatch in detail in a later lesson, but the idea here is that CloudWatch is monitoring our infrastructure, so we can work with that monitoring to scale based on different metrics. Autoscaling also supports a number of different events, or it triggers or generates events. So as there's through these different life cycle events, like as autoscaling launches a new instance, as that instance is put into service, as it terminates instances, those type of events we can leverage to further program or script our environment to respond to those things, or to automatically configure our environment now that we have a new instance in place, or now that we have terminated an instance. And those events could go out through the simple notification service. Those could go directly to Lambda, so that perhaps we have a Lambda function that is responding to the fact that now we have a new instance, or an instance was terminated. So there are two things that are required for autoscaling to work, and those are the launch configuration and the autoscaling group itself. The launch configuration determines what gets launched. As you can see here, the type of instance, be it a Teeth2 or an M4, an M5, a C5 large, whatever the case may be. Any additional volumes, perhaps you want additional EBS volumes attached to that instance. What machine image are we using? Is it Amazon Linux? Is it a Windows or Red Hat or CentOS? What user data, meaning what kind of script do we need to run on that machine? Now, it is important to remember that the launch configuration is immutable. You cannot edit one, but you can create new launch configurations, and then you can swap those out. The autoscaling group itself determines where that instance gets launched, right? So we would configure the autoscaling group to leverage subnets, and by choosing subnets, remember that subnets are one-to-one with availability zones. So by choosing subnets, we also choose AZs. We could also determine which load balancers to use, and I say that plural because it's possible for an autoscaling group to register its machines behind multiple load balancers. We can also determine the health check type. Where does it look to be informed of its whether or not an instance is healthy or unhealthy? The default is the hypervisor, or the EC2 status checks, which come from the hypervisor. You could also set that to pull from the load balancer. Now, whatever tags we put on the autoscaling group can then be propagated to the EC2 instances that are launched, right? So these two things, the launch configuration and the autoscaling group, are both required for autoscaling to happen. And if that's all you have, those two things, then you are essentially maintaining a fixed fleet. If we need to scale based on conditions, scaling out to meet a demand, scaling in to save money, then we could use either a scheduled action or a scaling policy. Scheduled actions are great for when you are aware of the need to scale ahead of time. Now, you could do this as a one-time event. Maybe, tomorrow at noon, you'll be featured on some television show, and you know that as a result, you expect to have, a lot more traffic tomorrow at that time, right? So you could schedule a one-time event to scale out and get ahead of that curve. Like, why wait for the traffic to get here before you scale? If you know it's going to come, go ahead and scale out before that. It's also useful for regular known events or predictable loads. There are plenty of applications out there where if you look at your traffic patterns, you can see a very predictable rise and fall, like an even sine wave. And so you can predict in many cases that every morning at 9 a.m. you start to see it rise, and by noon or 1 or 2 p.m. maybe you start to see the peak, and then after that it starts to fall off. Whatever those times are for your application, the scheduled action is useful in that it allows you to get ahead of that rise in traffic. With the scaling policy, this allows us to scale based on the actual load, and this is really useful for unpredictable loads. So maybe you are featured on some viral trend within Reddit or Facebook that you weren't aware of. You weren't prepared for that, or you couldn't predict that. But we can be prepared for that by leveraging a scaling policy so that as load comes in, or as that new traffic comes in, we can scale immediately. And so the scaling policy needs to be triggered, and we can do that either with CloudWatch alarms, which we'll talk more about coming up, or we could trigger those manually or even programmatically. We don't necessarily have to use CloudWatch alarms. We could have our own scripts that are looking for signals to show us that there is a need to scale. And so in the least, with autoscaling, we can create self-healing systems, right? In this example, as it stands right now, this diagram shows that we're running 2 EC2 instances behind a load balancer, but it does not show that there's anything that can automatically replace those instances. So if we wrap those in an autoscaling group, then now we can trust that if an instance were to fail, right? If that instance were to become unhealthy for whatever reason, then we know that autoscaling will terminate that instance. And now, of course, because we have another instance behind the load balancer, we have fault tolerance. And we also know that because those instances are managed by autoscaling, that autoscaling will replace that failed instance, right? So that in the least is a self-healing system. And all of that can happen without manual intervention. That's the goal that we try to get to, is creating a system that can be fault tolerant, that can heal itself without human intervention. And we will take a closer look as the course progresses. We will see more examples and more details about autoscaling as we continue. Now let's review demand-based scaling. Now, with demand-based scaling, the idea here is that we want to somehow measure that we are getting an increase in demand, whatever that demand is. For a web application, it's probably an increase in traffic. For other systems like back-end processing, you could be doing video transcoding, batch processing of some kind, other types of scientific research or simulations. And the idea here is that as there is more work to do, then we may need more servers to accomplish that work in a period of time. And so, again, we would wrap these instances in an autoscaling group. And now you'll notice here that we are using Amazon CloudWatch. And we'll talk more about CloudWatch in detail later on, but for now, suffice it to say that CloudWatch is essentially collecting metrics from each of these EC2 instances. And so it's collecting things like CPU usage and disk I/O and network I/O and so on. It's also collecting metrics from the actual load balancer. So the load balancer itself is sending metrics to CloudWatch according to the number of requests per minute, the number of HTTP 500s and 400s and so on. It's also sending CloudWatch a measure of latency between the load balancer and the EC2 instances. Each of these instances, like I mentioned, those are also sending CloudWatch a number of metrics, including CPU and disk usage and so on. And then the auto-scaling group, auto-scaling is also sending metrics, right? So auto-scaling is sending metrics in aggregate. These EC2 instances are sending metrics individually, but auto-scaling is sending metrics about those EC2 instances in aggregate. We get other things like average network I/O, average disk usage, and so on. And so now that we're collecting all of these metrics, we can then use those to create alarms. And these alarms could say, well, if a number is too high or too low, then we want to trigger an alarm and then use that alarm to trigger something else, like auto-scaling. So we may create an alarm, for example, to say if CPU is greater than 80% for some period of time. Then in that regard, we would want to, we might say that if CPU is too high for that long, then that would indicate a need to scale. It would indicate that there's more and more work to do, and we need more resources to accomplish that work, right? Now, it all depends on the application. Some applications may be CPU bound, some may be memory or network I/O bound, some may be perfectly fine in all of that, but still latency is rising, right? So it's all according to your particular application on the instances that you're running. I'm just using CPU as an example, right? And so in this example, if CPU is too high, then we can use that alarm to then essentially trigger auto-scaling. And auto-scaling will then add more instances to that fleet, register them behind the load balancer if you're using one, and hopefully the addition of that new instance would bring the aggregate CPU usage down to below 80%. If it doesn't, and it keeps going and the alarm triggers again, then auto-scaling would scale again, and we could keep going up to our maximum. We can set a maximum on the auto-scaling group to say, hey, let's continue to scale, but I'm only willing to pay for a particular amount. My budget only goes so high. And so you'll also notice that auto-scaling will always attempt to maintain a balance here. You'll see that across these availability zones, we have 3 instances across each of the 2 availability zones. And so as our demand goes down, we may have another alarm that says, when CPU is below 40% or when latency is too low or whatever the measure is, we could then again trigger auto-scaling to start removing instances. And again, it will always seek to maintain a balance across those availability zones. So if demand continues to stay low, then we could continue to remove instances down to our minimum. We may configure auto-scaling group to say that we always want a minimum of maybe 2 machines. In this example, we're using 2, but for your application, it could be 4, it could be 20. So that's demand-based scaling. Scaling out to meet demand, scaling in to save money. Now let's take a look at a demo of creating an auto-scaling group.
Now, auto-scaling can be found under EC2. So let's go to EC2, and underneath EC2, we can scroll down over here on the left to auto-scaling, and we can take a look at our auto-scaling groups. We don't currently have any. And so there are a couple of ways of going about creating an auto-scaling group. We can click here to go through the wizard. We could also kind of go around it from a different angle by going to our instances. If we already have an instance running, like we do, we have several, and in an earlier demo, we attached this Apache instance to our load balancer. And so if we wanted to auto-scale that application, then we could go to Actions, Instance Settings, Attached to Auto-Scaling Group, and then use this to create an auto-scaling group. That's probably like the fastest way if you already have an instance running. Otherwise, this would create it pretty quickly, but by doing that here in the demo, we would kind of end up missing some important points. So let's go ahead and create one from scratch. So again, keep in mind that you can create an autoscaling group from an existing instance, or you could go back here to autoscaling and create one from the wizard. All right, so let's go ahead and do that. Now, this wizard will kind of move us through the process of creating an autoscaling group that actually starts with a launch configuration. Before we can create the actual scaling group, we first have to have a launch configuration. So that's actually the first step here, is to determine, do you want to use an existing launch configuration, or do you want to create a new one? Now, I have a couple that I've created for projects in the past, but I'm going to create a new one. So we'll say launch configuration, create a new launch configuration, and then very much like launching an EC2 instance, we need to select all of the same things. And because the launch configuration is essentially a blueprint for the instance that gets launched. So, it makes sense that the launch configuration and launching an EC2 instance, that process looks very, very similar, right? So just like we did for the EC2 instance, we would choose our AMI, and I might, just go ahead and go with Amazon Linux 2, and you would probably use a private AMI. Normally, when you were creating autoscaling groups, it's most likely that we're using a machine image that we created, a private machine image that we know has a certain pieces of software installed and a certain configuration in place. And then if we need anything to change, if we need something updated or a process started, then we can do that with automation after the instance has launched. And so we also choose the type of instance, a T2 micro, a C5 large. For this particular demo, I'll stick with the T2 micro. And now we'll name the launch configuration. I will call this one fundamentals. And you probably want to name it something related to that application. And then, of course, we can look at kernel IDs, RAM disk IDs. We can also paste in user data, which would be user data would be, in the case of Linux, we could make it a bash script, right? And so anything that we put here would be executed as a bash script, at the time that machine was launched. And so I could use user data as a bash script to further customize that machine once it's up and running. And so if, like I said, if we need to update code, then I could do that here with bash. In the case of Windows, then I could write a PowerShell script. And then, of course, we need to choose what kind of IP address. Just like launching an EC2 instance, we need to determine, does it get a public IP? And here we could say only assign it, if it's launched into the default VPC, or yes, assign a public IP. Generally, my common practice is that if I'm autoscaling something, it's probably an application server of some kind, and I generally want those to be private, so I almost always say do not assign a public IP address. And then, of course, autoscaling can include extra volumes if we wanted EBS volumes to be attached. We also need to choose our security group. So we'll go ahead and select an existing one. We will choose the web app security group that we created earlier, and then we'll go to review. And so here, this is our blueprint for the EC2 instances that will be launched. This is exactly what they will look like. They will all use this machine image. They will all be a T2 micro, and they will all not receive a public IP address, and they will all have the same security group applied. All right, so then we'll say create launch configuration, and we'll say, yes, I do indeed have that key pair available. I can access it, create that launch configuration. Now that the launch configuration is created, now we can create an autoscaling group. And so I'll call this group fundamentals just for the sake of the demo. And we can say, well, how many instances do we want to start with? Should we start with 1, 2, 3? Let's go ahead and start with 2. And then where are we going to put these? So where the launch configuration specifies what is being launched, the autoscaling group specifies where it gets launched. And so we'll tell the autoscaling group that we want to use the web apps VPC, and we want to launch those into our applications subnet. And then, of course, we can have some advanced details here as well. We could, register this with load balancers, right? So if we were to do this, we could choose our Apache target group so that as the load balancer creates new instances, it automatically registers them with our Apache target group. And of course, we would have to have Apache running on that system. And then, of course, we could choose the health check type. If we are running in combination with a load balancer, then we would probably want to use health checks from the load balancer. And then if we could say, well, let's give it a grace period, give that machine some time to, become alive and actually get do its bootstrapping, start processes, and be able to handle a health check. And then, of course, let's go to scaling policies. And now we could say, well, you know what? I want to keep it at a particular size. Plenty of applications, plenty of scenarios where you're not looking to scale out and in. You're looking to maintain a certain number of instances, be it 1, 2, 3, whatever. If one fails, replace it and always maintain that number. And like I said, plenty of scenarios where that's exactly what you want to do. And in other cases, you want to scale between, maybe 2 and 12 or maybe 2 and 20, whatever your particular scenario calls for. And you might scale based on CPU, based on load balancer request count, network, so on and so forth, right? So you could say, well, I want to scale, when average CPU is 80%. So for now, we'll just go ahead and say keep it at its initial size. We can always come back and create policies, scaling policies later, and update the autoscaling group to leverage scaling policies rather than just maintaining an initial size. And then, of course, we can configure notifications. So as the autoscaling group goes through its life cycles, as instances are launched, as they are put into service, as they are terminated, all of those lifecycle events, we can receive notifications on those if we wanted to. Now, as far as tags go, again, being consistent here, and we could also add, project fundamentals. Then by selecting tag new instances, these tags that we're entering here are on the autoscaling group itself. By choosing tag new instances, the autoscaling group will then propagate these tags to the instances. So that's generally what we want, so that as those new instances come up, because we didn't create them ourselves, because something else created them for us, we would want those keys or those tags there to, again, help us organize our environment. All right, so let's go ahead and review that. So essentially what we're saying is that we're creating a group with that the current size of that will be 2 instances. And we could scale that simply by changing this number. And ultimately, that's all that scaling policies do. Scaling policies simply are a way of calculating what that new number should be. But the way that autoscaling scales is by changing the group size, the current desired capacity. How many machines do we want right now? And of course, they will all be launched into this particular subnet. We're currently we're going to skip load balancers for now. And we have our tags that will be propagated. Let's go ahead and create that autoscaling group. And then if we go ahead and close this, you'll see here that we have an autoscaling group, and it says that we want 2. We have a desired capacity of 2, but there are currently 0, but this little I here that says instances may be in the process of launching. All right. So let's go ahead and refresh that. Let me refresh my page and see if I can get more details around that autoscaling group. There we go. Let me pull this up. All right. So then if we go to, again, we can see similar information down here, desired capacity 2. And then if we look at our activity history, it will show successful. Launching a new EC2 instance was successful. Launching that second one was successful. And then if we look at our instances, we can see a list. These are the 2 instances that are currently in service. And they are healthy. As far as autoscaling is concerned, those instances are considered to be healthy. And we can force autoscaling to replace an instance by simply telling autoscaling, no, it's not healthy. Right? We can set the status of an instance to be unhealthy, and if autoscaling, once autoscaling recognizes an instance as being unhealthy, it will then terminate it and launch a new one. We could also detach an instance from an autoscaling group. Now, there have been rare cases when I've needed to do that. If I needed to make a change in something that required me to essentially delete and recreate the autoscaling group, then I may want to keep the existing instances in place while I go and recreate or reconfigure the autoscaling group, right? So it is possible to pull those instances out, and then once you have a new autoscaling group, you can put them back in. We can also see monitoring. This is monitoring essentially in aggregate. If we enabled monitoring for this autoscaling group, then let's go to EC2, and then we could see monitoring. We don't really have a whole lot of data because no time really has gone by in this demo in order for us to see anything. But we could see monitoring in aggregate across that autoscaling group. And
now let's review an introduction to Amazon CloudFront. With Amazon CloudFront, we have the ability to improve our end user's experience by caching content at the edge location. And by edge location, remember we talked about those early on in the course, that edge locations are more often than not, these are actually outside of a region. These are a place where we can cache content, or a place where the edge locations power both CloudFront and Route 53. Right, so that our end users can make requests directly to the edge location in order to download content faster, or to get their DNS queries answered faster. And so with CloudFront, we can use this to cache both static and dynamic content. We may have some content like CSS, JavaScript, PDFs that are pretty well static. They don't necessarily change very often, images and video and so on. We may have other content like HTML pages that are specific to a particular user, and those are very dynamic. And maybe we want certain things to be cached for certain periods of time, and maybe we want other things to be cached for lesser periods of time or not cached at all. And so we do get the ability to customize and control that cache behavior, right? And so we could set a default for certain things, that certain types of content defaults to being cached for a week or a month, and other types of content may default to a lower period. But we could always, on a request by request basis, change that and say that certain pieces of content are cached longer, or maybe not at all. Now, very similar to load balancers, where each load balancer gets its own domain name. When we create CloudFront distributions, those also get their own DNS endpoint. And so we can either use a CNAME, or within Route 53, we can use an alias record to map our custom domain name to the CloudFront distribution DNS endpoint. We can also configure CloudFront to use our own custom SSL certificates for that domain name, so that when our users connect to that CloudFront edge location, they can connect using SSL with our certificate. CloudFront also supports not only downloading static content, but it also supports streaming content, such as streaming video, streaming audio, and in that regard, we could use either RTMP or HLS streaming. And so again, the great benefit of CloudFront is that we can improve the end user experience by caching content closer to them at the edge location. And so again, within the Amazon CloudFront service, we would create what we call, in this example, we would create a download distribution. And you can see here that we want certain content to come from the load balancer, right? In this example, we want dynamic content to be pulled from the load balancer, and we want static content like our web assets, our CSS, JavaScript, images, PDF documents. We want those to come from S3 so that our back-end instances don't have to serve them, right? And so those, we would configure the distribution to recognize those as what we call origins, right? So in this case, the download distribution says, well, the edge location doesn't have content of its own. It has to get content from somewhere to begin with, and that's called the origin. And we can configure multiple origins, right? And then the question becomes, well, if we have multiple origins and multiple types of data in these different places, how does the edge location know to pull one set of data from one place and another set of data from another place? We can do that with behaviors. And behaviors are essentially like some type of a syntax pattern that you can write to inform CloudFront of a particular pattern. So in this particular case, we're using the asterisk to say that all JPEGs, all CSS files, all JavaScript files are pulled from S3. And these are listed in order. And so the first one in the list would be, this particular behavior right here, JPEG, CSS, and JavaScript. The next behavior in the list would simply be a fallback wildcard for everything, saying that essentially everything else is served from the load balancer. And so now the edge location knows. So now, when our users make a request for a particular piece of content, they make that request directly to the edge location. And the edge location says, do I already have that content? Do I have that object or that URL cached already? So if the answer is no, then the edge location will say, all right, I need to get it from the origin. So in the case of where the user is asking for a JPEG, the edge location will then go to the origin, retrieve that piece of content, and then cache it according to the cache behavior that is defined either in the default or that particular image, whichever one takes priority. The one on the image would take priority. And then the edge location will then hold on to that piece of content so that the next user who makes a request for the same thing doesn't have to wait for the edge location to retrieve it from the origin. It's already there. It's already cached, right? So the first person essentially suffers the latency penalty, but everyone after them has the benefit of downloading that piece of content much, much faster. Now, the thing to keep in mind here about CloudFront is that we don't have this edge location right here. There are, again, more than 100 edge locations all over the globe, and we as users of AWS, we don't have any direct access to the edge location itself. We cannot configure the edge locations directly. We configure the download distribution or the streaming distribution, right? So we configure the distribution to behave in a particular way, that distribution, and then the CloudFront service behind the scenes then configures the edge location for us. And so again, we can use all of that to improve our user's experience. So let's say that we have you'll see here, a load balanced application running on the East Coast, let's say in US East 1 in Northern Virginia. And again, within that particular region, we are running a load balancer for dynamic content. We have EC2 instances behind it. And of course, we have our static content within an S3 bucket. And let's say that we have users somewhere over here in Europe, throughout all of Europe. Now, instead of without CloudFormation, they would have to traverse the Atlantic Ocean for every single request. Every single user would have to traverse the Atlantic for every request, right? And that would incur latency. Now, instead of doing that, instead of making them do that, we could, by leveraging CloudFront and leveraging these edge locations, there is likely edge locations throughout Europe. So in this example, the first user to request a piece of content, they make a connection to the edge location, they ask for content, the edge location downloads it from our region, so that first user is incurring the extra latency, but everyone else then simply downloads it directly from the edge location. So again, keep in mind that CloudFront is meant for caching content, either static or dynamic content, whether it be downloadable like an image or streaming like a video, that we can improve our end user's experience for accessing that kind of data by leveraging edge locations all over the globe. Now let's review an introduction to Amazon API Gateway. With Amazon API Gateway, we get a fully managed service for creating, publishing, deploying, and running APIs at any scale. The service itself will automatically scale to support the level of requests that are passing through. And so an API Gateway essentially acts as a front door to back-end services. We can centrally manage a number of things at the gateway rather than duplicating those efforts across various back-end services. And so API Gateway does support REST and WebSocket APIs. All we have to do is within the API Gateway, we define our resources and we define methods for those resources. And then we define what backend service will handle that method. Now, our backend applications can run just about anywhere, including but not limited to EC2, ECS, Lambda, and so on. So we have a lot of flexibility, a lot of choices to where we actually put our backend services. And in fact, it could be that we have different services running in different places for different reasons. And so API Gateway also gives us a number of tools to centrally manage things like traffic management, rate limiting, for example. We also get tools to perform authentication and authorization. We could leverage something like Amazon Cognito if we wanted our users to log in with Facebook, log in with Twitter and Google and so on. We could also write our own custom authentication and authorization methods in Lambda. We also have built-in caching. So we don't necessarily need to set up a separate cache somewhere else. We could leverage built-in caching through the API Gateway service itself. And then we also have the ability to use API Gateway as a proxy to other AWS services such as S3 or Kinesis and more. So let's take a look at a diagram here. You'll see that all we have to do is, again, through the API Gateway service, we create a gateway. And then once we have that gateway, we simply define, within that, we simply define our resources and the various methods underneath those resources, right? And so once we define those, we then define the various backend services that will handle those methods. And again, those could be handled by applications running directly on EC2, and those would be behind a load balancer. We could have applications running in Lambda or functions within Lambda. So a pattern here could be that you have particular resources and methods that are then passed on to Lambda. Now, remember that Lambda gives us the ability to create functions, and we call them functions for a reason, because each function will do one thing, one specific kind of work. Now, technically, it would be possible for you to create one function that handles all of the methods for a particular resource.
but in my experience, doing that kind of thing actually becomes hard to maintain. What's more likely that you would do is create a Lambda function per method, right? So you imagine all of the RESTful API methods that would exist on any particular resource, you would create a Lambda function for each one of those methods. And then we could also use containers running within Amazon ECS or EKS. And so again, those containers would also, in that case, be behind some type of elastic load balancer. And so all of this here would be our applications, right? We would be running our applications, our custom code on one of these services. And like I mentioned earlier, we can also use API Gateway to act as a proxy for other services like S3. We could use API Gateway to act as a proxy for Kinesis and more. We're not limited to those two. There are other services that we could wire in. And so the benefit of using an API Gateway is that we can centralize common things. Again, we may have each one of these services may require some type of authentication and authorization, and we can centralize that here at the API Gateway. We might want to perform request tracing and access request logging. We may want to perform some type of caching. And so again, a number of things that we can centralize at the gateway itself. So if you are planning to build a RESTful API, if you are looking to migrate APIs into AWS, or what I've seen is organizations who are building new microservices while still relying on legacy monoliths. And so it could be that you put both of those together behind one API gateway, and then as time goes on, you swap out the monolith for microservices. And then your end users are never the wiser because they always hit the same endpoint, right? So if you're thinking about those kinds of things, I would highly recommend that you take a look at Amazon API Gateway.
So we have our region, and within a particular region, in this example, we're going to leverage 2 availability zones for the sake of fault tolerance and high availability. You might use more if the region provides those. And so the first thing that we'll want to do is create a VPC, a logically isolated network that allows us to make use of those availability zones. And then within that VPC, we can create subnets. And so if we're following a classic 3-tier architecture, then we have probably a load balancing tier, application tier, and a database tier. And so we need to create a footprint for our load balancer. So we would create two public subnets, one per AZ for the sake of high availability, and then those would be routed to the internet through an internet gateway. We would then create private subnets specifically for our application tier, and those we would call them private because they would not route to the internet. That gives us these subnets again. If you remember what we talked about earlier on, these subnets are giving us isolation between tiers. And then, of course, we might create subnets for our databases, private subnets as well. And then for our application, we would create an autoscaling group. And by creating the autoscaling group, that would then in turn create a number of instances, whatever number we said we wanted to be our current capacity. So if we specified 4, then autoscaling would create 4 instances and always seek to maintain a balance between the availability zones. And then, of course, we would probably need some kind of a database. And so by using the relational database service, we could launch not only a single instance, but 2 live instances by using a multi-AZ deployment. Now remember that in a multi-AZ deployment, the relational database service will create both a primary master and a secondary standby and manage synchronous replication between the two. And then, of course, our application servers can connect to the primary. And then we need to get traffic to be distributed among those backend instances. So we could create a load balancer, and then by using a load balancer in conjunction with autoscaling, the autoscaling group will then automatically register these instances with this load balancer. So now traffic coming in through the internet gateway connects to the load balancer, which then distributes that traffic among our backend instances. And of course, with autoscaling in place, if any one of these instances were to fail, it would automatically replace it. If an entire availability zone were to go offline, then autoscaling can shift these two instances to the other AZ, ensuring that we always have, in this example, 4, but we could be running 8 or 80 or 200. And then we might not want our application servers to distribute both dynamic and static content. One way of reducing the load on these is to offload the serving of static content to S3. And then, of course, through CloudFront, we could enable our users, we could improve the performance for our end users by allowing them to connect to an edge location. That is a server that is closer to them than perhaps this bucket or this load balancer, right? So by connecting to an edge location, the edge location can then retrieve dynamic content from our load balancer and retrieve static content from our S3 bucket and cache much of that content so that subsequent requests benefit from that lower latency. And then we would also want to monitor our infrastructure, right? We want to be aware of performance issues, and using Amazon CloudWatch, we can do that, and we can use alarms, CloudWatch alarms, to trigger autoscaling. So whatever the bottleneck is, whether it's CPU usage or latency or the number of threads, the number of processes, whatever that is, if that number is too high, then perhaps we scale out. If that number is too low, we scale in. So by using autoscaling in conjunction with CloudWatch monitoring and alarms, we can always match the current supply of resources with the current demand of traffic coming through. Now, if our primary database were to fail by using the relational database service, of course, if this fails, we would be without a connection to a database. We don't want that to go on for very long at all. And so by using the relational database service, when this failure is detected, RDS will automatically promote the secondary to the new primary master. And then by leveraging DNS, it can update the IP address, and then our application instances, without changing code, without updating configuration, we just simply continued to try to connect to the same DNS endpoint, and once that IP address changes over, as long as our application honors the TTL or the expiration of that DNS record and refreshes, then we can just connect to the new primary without restarting or even making any code changes. Now, we'll also probably need SSL certificates, and remember that we can get those by using the AWS Certificate Manager. The Certificate Manager allows us to we can create free SSL certificates, we can also import existing certificates. Either way, whether you create them or import them, the Certificate Manager can automatically deploy those to CloudFront edge locations and Elastic load balancers. And so the benefit there, the reason I highlight this, within the context of highly available web applications, is that I've seen this happen. I've seen SSL certificates expire. And if the SSL certificates expire, browsers will oftentimes give a warning and initially prevent you from getting to the site, and then in order to get there, you would have to add, some kind of an exception to your browser. A lot of people don't know how to do that. They just get scared away. And then there are other clients, like mobile applications, that just refuse to connect and don't give you an option to force that connection, right? So if an SSL certificate expires, then at least as far as your users are concerned, your site is unavailable, right? They can't get to what they're looking for. And so the benefit of the Certificate Manager, as it relates to high availability, is that at least for certificates that it creates, it can automatically renew them and automatically redeploy them to, again, edge locations or load balancers. So by using the Certificate Manager to create and deploy SSL certificates, we don't have to worry about being in that situation of, having to scramble and, hurry to, rekey and re-sign and redeploy SSL certificates to a number of different places. I've been there, and it's not really a pleasant experience, especially when you have users that are upset that they can't get what they're looking for. So as you can see, we have a lot of tools available. Again, VPC giving us the network footprint we need to use multiple availability zones. Autoscaling giving us the ability to self-heal and scale, both out and in. The relational database service giving us the ability to fail over automatically to a live standby. S3 giving us the ability to offload static content, thus reducing the load on our backend servers. CloudFront giving us the ability to improve the performance for our end users by caching content at edge locations. And then if we wanted to take this a step further, if we wanted to be resilient not only to the loss of a data center, but if we wanted to be resilient to the loss of a region, then we could duplicate this whole thing in a second region and use DNS to fail over from one load balancer to another. Right? So again, we have very easy tools to make our web applications highly available.
Big data and real-time analytics are hot topics these days, but not necessarily a simple or easy thing to jump into. In this lesson, we will explore the exciting technologies AWS has to offer, such as real-time stream processing with Amazon Kinesis, big data processing with Amazon EMR and Athena. We'll review tools that make it easy to move and transform data between various sources and destinations. We'll also review a use case highlighting business intelligence by making use of a number of various services.
Now let's review streaming data with Amazon Kinesis. Now, before we get into the details of Kinesis itself, let's first take a look at a use case to understand the context in which we will be using real-time streaming. And so here in this example, we're going to use a large pizza chain as an example for a business use case. And so what we have today is, let's say that our particular pizza chain has 11,000 locations worldwide, tens of thousands of locations, and nearly 40,000 delivery drivers, right? So we have a lot of locations, a lot of drivers, meaning that there's a lot of data being produced. There's a lot going on, many events happening at any one time. And we also have millions of customers who are placing orders constantly all over the globe. Orders are coming in, and those we're serving more than 1.5 million pizzas per day, and we want and of course our users are wanting some type of real-time updating on their pizza, but they can't get it right now because we're using an antiquated ordering system. They basically have to call in their order to a local store, and then give them their credit card over the phone, and then wait for their order to be delivered. The customers have essentially no way of knowing what is going on with their order until it shows up, or unless they call back to the store. And then, of course, management is relying on reports, daily reports, weekly and monthly reports. They don't have any kind of real-time insight into what's going on with different locations or different regions or different franchisees. They have to wait on reports to be generated. And like I mentioned, customers have no insight. They place an order, they wait for their order. And if it's taking longer than they expect, they have to make a phone call, right? So this is the kind of thing that could really be brought into the 21st century, brought into real time, rather than relying on phone calls or old reports. And so what we want, out of this system, is that we expect to add more locations. So we're going to have, over the next year or two, we will be adding more locations
more delivery drivers. And so that means that we're going to have even more data, even more events. And we want to serve, over the next year or two, we want to increase the number of pizzas to more than 2 million per day, right? So again, we expect that not only do we want to bring this into the 21st century, we also want to increase sales significantly and increase locations, right? So we have more events and more locations, more employees that will be adding more demand to the system. And so we also want to enable mobile ordering. We want our customers to be able to order directly from their phone, and we want real-time reporting per location for sales and trends of that location and per pizza. We want our users to have to be able to look at that app on their phone and see exactly what's going on with their pizza. They don't have to make a phone call. They shouldn't have to just sit there and wait, blindly wait, wondering what's going on. They should be able to look at their app and see, my pizza is exactly here. My pizza is, they're preparing the dough. They're putting on toppings. It's going into the oven. It's coming out of the oven. It's going out for delivery, right? And then, of course, the user should be able to get push notifications as their order moves through the different stages in the process between dough and toppings and oven and out for delivery. Hey, your order is actually here. Your driver's at your door, right? Those kinds of events should deliver push notifications to our users. And so, again, in order to do that, we have to collect a lot of data from a lot of different places. And so here, you can see that we have in our various locations, right, our various offices or the different franchise locations throughout the globe, the actual stores, have workstations along the way, at different places, different key areas for, dough preparation, the oven, going out for delivery or whatever. And those events are being sent to our load-balanced, auto-scaled API. We have delivery drivers out there who are using their different phones, different tablets, and they are sending their events, updating their orders, right? And we have our customers that are placing orders. And so all of this data is coming in from various devices, various locations constantly. And so we need a way of collecting that data. Now, of course, we have an API, but an API should be just an API, right? One of the issues with just having this that we have that we're seeing right here in this example is that if we want to be able to perform analysis on, let's say, a particular pizza location in some type of maybe a sliding window as an example, how many orders have come in for that location? Well, if an order comes in, one order may come in for a location and be sent to one server, and then for that same location, the next order may come into the load balancer and then be distributed to another server, right? And so these orders are being distributed across these different servers, which means that if we try to do processing, any kind of analytical processing here, we are only processing a subset of the data, right? And by doing processing here alongside the API, we're kind of merging two completely different systems. We have an API, and then we have analytical processing. They don't need to run on the same machine in the same code base. They should be completely different systems. And by having them completely different systems, that would allow us to tune our code, write them in languages that are appropriate, and scale them independently and tune them independently, right? Our analytical processing and our API may need different, amounts of CPU, memory, and so on. And so we have all this data coming in that we want to try to analyze in real time. And so we need a way of ingesting that data very quickly and storing that data for some period of time and making that data available to analytical applications. And so that's what Kinesis does. Here in this diagram, you can see, again, we have pizza locations sending
their events, right? Pizzas are going into the oven, pizzas are out for delivery, so on and so forth. We have delivery drivers saying, hey, I'm leaving the location, drivers saying, hey, I'm at your door, and so on. All of these events coming in. We have customers that are placing orders. All of that's coming into our API, and our API says, hey, I don't know how to process it. All I do is take that order. So a request would be distributed to, let's say, one of these instances. That instance would say, all right, I'm going to create a record in Kinesis. I'm going to publish that particular event to Kinesis, and then I'm going to return a 201 created. An event comes in, published to Kinesis, return a 201 created. That's all the API does. It doesn't know what happens after that message is published to Kinesis. It doesn't need to know. So this is also an example of loose coupling, where we have the API doing one thing, it can continue to receive things even if our analytical processing is offline, right? And so within the Kinesis service, within Amazon Kinesis, we create Kinesis streams. We may create different streams for different purposes. For example, we may have a stream dedicated to processing events per pizza. So as an event comes in, we store that in Amazon Kinesis, and then our consuming applications can perform whatever analysis or different functionality on that particular stream based on pizzas. And we may have other streams. We may have a stream for for locations. We may have a stream for groups of regions or franchisees. And so let's just say that let's just focus on pizzas, for example, right? Our users want to receive notifications when their pizza goes through the different stages of the process, right? Hey, your pizza's out for delivery. Hey, your pizza's at your door. So a couple of things I want to point out here is that, one, we may want all of that data, we may want to flat file that to S3 so that we could maybe perform some type of advanced batch processing later and derive more deeper meaning out of all of that data than what we can do in real time, right? And so that's what Kinesis Firehose can help with. Kinesis Firehose, to put it simply, Kinesis Firehose is sort of an out-of-the-box solution for doing exactly that, for flat filing and deduplicating to S3 or to Amazon Redshift, right? And so we don't necessarily need to write code to do that. We could leverage Kinesis Firehose to do that for us as an out-of-the-box solution. Now, if we wanted to do our own custom processing, again, in real time, then we could write our own Kinesis-enabled applications. Now, we may have one application that is meant to look for a particular type of events, or just record every event, record the status of a particular pizza, right? So maybe this one application, each of these applications are ideally very small and very targeted. They do one type of processing. And so maybe one application is looking to see, oh, here's a particular pizza. For this particular pizza, and for the related order, here's the current status. Based on the event that I'm seeing, I can update the status in DynamoDB, right? So this is looking at that particular pizza event and updating the status of that pizza and status of the related order in DynamoDB. Our users then could essentially, our mobile application could essentially then query DynamoDB directly and pull that status. And so we could use DynamoDB as sort of a real-time dashboard. Another Kinesis application that we might use, we might run another application up here that is looking for certain events that warrant sending a push notification, right? So maybe the user has opted in to push notifications for when the pizza is out for delivery and when the pizza is at their door. And so perhaps that's all this application does, right? So this particular application here, perhaps all it does is looking for those events, and it says, oh, this event belongs to a user that wants these notifications, and then that
that particular application could be running just about anywhere. It could run on EC2, it could run within a container, it could run within a Lambda function. We have a number of options in that regard. And so that particular function then could leverage Amazon Pinpoint to send those push notifications, right? So that application tells Pinpoint to send a push notification to that user. And then Pinpoint can then not only send that push notification, but also gather its own analytics in regards to whether or not the user performed an action against that push notification. So as you can see, Kinesis is a very powerful platform that allows us to perform real-time processing on data as it's coming in, right? And we will take a closer look at the details of Kinesis streams as the course continues. Now let's take a further look at streaming data with Amazon Kinesis. Now again, Amazon Kinesis is a fully managed real-time streaming service. Kinesis allows us to ingest a large amount of data from many, many sources and then store that data temporarily. So with Kinesis, we can collect potentially terabytes worth of data every hour from hundreds of thousands of sources. Now, as these events are coming in, Kinesis does maintain that message order. So if your application depends on those messages being in order, Kinesis can help with that as well. Now, keep in mind that Kinesis is not really a long-term data store. It's a temporary data store. And we can configure Kinesis to keep those records anywhere from 1 to 7 days. Now, the way that we scale Kinesis is dependent on shards. Kinesis, under the hood, behind the scenes, is comprised of and powered by shards or nodes. And each shard is capable of 1,000 put operations per second. And so we can scale Kinesis by simply adding and removing shards. So taking a closer look here at a diagram, here we have an Amazon Kinesis stream. And going back to our earlier example with the pizza chain, we have millions of pizzas being delivered every day. And each pizza, as it goes through its various life cycle events, will generate events into this Kinesis stream. And so we have all of these records coming in, millions and millions of records coming in every day. And those are our records. Within Kinesis, those events would be our records. And so depending on the volume of traffic that we're talking about, depending on the level of events, there may be no way for any one shard to handle that. It's likely that a stream will have multiple shards so that you can handle that volume of data, right? So within the stream, we have these shards. And one of the things that Kinesis does is that it spreads that data across those shards. And ideally, that data is spread across those shards evenly. Now, the way that we determine which data goes to which shard, or the way that we help influence how that data is spread across shards, is with the partition key. Every record has a partition key. Now, the partition key does not have to be unique. It's simply used to determine which shard that particular record will go to. Now, in fact, in our example here, we know that each pizza will generate numerous events. And so we don't need the partition key to be unique. And it will be unique per pizza, but each pizza having multiple events we will have numerous events all with the same partition key, but Kinesis will add its own unique message key per message, right? And so by doing this, then we could say that behind the scenes, Kinesis is perhaps putting all of the events for pizzas 3 and 9 on one shard, all of the events for pizzas 2 and 4 on another, and then all of the events for pizzas 7 and 12 on yet another shard. And so again, ideally we choose a partition key that would allow us to spread those records across as evenly as possible across those shards. So now that we're ingesting all of these events, we need to process them. So one stream can be processed by multiple applications, and that's a very powerful feature of Kinesis. It allows us to perform different types of analysis on the same set of data. And so we could, maybe one application does some kind of aggregation and deduplication. Maybe another application is focused on real-time metric extraction, saving that to DynamoDB in order to inform a real-time dashboard. Perhaps another application is doing sliding window analysis, every hour or every day or every week, whatever the window happens to be. We may have another application that is specifically looking for certain events that require other types of processing or notifications to be sent as a result. Kinesis also very easily integrates with other data stores, right? So again, our data is essentially coming into Kinesis. Our analytical applications are performing their analysis and then storing their results somewhere else. Perhaps we're storing those results in DynamoDB. Maybe some things are stored in RDS, and other things may be stored in Redshift. We have our choice. We have a lot of different options, and the use of any one of these data stores is really easy. And so again, going back and kind of covering again something that we looked at earlier, is that again, we have this Kinesis stream where we are ingesting a vast amount of data that we want to analyze in real time. And then of course we have our Kinesis applications, where again, each application is doing its own type of processing or performing its own type of functionality specifically for certain types of things, pulling the same data but doing different types of operations on that same stream of data. So again, with Kinesis, when you hear the term Kinesis, we should think real time. And if you are in discussions with your team about different types of data, if you hear the term real time, if you have a need for performing some type of analysis in real time, think of Kinesis. Now let's review big data with Amazon EMR. With Amazon EMR, EMR simplifies or helps us simplify big data processing by providing us with a fully managed Hadoop framework. Now, of course, we don't have to run Hadoop. We could run some of the other Apache big data tools such as Spark or Presto or HBase. But the idea here is that we have the ability, whatever we're running, we can provision thousands of instances within an EMR cluster in order to process very large data sets quicker. And so EMR is really ideal for those data-intensive applications when you have potentially, many terabytes or even petabytes or more worth of data that you need to derive some kind of meaning from in a shorter period of time, right? So many different Amazon clients are doing all kinds of amazing things with EMR, such as data mining, log analysis, or even scientific simulations, such as weather models or electromagnetic field simulations, and then, of course, genomics. There are customers doing these things with EMR today. And, of course, EMR also integrates very easily with other services, and we can see that, an example of that here in this diagram. Now, this diagram is not by any means an exhaustive list of the services that EMR can connect with. This is just a few of the possibilities. But the point here is that we have within the EMR service, we can create an EMR cluster. And we have the ability to scale that cluster to just about any size we need, right? In some cases, maybe we have a small amount of data and we only need, maybe 2, maybe 20 nodes in that cluster. Maybe we need 200 or 2,000, right? It all depends on the nature of the work and the size of the data. And so we can pull data from just about anywhere. We could pull data from DynamoDB, perform our, maybe extract our transforms and then load that data into Redshift, right? And the same thing applies to S3. We may have a very large amount of data in S3 that we pull out that are in flat files. We pull that out. Maybe it's not even structured. Maybe it's semi-structured, right? Or maybe it's totally unstructured, and we're trying to pull out some type of useful data and then convert that into something that can load into Redshift, or convert that into results that could go to DynamoDB or to RDS, right? So the idea with EMR is, again, that we could pull data from just about anywhere, you name it. If there's data within AWS or even on premises, we could pull that into EMR, we could perform that very intense processing, and then store the results, again, pretty much anywhere. So EMR is really well suited for performing very intense processing on very large data sets that already exist. But with Spark or Spark streaming, you could also, a common pattern that plenty of Amazon customers use is to have Kinesis ingest the data, but then have Spark streaming running on EMR process the data. So EMR is not just for batch processing. It can also play a key component in real-time processing as well. Now let's talk about AWS Data Pipeline. With AWS Data Pipeline, we have the ability to move data between various stores, right? We may have all kinds of different databases and data stores, or even flat files within AWS and also on premises, and maybe not just one site, but maybe multiple sites, right? So we may have a need to move data from one place to another, and perhaps it's a one-time thing, perhaps it's an ongoing thing that occurs on regular intervals. And so Data Pipeline not only supports those sources within AWS, but it also supports sources outside of AWS. Those could be on premises, it could be a third party. It doesn't have to be inside AWS in order for us to move that data with Data Pipeline. Now, Data Pipeline can help us perform extract, transform, and load operations, but the Data Pipeline service itself doesn't do it. It will move the data or essentially hand the data to either EC2 or EMR for that ETL operation, and then once it's finished, it will then take it back and put it to where it's supposed to go. And so we can also configure Data Pipeline to take particular actions, right, such as executing SQL queries or even executing custom applications in order to store data or access data, right? So perhaps we have two different database engines that we need to move data between, or maybe we have the same engine but two different databases for two different purposes, and we want to get some type of data from one into another. And so we execute a SQL query to pull a particular set of data and then store that somewhere else. It also, like I mentioned earlier, it does support scheduling. So again, maybe you have, the need to regularly move data, perhaps every day or every week, on a regular schedule. Data needs to move from one place to another in order to support the updates that are coming in to the source, right? So Data Pipeline, again, can support scheduling. It also has built-in error handling, and the full execution logs are stored in S3. So it does give you full transparency as to what's going on in that movement of data. You're not left blind wondering what's happening, right? You do get to see everything that's going on, and if there were an issue, you could see that in the logs and also rely on that built-in error handling to either try again or inform you that something is going wrong. And so taking a look here at a diagram, again, this is not an exhaustive list of the possibilities. It's hopefully to show you that we can pull data from just about anywhere and move it just about anywhere. So classic examples might be that we have some type of a very large file in S3 that we want, and that has some kind of data, and we want that data available somewhere else. We could have potentially Redshift load files in S3 and we want those loaded into Redshift. Perhaps we have some kind of unstructured data in S3 and we need to do some type of processing or extraction and transformations before we can load it somewhere else. So we could, again, we could pull that data from S3 and then pass that on to either EMR or an EC2 instance to do the extraction and transformations, and then we could load that pretty much anywhere. We could load it to, maybe we're running MySQL on RDS or Postgres, or maybe we want to put certain types of data in DynamoDB. Perhaps we're running Cassandra on EC2 or MongoDB, right? So we could pull data, again, from just about anywhere and store it just about anywhere. And remember that data pipeline itself, the actual data pipeline service, is not in itself doing any kind of processing or transformations. It's only moving data from one place to another, though it does have the ability to execute SQL statements. So, for example, perhaps you have, Oracle on premises, and you want to get certain types of data out of that and into something in RDS. So perhaps data pipeline simply runs a SQL query against Oracle on premises and then takes that result set and stores it in RDS. Even if it's not Oracle there, you could be running MySQL or MariaDB or Postgres or just about anything. So again, when you are thinking about your architecture and you realize that you have various data sources, maybe several in AWS or different sources on premises, and you need to move data from one place to another, take a look at AWS Data Pipeline. Now let's review an introduction to Amazon Athena. With Amazon Athena, we gain the ability to perform serverless queries across vast data sets. By vast data sets, I mean petabytes worth of data, many petabytes worth of data. And by serverless, I mean that within the Athena service, there's no server or instance for us to create. If we compare this to something like RDS or Redshift or EMR, those services require us to create some instance of something, right? Even though AWS is managing that instance for us, the underlying infrastructure, there is still this resource that exists within our account that we are paying for even if we're not using it. But with Athena, there's nothing there. There is no instance of anything. It's completely serverless. There's nothing for us to manage other than configuring Athena, telling it what our data looks like, and then running queries. And so with Athena, the data resides in Amazon S3. Again, could be terabytes, could be many petabytes worth of data or more. And then all we have to do is define the schema, tell Athena what that data looks like, and then run our SQL queries. And one of the beautiful things about this, besides being serverless, is that there's no need for us to extract the data, no need to transform it, and no need to load it into anything else. The queries are run in place where it resides in S3. And so, again, comparing this to something like RDS or Redshift, where we have an instance sitting there that we're paying for, even when we aren't running queries, with Athena, the only thing that we pay for are the queries that we run. So we know that we're paying for work that was actually done rather than idle time. Now, behind the scenes, Athena uses Presto, and Presto is complete with full ANSI SQL support. So there's no need to learn any new DSL or new specific non-standard form of SQL. It's all standard ANSI SQL. So if you know that, you can step right into it and start running queries. Athena does support multiple data formats like CSV, JSON, ORC, Avro, and Parquet. So, you have your choice. You're not limited to any one or two things. You have a pretty wide variety of different types of formats that you can store that data in. And then, of course, when we run our queries within Athena, those queries are executed in parallel across some number of nodes. Now, of course, we don't really need to even be concerned about how many nodes are running. We just know that Amazon is managing all of the infrastructure necessary to make these queries run. And there's really nothing for us to do or even worry about. And so taking a look at another diagram here, again, within the Athena service, right? We have the Amazon Athena service. Again, there's nothing for us to create there. We just leverage the service itself. And so we might have our business intelligence software on premises, whatever that is, and we want to run queries across maybe many petabytes worth of data that's living here in Amazon S3. And so we connect to the Athena service using JDBC, ODBC drivers, and we define what the schema of our data looks like within S3, and we start running queries. And so the advantage of Athena over something like Redshift is that, keep in mind that with Redshift, the largest cluster is somewhere around 2 petabytes. But you may have data sets that are 200 petabytes in S3, and you want to run queries across that. So again, when you have very large data sets already in S3, and you don't want or need to extract and transform and load that data, take a look at Amazon Athena. Now let's review an introduction to Amazon Elasticsearch Service. With Amazon Elasticsearch Service, we gain access to fully managed Elasticsearch clusters. Now, very similar to RDS, where AWS is managing the operating system and the database engine, the same kind of thing applies here to Elasticsearch. AWS is managing the operating system and the Elasticsearch engine for us. So again, it's another opportunity for us to offload operational burdens. And so if we have a need for Elasticsearch, we can leverage the Elasticsearch service rather than managing Elasticsearch ourselves on EC2. And so when we build an Elasticsearch cluster, even if there's only one node in that cluster, we gain built-in integrations with a number of very useful services, such as one, Kibana. Kibana is a very powerful, very useful UI for interacting with Elasticsearch. And so in the least, you can search through records within Elasticsearch or create dashboards and even create analytical dashboards to help you derive meaning from whatever data you have in Elasticsearch. Elasticsearch clusters also provide built-in integration with Logstash, with AWS Lambda, so that as maybe your data is coming in through perhaps Kinesis, for example, and Lambda can automatically pull that data out of Kinesis, do some type of processing, and then store something in Elasticsearch. Or vice versa. Perhaps Lambda can pull data out of Elasticsearch and create some kind of output somewhere else, be it a record in another data store or a notification going out through the notification service or Pinpoint. And then all kinds of other integrations with other Amazon services. Elasticsearch service clusters can scale to well over a petabyte, right? So we're not necessarily limited in our data. And of course, when we create an Elasticsearch service cluster, we do get direct access to the Elasticsearch API, and which means that once we create that cluster, very similar to RDS, we can connect to an RDS instance directly without having to go through the Amazon API. The same applies to Elasticsearch clusters. Once that search cluster is created, it has its own DNS endpoint that we can connect to and gain direct access to the Elasticsearch API to which we can program against. And then because there are instances, right, because Elasticsearch does include some type of an instance that is running, we can provide network isolation for that instance by putting that in our own VPC and controlling the networking environment around that instance. Elasticsearch clusters also support encryption at rest with the AWS Key Management Service, and we'll talk in great detail about KMS later on. But if you need this data to be encrypted at rest, then we can gain that by integrating with KMS, where KMS is managing the keys and Elasticsearch is performing the encryption. And we can also rest well at night knowing that the data that is stored in that cluster is replicated. Very much like other services, the data that we store in Elasticsearch clusters is replicated across multiple AZs, right? So again, it's inherently fault tolerant and durable, so that if any one data center is offline, our data is still available. And of course, Elasticsearch is also very tightly integrated with other services. It makes it very easy to pull data in from one place and then get that data into Elasticsearch. And one example may be CloudWatch logs. And we're going to see an example of this later on, where perhaps our application logs are going to CloudWatch logs. And we can very easily, with one command line on the CLI tools or 2 clicks in the management console, we could very easily pipe data coming into CloudWatch logs and have that go to an Elasticsearch cluster, so that we could use something like Kibana in order to perform, viewing, searching, or analytical processes on that data in Elasticsearch, right? So if you currently have a need for Elasticsearch and you don't want to manage the operating system and the Elasticsearch engine yourself on EC2, take a look at the Amazon Elasticsearch service. Now let's review a use case of analytics for subscription video on demand service.
Well, as you can see, when it comes to analytics, we have a lot of options. So we'll just start from the top and move our way down here and kind of explain what's going on. So let's just say that we have an API, and that API is powered by perhaps containers running within ECS or ECS for Kubernetes. It could be running on EC2 directly, but in this example, this comes from personal experience of running a video subscription service very similar to Netflix, where it was all of the microservices were powered by ECS, and they were all available through a load balancer. And so all of those microservices, a couple of dozen different applications, were all sending logs to CloudWatch logs. And the benefit of that is by streaming those logs to CloudWatch logs, we had the benefit of, if a container went away, which it often did, then we still had those logs. We didn't have to worry about them, being unavailable. And then it was very easy to connect CloudWatch logs to Elasticsearch, the Amazon Elasticsearch service, and have those logs stream essentially in real time into Elasticsearch, so that developers could very easily access those logs within Elasticsearch. Now, technically, developers could access logs in CloudWatch logs, but Elasticsearch gave us much more power and flexibility in how we could not only view those logs, but run analysis on those logs as well. So even from an application performance standpoint is really the biggest benefit to our developers, is really understanding how our applications are performing by looking at those kinds of logs. And so we also had several different databases within the relational databases service. We had MySQL data stores. We also had Postgre data stores or databases within Aurora and non-Aurora based RDS instances. Certain data stored here, like user account information, video metadata, and a number of other things. And then we also had a lot of financial information stored here in a SQL Server database, primarily because the finance and accounting departments, their tools were all Windows-based, and we stored information as it related to not just billing, but also as it related to the cost of producing videos, as it related to the cost of marketing those videos. And so by storing all of that there, then finance and accounting could use their Windows-based tools to work with that data, but we could also as we'll talk more about later, we could pull that in to Redshift. And so we also stored a number of other types of information in DynamoDB. We actually duplicated a lot of the user information. The video information was duplicated from MySQL into DynamoDB, and that's because we had CMS tools, content management systems, that allowed editors and content creators to edit that content here, but then for running in production for our users and coming from their mobile applications and from the website, they got a much better performance by reading it from DynamoDB. And so we had other services in the background that could replicate that data from MySQL over to DynamoDB, doing an ETL operation. We had other data coming in as users were performing different things, as they clicked on a web page, as they searched for something, as they pressed play, as they paused, as they fast forward, and as they continued to watch a video. There's so many different events that users were generating that our API was collecting. A lot of those events were sent into Amazon Kinesis. And Amazon Kinesis gave us that reliable way of ingesting a very high volume of data coming in at a high velocity. And so we split that in a couple of different ways. We had what we would call Kinesis-enabled applications, or consumers, Kinesis consumers, that were reading from this Kinesis stream and performing a number of different kinds of analysis on that stream. So we were doing real-time information, such as how many people are viewing the website right now, how many people are viewing the videos right now, and then other kinds of longer-term trend analysis, such as what videos are more popular based on the length that they were watched. Are people watching to a certain point and then skipping ahead? That kind of information. So we could use Kinesis-enabled applications, consumers, to read from that stream, perform analysis on real-time kinds of things, and store that in DynamoDB. And then, of course, other users could potentially read that. Like if we wanted to also display the popularity of a particular video, then these Kinesis applications could determine that popularity, and then other users could read that from DynamoDB. We also had Kinesis. These Kinesis streams could connect to Kinesis Data Firehose, and Kinesis Data Firehose is sort of an out-of-the-box solution for writing Kinesis data either directly to S3 or directly to Redshift, among a couple of other places. And so here we could leverage Kinesis Firehose without writing our own code, just leverage Kinesis Firehose to get that data into flat files in S3, where they would remain for some time. And from there, we had access to large data sets that we could run analysis on using Amazon Athena. So our analytics team, our data team, could use their own SQL-based tools connecting to Athena using ODBC, JDBC drivers, and running whatever ad hoc queries they could think of against that large data set within S3. And then, of course, like I mentioned earlier, we had user data, we had video, and a number of different types of data here in MySQL. And we had financial information here as it related to those videos. And then we had real-time popularity information within DynamoDB. And so we could use Data Pipeline to pull all of that data in from all of these various sources, performing an extract and transformation, and then load that into Redshift so that our analytics team could perform regular queries around, well, how did the popularity of a video, how does the popularity of a video relate to the money that we put in to produce it? We spent a certain amount of money to make this particular video or this series of videos, and we spent a certain amount of money to market it. Are we seeing a level of engagement to justify that expense, right? And so the only way to know that is to be able to join, user data, account data with other, financial data with popularity data. And we can do that by pulling all of that data in to Redshift and allowing our analytics team to, very much like Athena, they could connect to Amazon Redshift and run any ad hoc query they can think of across a very large data set and determine not only popularity as it relates to cost, but also how does our marketing efforts relate to users continuing their memberships and their subscriptions. You know, are users canceling their subscriptions? And is there a relationship between activity in the video and users either canceling or renewing their memberships? Is there a relationship between activity on a new series and whether or not we were getting new people subscribed, new users signing up? And then how did, is the money that we're making on that, is it allowing us to be profitable considering the money that we spent to create and market that, right? So there was a lot of information here that required some very complex SQL statements that could only really be run in one place. And Redshift served that really well. So as you can see, we have, when it comes to analytics within AWS, we have a lot of options, a lot of very powerful options, and it's very common for applications to use a number of different data stores because each one of these is targeted for a particular use case, and it serves that kind of data in that kind of scenario, that kind of access pattern really well. Right, and of course there are others. There's Amazon EMR, which was not really used in this particular scenario, but that is also an option. So again, as you continue to move forward in your exploration of AWS, I would highly encourage you to explore some of these tools, such as Kinesis, DynamoDB, Athena, Redshift, Elasticsearch, and of course Amazon EMR as well.
Ensuring high availability, performance, security, and cost effectiveness requires instrumentation, and not just the ability to evaluate the past, but more importantly, the ability to respond to changing conditions now, in near real time. In this lesson, we will review monitoring and log collection, user activity tracking, inventory and change tracking, as well as tools to help build a more secure approach to configuration management.
Now let's review monitoring with Amazon CloudWatch. Now with Amazon CloudWatch, we can gain instrumentation for our infrastructure by, one, collecting metrics, key performance metrics from our EC2 instances and ELB volumes, RDS instances, and so on. We can also collect logs from those systems, and we'll talk more about logs later on. But for now, let's focus on collecting metrics. So again, this is one of the key things that Amazon CloudWatch does, is to collect performance metrics. And it's important to remember that these metrics are only stored for up to 2 weeks. And so if you needed the ability to see much more historical data, if, for example, if you wanted to compare this week this year with this week last year, then you would need to pull those metrics in to either your own system, perhaps on EC2 or on premises, or rely on a third-party service such as New Relic or Datadog or something else. And of course, like all Amazon services, the CloudWatch allows us to pull these metrics out by accessing the API. And we can give third parties access to that API so that a third party like New Relic or Datadog or Nagios running on premises can connect to CloudWatch and pull those metrics in. Now, every service, or most services anyway, will generate their own unique set of metrics. So EC2 has a particular set of metrics, RDS, Redshift, Elasticache, and so on. They all generate their own unique set of metrics. We also have the ability to publish custom metrics into CloudWatch. So if our own applications, if we wanted to publish something like JVM heap size, or the number of processes, the number of concurrent threads, render times, those kinds of things,
If there are metrics that are very easy for our application to readily grab, then it's fairly trivial to publish those to CloudWatch so that we can monitor not only things reported by, say, the hypervisor, but also things reported by our applications. And then, of course, we can correlate things that are happening within our application to things that are happening within our infrastructure. And so now, for example, if we take a look at EC2, with EC2, the default interval collection is every 5 minutes, right? And so for things like auto-scaling, that's going to be too long. We may need to scale within a minute or two. And so we can pay an extra fee per instance to gain access to a detailed 1-minute interval. Now, a thing to keep in mind about EC2 is that these metrics that EC2 collects and reports are reported by the hypervisor. And now the hypervisor will have a very accurate, perhaps the most accurate metric on something like CPU usage and network I/O, disk I/O, and a few other metrics. But one thing to keep in mind is that the hypervisor has no idea how memory is being used. And so while the hypervisor may know how much memory an EC2 instance actually has, it doesn't know how it's being used. So if you need detailed memory usage, that kind of metric needs to be reported to CloudWatch from inside the instance. And of course, CloudWatch does provide a very powerful agent that can just readily, out of the box, report very detailed memory usage. And of course, those are reported as custom metrics, and we do pay an additional fee per custom metric. Now, for the Elastic Load Balancer, as an example, the default is 1 minute, and that's so that that service can support scaling. For the relational database service, we do get access to memory because the database engine is already running, and typically the database engines are aware of memory usage and connections and disk I/O and things like that. Then we are relying on the software that's already a part of that instance to report those things. With DynamoDB, we do get such things like read and write throughput. And again, this is not an exhaustive list, but just an example of the type of metrics that we might see with different services. Another powerful feature that we have with CloudWatch is the ability to create alarms, where we want to either be notified when something is happening, or we want to leverage the breach of a threshold to trigger some other process. And so with CloudWatch alarms, we define a threshold. We say, well, I want something to happen. I want to create an alarm when some number, some metric is either too high or too low. And so even though we use the word alarm, it does not necessarily signal an emergency. It simply means when the alarm is triggered, it simply means that a number is too high or too low for too long of a period of time. And whether or not there's an emergency, that's up to you to determine based on the nature of your application on that particular infrastructure. But we can use those alarms to trigger things like auto-scaling. We can also use that alarm to simply terminate an instance. We could also use the alarm to reboot an instance. There could be a case where maybe you are aware of a memory leak, as an example, and you're waiting on developers to fix it in code, but in the meantime, you're trying to mitigate the issue within infrastructure. So perhaps as a stopgap measure, you have you're collecting memory as a custom metric, and then when memory becomes too high, you simply reboot the machine, right? Of course, that's not a long-term solution. It's just one example of something that you could do with alarms. It's also important to remember that with most Amazon services, there are both hard limits and soft limits. Hard limits are just the nature of the technology, but soft limits can be overridden by submitting a ticket to Amazon support. And so with CloudWatch, there is an initial a limit of 5,000 alarms per account. So that's 5,000 alarms across all the regions, right? Some limits within AWS are specific to a region, and some are more broad. Some are specific to an account across all regions. So let's take a look here at a diagram. In this diagram, we are collecting, you can see here that we have a load balancer, and this load balancer is sending metrics to CloudWatch, such as requests per minute, the number of 500s, the number of 400s, backend errors, and those kinds of things. Our EC2 instances individually are also reporting those metrics, such as CPU usage, disk I/O, network I/O, and then our autoscaling group is also reporting metrics about that group in aggregate. So average CPU, average disk usage, and network usage, and so on. Our RDS instance is also reporting metrics into CloudWatch. So CloudWatch is collecting these metrics from various different types of places. And so in the least, one really helpful thing is if you are seeing some kind of performance degradation, you could look back on those CloudWatch metrics in the console and create a graph and overlay different metrics, and then correlate what you're seeing in the load balancer, maybe requests per minute, how that affects CPU or disk I/O within your EC2 instances, and or how that is affecting your database, right? And then, of course, here we have an alarm. You can see here that we've defined an alarm that says when CPU utilization is greater than 80% for 2 periods of 1 minute. So essentially, when CPU is greater than 80% for 2 minutes, then we want an alarm to go off. Now, again, it's not necessarily an emergency, and what happens is totally up to us. We get to configure what happens when that alarm goes off. It's very possible that nothing happens, right? We can do that. We could have an alarm that just goes off and then nothing happens. But here, in this example, we may want that alarm. You can see that we could use that alarm to trigger autoscaling, so that perhaps that alarm signifies that there is more work to be done than what can be done with our current set of instances. And so this could signal the need to grow and expand our fleet of EC2 instances in order to meet that demand. We could also send that alarm out through the simple notification service. And so here we have a simple notification topic, and then from there we could do a number of things. We could have Lambda respond to that, right? So we could write a Lambda function that would, respond to that alarm in some kind of intelligent way, doing some kind of automated process in response to that alarm. Another thing that we could do is to perhaps, if that alarm is for a particular application, then perhaps we send that alarm to a Slack channel, right? So that, our developers are basically, in many teams that I've worked with, developers have 2 things in front of them all the time: their IDE and their Slack channel. And so instead of putting notifications and alarms off in some place that requires them to go look for them, then it's better, in my experience, to have that alarm go right to where they're already at, such as Slack. And also, instead of that alarm or notification going to one person and waiting for that one person, we could send that notification to an entire team of people, so that we have a greater chance of some, people or multiple people being aware of an issue. And I've seen that, be a really powerful pattern for helping development teams jump on issues much faster. We could also have those alarms be sent to some other kind of ticketing issue or bug tracking software like Jira, or some kind of a SIM management system. Or like I mentioned, maybe you're not using Slack, but maybe you're using some other kind of chat system. The point is to automate the collection of metrics, automate the triggering of alarms, and then get those notifications to the appropriate people in an efficient way, right? So you can see that CloudWatch plays a very key
role within our AWS infrastructure. And we will take a closer look at CloudWatch and CloudWatch logs as the course progresses. Now let's talk about log collection with Amazon CloudWatch logs. So before we get into the nature and details of CloudWatch logs, let's first take a look at where logs come from. We have applications running in different places, and we have other resources that are generating logs. And so a number of places, including the Elastic Load Balancer, will generate access logs. We could have applications running on EC2. They could be running within the Elastic Container Service, within containers. We might have applications running within Lambda. Now, of course, Lambda will generate its own logs, whether or not your application is writing any logs or not. Lambda will include its own logs. And then, of course, we have S3 access logs, right? So again, if we're storing static content, for example, images, CSS, PDF files, and so on in S3, and those are publicly available to, as part of web assets, for some kind of a website or web application, then as those files are accessed, S3 will generate its own access logs. And then, of course, we can also collect VPC flow logs. So an important component of network security is understanding the nature of the traffic, whether traffic is being accepted or rejected. And so you can look at least metadata about network traffic with VPC flow logs. We also have CloudFront access logs. If our load balancer or our S3 buckets are behind a CloudFront distribution and our users are going through those edge locations to retrieve that data, then CloudFront will generate access logs. We also have CloudTrail. CloudTrail is a service that collects and records API calls. So anything that you do through the AWS API, for the purpose of creating or managing some Amazon resource, then those calls to the API are recorded. The credentials that are used and metadata about that request are recorded through CloudTrail. And of course, there are plenty of more places where logs could be generated from. So again, in terms of capturing logs, let's take a look at this diagram. And you'll see here, of course, we have our users out there, and our users are accessing our dynamic content and our static content through those edge locations. And of course, those edge locations, CloudFront is sending CloudFront access logs to S3. And then, of course, we have our load balancer here, and our load balancer is sending access logs directly to S3. We have our VPC flow logs, which are being collected directly by CloudWatch logs. Our Lambda functions are being collected by CloudWatch logs. And then, of course, we could, for our applications running on EC2, we have a couple of options. We could use the CloudWatch logs API to have our application log directly to CloudWatch logs. Or we could have our application log to local files and then have the CloudWatch agent essentially stream those files in near real time to the CloudWatch log service. So either way, we have our choice there in terms of how we get our application logs to CloudWatch logs. But the point here is that either way, we can collect those logs to CloudWatch logs. And so the benefit here is that those days of shelling into individual instances and trying to find the log files, where are they? Are they in varlib, or are they in opt somewhere? Trying to find them to begin with, and then getting to that directory only to find out that they've been rotated, or maybe they haven't. Maybe they're just so large that you can't find what you're looking for. And so I've been there. I've done that. It's a painful process, right? And so the idea here with CloudWatch logs is that, one of the patterns of cloud computing
is to treat logs as streams. And so you could have, within EC2, remember that we could have just about any number of instances here. We could have 2, we could have 200, we could have 2,000. And, like I've mentioned before, that these instances are essentially disposable, right? There could be an issue where they just go away on their own, or auto-scaling can terminate them, or we may decide to terminate them. Or they could be terminated by accident, right? So we can't count on the EC2 instance being there. Therefore, we can't count on the logs being there for any length of time. And so when you have such a dynamic system where EC2 instances are coming and going, it's really important that we have one central place to which we can record our logs. That way, we don't have to worry about the machine being gone. We know that we've already collected as much logs as we can from that instance before it went away. And we have, not only do we have one place to collect it, but we have one place from which we can pull those logs instead of having to hunt them down across all of these various disparate places. Now, of course, like I mentioned earlier, we also have CloudTrail. Now, CloudTrail could go directly to S3. We could have CloudTrail send files to S3, but we also have the option of having CloudTrail send the various API events directly to CloudWatch logs so that we get more of a real-time insight into what's happening with CloudTrail and what's happening with our credentials and our AWS environment. We also have Route 53 DNS queries. So as our users are out there and they are making DNS queries to various domain names, and maybe we use different subdomains for different purposes. Maybe we use different subdomains for different marketing campaigns. And so perhaps there's some kind of data to be found or some type of value to be found in analyzing DNS queries. And so we can capture those as well. Route 53 can send its DNS query data to CloudWatch logs. And so we could also have CloudWatch logs archive those logs off to S3, and then perhaps from S3 we could have EMR or Athena pull those logs and perform some kind of an analysis or SQL query on the data from S3. And maybe that kind of thing is performed, some kind of processing is performed in the first week or the first 30 days of those logs, and then after that, perhaps we need to keep those logs for some extended period of time because of legal or regulatory compliance. And so we also have the ability to configure those lifecycle rules and have those logs archived to Glacier so we can lower our long-term cost of archiving data that we have to keep. So again, when you think about your applications running in these various places within AWS, whether they're running on EC2 or in containers, whether they're running in Lambda, and you want a central place to collect those logs, take a look at Amazon CloudWatch logs. Now let's talk about user activity tracking with AWS CloudTrail. With AWS CloudTrail, we have the ability to record all of the calls made to the AWS API. So when our team is using their credentials, whether it be long-term credentials or temporary credentials, the fact that some set of credentials were used to at least attempt to create or delete or otherwise modify Amazon resources, then that API call is recorded, and the result of that is also recorded, whether or not it was a success or was a failure due to some kind of an error or invalid credentials. And so again, CloudTrail records all of the calls made to AWS APIs, and we can configure CloudTrail to deliver those log files to an S3 bucket, or we could also have AWS CloudTrail deliver log events to CloudWatch logs in near real time. And so these log files in the data includes the identity
of some kind of a key marking the identity of those credentials, the source IP, and a number of request and response details. Now, of course, if you're using the API to get some kind of sensitive data into AWS, then the data itself, it will not be recorded. CloudTrail is not recording sensitive information. Even for the identity, usually these credentials have a two components to them. There's a key, and then there's a secret. And the secret is not recorded, but the key is, because the key is meant to be public. And like I said, that the actual data is not recorded. And so another thing that's not recorded, several things, would be like the operating system logs, right? So if you're running Ubuntu or Windows or Red Hat on EC2, anything happening inside that operating system, that is not recorded by CloudTrail. Database queries are also not recorded. These are just a couple of examples of things that are not recorded, right? So hold that thought. We're going to talk more about that here in just a moment. So let's take a look at this diagram. And again, we have the AWS API, and from wherever we are, we could be making calls to the API from on premises, from our laptop at home, or even from within AWS. But either way, these calls are coming into the API, and perhaps some of those calls are coming from the CLI tools. Perhaps some of those calls are being generated from the SDKs, and perhaps some of those are coming in through the API from the AWS Web Console, right? It doesn't really matter where they come from. The fact is that the CLI tools, the SDKs, and the Web Console all make use of the API. There is no tool that we have access to as a customer that can in any way skirt the API. Everything that we do goes through it. And so you'll also notice here that in this diagram, we're making use of two different regions. And so we have the ability to turn CloudTrail on region by region, or we could turn CloudTrail on for all regions at once. And so a typical pattern is that when we turn CloudTrail on, it's generally easier to deal with logs in one place, right? And so here what we're seeing is that the CloudTrail is essentially running within each region, but each CloudTrail service for that region is sending its data to the same S3 bucket, right? So now we have one place that we can go to retrieve those CloudTrail log files. And so again, it could be that we have other services within Amazon. We could have, for example, Jenkins running on EC2, and Jenkins is responsible for communicating with the Amazon API in order to upload artifacts to S3. That call would also be captured, So again, anything that uses the API will be captured. But if we notice here in this diagram, we have EC2 instances running. Of course, the API was used to launch those instances. The API would be used to terminate those instances. But once those instances are running, there is then an operating system. If we shell into that operating system, if we gain some kind of remote access, now we're in a completely different realm of authentication. We're within the realm of the operating system. It has its own set of credentials. And so anything that we do in there is CloudTrail is completely blind to, right? So if we need that kind of access logging, we would have to collect that with CloudWatch logs. And the same is true for our databases, right? If we have some type of relational database running in RDS, again, the AWS API would be used to create the database, but then once we have that database and we want to connect to it and start running queries, the database itself has its own realm of authentication. We connect to that and we use database level credentials. And anything happening within the database engine, any alters to tables, any schema changes, any SQL queries that are run, CloudTrail is blind to that activity as well, right? So again, for anyone who really needs to satisfy, change management or compliance, AWS CloudTrail is a key service that allows you to record all of the calls, including the credentials that were used, as they are made to the AWS API. Now let's talk about automation with AWS CloudFormation. With AWS CloudFormation, we gain the ability to automate the creation and management of our infrastructure. And so CloudFormation uses template-based infrastructure management, where we express our infrastructure as code, and we can do that with a declarative programming, right? So the benefit of declarative programming versus imperative programming is that we essentially define or declare the resources that we want and the way that we want them connected and related, and we can do that writing either JSON or YAML. And we don't have to worry about the order of operations. We don't have to worry about imperative instructions. And we don't have to worry about serial versus parallel executions. We simply define in that template all of the things that we want. We pass that template to the CloudFormation engine and allow the CloudFormation engine to worry about the imperative instructions. We allow CloudFormation engine to worry about, which resource needs to be built first before it can then build other resources. And so another benefit of CloudFormation, as opposed to something like OpsWorks or Beanstalk or third-party tools, is that it offers us access to the full breadth of AWS. The great majority of AWS resources can be created, updated, deleted, or managed by CloudFormation. Not everything. Generally, new services that are launched, new features and new options generally do take some time to make their way into CloudFormation, right? So if you get in there and you find something that's not available, it's usually just a matter of time. And so another benefit of CloudFormation is that because it is template-based, because we are expressing our infrastructure as code, we can and ideally should store that template in source control. And from there, we can apply all the tools and procedures of software development to our infrastructure. We can gain the efficiencies of continuous integration and continuous delivery with our infrastructure. And so we can, by putting it in source control, we can more easily collaborate on our infrastructure, or we could fork, we can branch, we can merge, we could do pull requests where, maybe perhaps one member of our team is writing a template and another more senior member of the team is doing a code review before that pull request is actually merged, right? So we have the ability to again, apply the same kind of processes that we were using for good software development. And the other benefit of CloudFormation, of expressing our infrastructure as code, is that we now have the ability to write a template once and then deploy it many times. You may have certain types of applications or certain patterns of infrastructure that are deployed numerous times within a particular environment. Or maybe you have one thing that needs to exist across different environments like dev, test, stage, production, and so on. Or maybe you want to make use of multiple regions. And so we want the ability to create an infrastructure in numerous regions. And instead of creating them manually over and over again, by writing a template once, we can very easily deploy it many times. And then, of course, we could also create a library for common architectures. And, of course, AWS also offers a related service called the Service Catalog, which is based on CloudFormation. And so by creating common architectures in CloudFormation, we could then make those available to other members of our team through the Service Catalog, so that by doing that, not everyone needs to know how to write CloudFormation. Perhaps a few members of the team are really, really good at CloudFormation and fluent, and then they can make common things available to other members of the team simply to launch and create. Another nice thing about CloudFormation is that it does not impose its own model. When you have other configuration management tools like Chef and Puppet and different things, then a lot of these kinds of tools tend to impose a particular model, where and there's a box within which you have to work. And really the only thing that CloudFormation is imposing is the syntax of the JSON or YAML. But beyond that, you have complete freedom to create any infrastructure in any way that you see fit. So once we have a template created, we could give that template directly to the CloudFormation engine and then have the CloudFormation engine create those resources, or we could take it a step further and have that template go through an entire pipeline. So let's take a look at a diagram here. In this diagram, we have our CloudFormation template, right? And perhaps we've taken some time to write and define or declare a number of resources that we want built, and we've defined the ways in which we want those resources related, how they connect to one another. Now, again, like I said, we could, if we wanted to, we could send that template directly to the CloudFormation engine and have that engine then build out all of those resources and manage those resources underneath a stack. But by doing that, we miss out on an opportunity to automate the testing of that template, right? So instead of doing that, instead of sending it directly to the CloudFormation engine, perhaps we commit that to CodeCommit. CodeCommit is Amazon's private Git repository hosting. So it's essentially Amazon's answer to GitHub, right? So we can create private Git repositories within CodeCommit, and we can create feature branches, we can merge, we can create pull requests, all of those great processes for software development. And so perhaps we do a pull request here, and one member of the team can look over that template and suggest changes. And once the team as a whole is satisfied with that state of the template, then once it's merged into a particular, let's say, for example, merged back into the master branch, then that merging to the master branch we could configure code pipeline, and we could configure code pipeline to pull that template in and then pass that template on to something like Code Build or Lambda, or either way, they're both well suited for doing these types of automated processes where we have code and we need that code to be tested, that code to be built, and then that code to be deployed. And so here, our code is expressing our infrastructure. And so the beautiful thing about this particular pattern is that now we have the ability with Code Build or Lambda to run tests on our infrastructure. We can use automated tests to ensure that our infrastructure that is being expressed in a way that satisfies business policies, security policies, compliance policies, and so on, right? And so the nice thing about that is that we can validate our infrastructure before anything is ever even built. We can prevent building things and spending money on resources that we know we will end up tearing down anyway due to some misconfiguration, right? Those are the kinds of things that automated testing can help us avoid. Once Code Build or Lambda has verified that our template meets all of our business requirements, policies, and so on, it can then send that to the CloudFormation engine. And the CloudFormation engine is then responsible for building the resources that are expressed in the right order. For many resources, CloudFormation is already aware that, for example, before it can launch an EC2 instance into a subnet, it has to create the subnet. Before it can create the subnet, it has to create the VPC, right? So for many resources, it is aware of dependencies. It is aware of the order of operations. Doesn't matter what order they come in the template.
CloudFormation already knows that. And then once CloudFormation builds out, so let's say that we have all of these moving parts here, right? Let's say that we have VPCs, we have load balancers, we have S3 buckets and auto-scaling groups. We even have moving parts that aren't even necessarily shown here on the diagram, but all of these moving parts would then be essentially managed underneath what we call a stack. And so if we wanted to update that, we could go back here to our template, make changes to the template, push that template back through the pipeline, and have CloudFormation update that existing stack. And then, of course, we could use this pattern to ease the development and ease the ongoing testing and deployments of any environment, be it development, testing, production. Maybe we are deploying to multiple regions. And it's also really powerful and really helpful for temporary environments. Perhaps developers want to deploy a feature to an isolated environment so that they aren't interfering with dev, stage, and production, right? And so we could use this pattern to very easily deploy, some kind of a temporary environment, allow that environment to prove some kind of point, and then when we're done, all we have to do is come back here to CloudFormation and tell CloudFormation to delete the stack. And if we delete the stack, CloudFormation will then remove all of the components, all of the resources that were included in that stack, right? So you can see that CloudFormation is a very powerful tool for automating the creation and ongoing management of your resources. Now, another powerful feature of this pattern too is that Code Pipeline, as things are happening within Code Pipeline, we can receive notifications throughout that process. All of the lifecycle events that happen in that Code Pipeline process can be sent through the simple notification service. And then, once any kind of testing that's happening here could send its output through simple notification service. And then, of course, the CloudFormation engine could also send its lifecycle events, its status throughout the lifecycle of creating these different resources. And so with every step along the way, whether things succeed or whether something fails, all of those events being sent through the simple notification service could then be sent pretty much anywhere else, right? We could have that information, for example, be fed into a Slack channel so an entire team is aware of the current state of that deployment, whether it be to dev or whether it be to production. Right? So as you can see, AWS CloudFormation really gives us a very powerful platform that we can use to automate the deployment of our infrastructure throughout AWS. And one last point here about CloudFormation, and this is true for automation in general, whether you use CloudFormation or something else, such as a third-party tool like Terraform or Ansible, the only way to truly realize the full power and benefit of AWS, the efficiency, the performance, the agility, flexibility, cost savings, and security, the only way to truly realize and gain all of that is through automation. There's no way that you can gain all of that by doing things manually every time, right? So my advice for those of us that are new to AWS is to really explore these kinds of automation tools like CloudFormation, like third-party tools like Terraform and Ansible, because in the long term, these kinds of automation tools can really make your life a whole lot easier. Let's take a look at a demo of creating resources with AWS CloudFormation.
From the Management Console dashboard, we'll go ahead and go to CloudFormation. And you'll see here that we'll go ahead and make sure that we're here on the stacks menu item, and we can shrink that. And we don't have any stacks yet. So before we create one, let's take a look at some code. All right, so here in my editor, you can see that we are going to create, as the description says, we're creating a single VPC with 2 public and 2 private subnets. You'll remember that we did that manually. At least we created a VPC with 1 public subnet and 1 private subnet in an earlier demo. We did that manually. And here we're going to see how we can do that through automation. And so again, all of the demos up until now, we have created things manually. We created VPCs and subnets, EC2 instances, RDS instance. We've created DynamoDB tables, and all of that stuff we did manually. In a sandbox environment, that's perfectly fine. If you're wanting to get in and just learn AWS and experiment, try something out, prototype, then doing things manually in the console is probably perfectly fine. But in a real-world scenario, when you're working with a team and you're launching real applications out there for customers and end users to use, then I would highly, highly recommend that you avoid doing things manually. We only did those things manually here, in this video course as a way just to illustrate the principles of those services. But ultimately, I highly recommend using some kind of an automation tool like CloudFormation. It doesn't have to be CloudFormation. You can use other third-party tools like Terraform or Ansible or something else, right? So let's take a look here at some of the resources that we're creating. So we're essentially expressing our infrastructure as code, and so I don't have to worry about imperative instructions. I don't have to explicitly state, hey, build this, then do that, and then do this, and if this condition. I don't have to worry about imperative instructions. I'm simply defining or declaring the kinds of resources that I want. So here I want a VPC, and then I give it certain properties. I want DNS support turned on, I want DNS host names turned on, and here I want certain tags. And then down here I'm creating subnets and the same thing. And so again, you'll notice that there are no imperative instructions. It's all just me saying, hey, I want these kinds of resources to be built, and I want them to be related in certain ways. And you'll see here that this particular subnet DMZA, is related to the VPC. You'll see here that we're referencing the VPC that we're creating up here. So that's really all CloudFormation is a way of us describing these are the resources I want created, and this is the way that I want them to be related to one another. And the CloudFormation engine will take care of all of the imperative instructions. It will take care of the order of operations for the most part. It knows that before it can create the subnet, it first has to create the VPC. It doesn't really matter what order they come in this template. It knows that it has to build one before the other, right? So that this VPC could technically be listed last in the template, but it would still be built first. Now you'll also notice that we are here, if you remember from the earlier demo, when we created the VPC, we had to specify a range of IP addresses, and the same thing for the subnet, and that's called a CIDR block. It's just a way of expressing a range of IP addresses. Well, if I were to hard code that, right, if I were to put in 10.000/16, if I hard coded that, then that's all that this template will ever give me. It becomes inflexible. It becomes too specific. But if instead of hard coding it, if I instead use a variable or a parameter, then now here I'm referencing. You'll notice this REF means reference. I'm referencing VPC subnet CIDRs, which is a parameter up here that I get to specify at runtime. So when I launch this template to the CloudFormation engine, then I get to enter in that CIDR block, and then the whatever value I put in here, whatever value I put in there will come out here. And then down here, AWS gives us a number of different what we call intrinsic functions. The CloudFormation engine allows us to perform, use these intrinsic functions to make our stacks much more flexible and programmatic. And so here, I'm essentially saying, hey, give me a CIDR block or a smaller CIDR block from a larger CIDR block. That's what this intrinsic function does. It says give me a smaller block from a larger block, and then that essentially returns an array, and from that I can select the arrays being 0 indexed. I can select the 0 element, or the first, meaning the first element in that array. And so for all of my subnets, you'll notice that they all look the same, except down here on the next subnet, I'm selecting the second element in that array, and so on and so forth. So by doing that, I don't need to hard code anything, and I don't need to specify a separate parameter for each subnet. All 4 subnets can be derived from that one CIDR block that belongs to the VPC. So it makes coding this whole thing much easier. And then, of course, we can add our tags. You'll see that we're adding a number of different tags to these subnets. And then down here, we're creating subnets that are meant to hold nodes or private application servers, right? And you'll also notice that even the availability zone is programmatic. Remember earlier in the VPC demo when we created subnets, we had to select the availability zone that the subnet belonged to. And here, instead of hard coding that, I can also use, again, intrinsic functions to say, well, you know what, give me the availability zones, get the current availability zones for the current region. So I don't even have to specify the region here. If I run this in US West 2, then it will give me all of the availability zones for that region. If I run this in US East 1, this particular function will give me all of the availability zones in that region. And then, of course, I can select the third element from that array. And then, of course, I might want to know, once this stack is completed, once all of those resources, the VPC and the 4 subnets are fully created, successfully completed, then I would want to know certain things about those resources without having to go and dig for it. So I might want to know the ID of the VPC, the VPC CIDR. Those things I could find, but by declaring them as explicit outputs, it puts a number of different values that would normally be spread across a lot of different areas. It puts them into one place, one central place that I can very easily find them. And then, of course, by exporting them, I can then leverage those within other templates, right? Other templates could then build on top of this template, right? So you don't have to write, all of your moving parts, all of the things that would go into an application, auto-scaling groups and load balancers, security groups, and DynamoDB tables, RDS instances, and so on. You don't have to put all of it in one CloudFormation template, and you shouldn't. It just becomes too much. And so by using things like exports, this is a way of helping us to break up our cloud, what might otherwise become a very large and unwieldy template, right? Okay, so let's go ahead, now that we've kind of explored what the code looks like, let's go to the CloudFormation console and watch this in action. We're going to say create a stack. And of course, we can use a sample template if we wanted to. We could upload this to S3 and then reference the S3 URL, or we could just upload it directly to the CloudFormation engine, right? So let's go ahead and do that. All right, so now I have my YAML file that I'm going to upload, and here we need a stack name. We need to name this collection of resources. Remember that a stack is a collection of all of the resources that we just saw, the VPC and the 4 subnets. and the outputs. And so this particular stack we could call fundamentals VPC. And then remember, it asks us, the template had declared one parameter, and this is where we get to enter that, the CIDR block for the VPC, and then the subnets will be derived from that. And so earlier we used 10.0, and then we also used 10.1. So here we could say 10.2.00/16. We'll go ahead and say next. And then of course we could tag. If we were to tag here, then these tags would be a part of the stack, and they would also be applied. Any tags that we put here are also applied to each resource, right? So I could say environment dev. And so you'll notice, if we go back to the template real quick, you'll notice that I do have tags, and I usually use this to for tags that are specific to that particular resource. And then for tags that I want to be common across all resources, I will put here, right? So here, all resources, I might put environment development or project or cost center or whatever. All right, and we could of course add more tags. We won't worry about that stuff. Now we can get notifications if we wanted to. Remember that as CloudFormation builds these resources out. And if it encounters an error, if it completes successfully, there are a number of events that go along the way, and we could subscribe to those, and we may want to do that in order to see a real-time output. Rather than having a team, log into the management console and sit there and look at that one screen waiting, they could have these kind of notifications through the simple notification service piped into something like Slack. So, you could continue working in your IDE on one screen, have Slack on another, and then, just glance over and see, event successfully created. So we'll go next, and we'll review that. Yes, single VPC with 2 public and 2 private subnets. There's the CIDR. There are my tags. All right, so let's go ahead and create that. And you'll see now create in progress. And we can always refresh there. We don't have to refresh the whole screen. And you can see it has started the creation of the VPC. Again, because CloudFormation inherently knows that the subnets depend on the VPC. In other cases, it might not know that. And in other cases, for example, if you had an EC2 instance and an RDS instance in the same template, there's nothing inherent about those two that says one comes before the other. So it would probably try to create them both at the same time. But you can control that. You can explicitly state, hey, this EC2 instance depends on my RDS instance, which means that you would want, you could force CloudFormation to build one thing before another. All right, so there we go, just like that. And very quickly, it created there are all of our subnets. It says create complete. And then the stack itself, fundamentals VPC, create complete. And so then if we go to stack info, create complete, let's go to events, and there are all of that. Let's go to resources. There we go. And now we can see here is the physical ID. If we were to click on that, this would take us to VPC, right? So let's go ahead and do that, and then that will take us to the VPC console dashboard. And now we can see the details about that VPC. And so if you recall from the earlier demo, there was a lot more work involved to essentially do the same thing, right? To create a VPC and then create subnets, it took us click by click, screen by screen, typing things in. And even in that regard, we only created 2 subnets. And so here with CloudFormation, we created a VPC with 4 subnets in a fraction of the time. And now they're all managed underneath this one stack. And so if I decide at some point, if this were a temporary environment, if I decide that I don't need it anymore, then all I have to do is say delete stack. Or if I wanted to make a change, if I decided, you know what, I want to add 2 more subnets, 1 more public and 1 more private, then I could make that change in my code, come back here and update the stack. You can also see the outputs. So this is that one place where I said, you know, there may be certain pieces of information that we want centralized in one place. And so here's all that information, but you can also see that it's being exported, which means that because it's exported, we can then use this value, we can use these values to import into another stack, and allows us to help organize stacks so that we're not putting, like I mentioned earlier, we're not putting a whole bunch of resources in one stack, all right? And then we can also see the template here. You can see the parameters that were used for this. And then, of course, because this is a generalized template, I could launch it again and use 10.3, 10.4, and so on, and create the same kind of infrastructure over and over again, but with different values. If I wanted to duplicate this whole thing in another region, I can do that very easily, right? So again, the takeaway from this is that the only way to truly realize all of the benefits of AWS, the cost, not just the cost savings, but the agility, the flexibility, the efficiency, the only way to realize that is through automation, right? So again, we did things manually in earlier demos to prove and concepts and try to understand concepts about those services, but this is where the real power is. Automation. And again, it doesn't have to be CloudFormation, right? So again, I would encourage you to really explore the world, not just AWS, but automating it through tools like CloudFormation or third-party tools like Terraform, Ansible, and so on.
Now let's talk about inventory and change tracking with AWS Config. So AWS Config is a service that continuously monitors and allows us to audit our current resource configuration. So as we've seen so far through this course, we've seen a number of diagrams that illustrate a number of different resources that are configured in different ways. And so we may have EC2 instances and security groups, VPCs and firewalls and load balancers and S3 buckets. The list goes on. We could have all kinds of different resources. And if that configuration changes, it could lead to downtime. Even small changes could lead to big consequences. And so small changes could lead to security incidents and so on. I know this because I speak from experience. I've seen it happen. I've seen what seems like a small security group change bring production down. And so with AWS Config, we get the ability to continuously monitor and assess the compliance with particular policies. So we could write rules and say that our resources should look a particular way, that this configuration should exist in a particular state. So just for example, we could say that if we have security groups, then security groups should have either a certain set of rules or they should not have a certain set of rules. And so if AWS Config finds that a security group has rules or doesn't have rules, if it finds that a security group is out of compliance with our policy, then it could trigger some kind of an alert, and we can use that alert to either inform us or take some type of programmatic automated response. And so another thing that AWS Config does is it will also provide us with an inventory of all of our resources, including software that's installed on our EC2 instances, so that we can monitor the configuration not only of physical or virtual resources within AWS, but also the software that's installed and running. AWS Config will also give us a complete history of configuration changes so that we can use that for change management, for compliance auditing, and show exactly the different states that our resources and our environments went through during their evolution. And so if we see that a change was made that has now violated some kind of security policy, we could go back to the history and very easily roll back to a previous configuration. And so AWS Config, again, as I mentioned, allows compliance auditing, it allows security analysis, and it also enables change tracking and even troubleshooting. So again, I speak from experience. Looking back some years ago, before AWS Config was an offering, I had a situation where I had a particular security group that existed on EC2 instances. And I saw a particular rule in there, and I remember thinking, how did that get there? That doesn't make any sense. And so I thought, well, that rule shouldn't be there. That doesn't match a pattern that I've used in other places. And so I removed the rule. And then about a minute later, I start getting alarms because production was down. Just making that what seemed like one small change ended up removing the ability for my load balancer to communicate with backend instances, and as a result, my users were no longer able to reach their application. And so in that regard, had I been using config, I could have gone to config and it would have shown me, right then and there, it would have shown me exactly the thing that was out of place. It would have shown me I could have looked to the previous configuration and very easily gone back to that. Even before troubleshooting to figure out what exactly the problem was, I could have just rolled back to a previous configuration and fixed the issue and debugged it later. So taking a look at this diagram, you can see here in a particular region, we may have a number of moving parts, right? We have a VPC that would have subnets, and it has routing rules that allows traffic to route between the internet and between different VPCs or back to on-premises over VPNs. We have different security controls around, we might have firewalls around our subnets. We would have, which are called network access control lists. We would have security groups around our EC2 instances. We have, S3 buckets with different policies applied to them. We would have security groups around our load balancer. So we have all these moving parts that exist in a particular configuration. And we want a way to monitor our resources and to inform us when that configuration changes. And some of those changes may be intentional, but what we really want to look for are unintentional or malicious changes to our environment, changes that would either cause downtime or cause some kind of security issue like exposing access to sensitive data. And so by using the AWS config service, there are no servers for us to put in place and manage and run. We configure the service by creating rules. And we set up rules to say security groups should look a certain way. Network access control lists should look a certain way. Routing tables should contain or not contain certain rules. S3 buckets should contain or not contain certain policies. And then the AWS config service will, again, automatically, continuously, this is not something that happens once a day, this is a continuous monitoring of all of our resources for which we have rules defined, and so config is looking at our resources, and when it finds something that is violating those rules, it can send notifications out through a simple notification service topic. And from there, we can either leverage Lambda, something like Lambda, to automatically, programmatically respond to that incident, perhaps automatically undo that change, or we could also send that notification into other systems like a ticketing system, a SIM, or a chat, something like Slack, for example, so that an entire team is made aware of this particular issue. And what the level of severity is would be up to us. Some things may be more severe than others. And so as you can see here,
monitoring our infrastructure becomes much more than just collecting, metrics. Of course, we're collecting metrics into CloudWatch, and we can create metric alarms, but monitoring is more than that. Monitoring is also monitoring the state of our infrastructure. So for those of us who are looking to build systems within AWS, it is likely that those systems will use a number of different resources. And if you want to ensure a secure, continuous operation of those resources, then by all means, take a look at AWS config. Now let's review an introduction to AWS Systems Manager. With AWS Systems Manager, we can very easily automate maintenance and deployment tasks such as patches, operating system updates, even code deployments, configuration changes, and so on. And so another nice feature of System Manager is that it gives us the Insight dashboard, which is sort of a single view into operational data that we would normally find in a number of disparate places. So if we weren't using Systems Manager and we wanted to gain operational data about our various resources, we would have to go, if we're using the console, then that would require us to move from service to service, screen by screen, click by click, trying to gather and collate this data on our own. Whereas with Systems Manager, using the Insight dashboard, it will automatically centralize a lot of information from a lot of different places for us. We can use Systems Manager to manage both EC2 instances and on-premises servers. So it's very useful, especially for hybrid environments. Everything that we do with Systems Manager, as we use Systems Manager to make changes to running instances, all of those actions are recorded to CloudTrail. Now, Systems Manager does include a number of features, and I just want to point out what I think are some of the highlights. So we have a number of features that we will take a closer look at, such as Run Command, Session Manager, Patch Manager, and State Manager. And of course, there are more, but these are the four that I thought were important to talk about here. So let's take a closer look at those. With Run Command, we have the ability to gain secure remote management without the need to actually log into servers. You can imagine that if you have to open port 22 and allow people to shell, if you have to open 3389 and allow people to access Windows remotely, then now you have a wider surface attack area. If you can close that, you can remove security issues, right? So Run Command allows us to execute commands without having to enable any kind of remote access. And so we can also, another nice thing is that now we don't have to leverage a completely different realm of authentication to control access. If we're gaining remote access in a traditional way, then we would have to control access in some separate realm within the operating system realm. But by using something like Run Command, we can control user actions through the Identity and Access Management Service. And, of course, we can also log those things through CloudTrail. And so we can use Run Command to do a number of different things. We can install software, we could execute different types of scripts, we could update configurations, we could restart processes, and we can do any of that with Bash, with PowerShell, with Ansible, just about any binary that exists on the system. With Session Manager gives us a browser-based CLI access to both Linux and Windows instances. So again, very much like Run Command, there's no need to open ports, no need to manage SSH keys, for example. We can get some type of an interactive terminal right there in the browser. And so the difference between Session Manager and Run Command is that with Run Command, we define a document, and such as an Ansible playbook, for example, or a CLI script.
We give that to run command then ensures that that gets executed on the machines. But with Session Manager, we have the ability to gain direct access to the shell that we can then type a command into manually if we need to. And again, we can do that without opening ports, without the need for SSH keys. And we can, very much like all the other systems manager services, we can control access through the identity and access management service. Now, with Patch Manager, we can use Patch Manager to deploy patches across very large groups of Windows-based instances. And so these patches could be operating system patches, they could be application patches, or some type of dependent library patch. And we can create patch baselines, and we can use those to define sets of patches that are approved for deployment. So Patch Manager does leverage run command, and so by leveraging run command, you can customize the deployment. So you can take that run command document and say that perhaps you want to stop a particular process before the patch is actually deployed. So you do have the ability to customize that deployment. Now, with Parameter Store, as the name suggests, we gain access to a secure, centralized parameter store. And we could use that to store configuration of our applications, such as connection endpoints, application settings, feature flags. We could use the Parameter Store to turn different features of our application on and off. We could also use it to store passwords, right? So the Parameter Store does support secure information by integrating with the key management service. So it can store such things as passwords. If we opt into a secret type of data, then Parameter Store can leverage keys with the key management service to encrypt those passwords with AES 256. So you can see that with AWS Systems Manager, we have a very rich set of tools to help manage our existing EC2 or on-premises servers. And so you can think of Systems Manager as sort of a comprehensive configuration management. So if you have a number of instances, whether they be Linux or Windows, and you want the ability to automate the patching, the updating, installation, and ongoing configuration management of those instances without the need to open remote access, then take a look at AWS Systems Manager. Now let's review optimizing usage with AWS Trusted Advisor. So AWS Trusted Advisor is an automated tool that regularly automatically analyzes your environment and compares what you're doing and the state of your infrastructure to best practices. And then it can advise you, based on those best practice recommendations, it can advise you to ways that we can improve cost optimization. It will recommend ways to save money, recommend ways to improve performance. It can recommend ways to improve security, and also recommend ways to improve fault tolerance. So, for example, it might look to see that you have certain security group ports that are open that are known to be insecure, and it might recommend that you close those ports. It might see that you've been running a particular EC2 instance using the on-demand billing model for an extended period of time, and it might recommend that you could save money by switching to or purchasing a reserved instance. It might see that you are running, let's say, one EC2 instance behind a load balancer, and in which case you don't have any fault tolerance. It might notice that you're running an RDS instance in a single AZ rather than multi-AZ deployment, which could improve fault tolerance. And so everyone, no matter what level of support you are paying for, everyone gains access to 7 core checks. And those core checks are, one, looking at your S3 bucket permissions. This is an area in particular where over the years a number of organizations have kind of gotten themselves in trouble by making sensitive information available to the public. And I think in those cases it's just a matter of a combination of a lack of education and a lack of communication. And so one of the things that the trusted advisor can do is take a look at your S3 bucket permissions and inform you that certain buckets may be making certain data publicly available. Another thing that the trusted advisor will do is, like I mentioned earlier, looking at your security groups and taking note of certain ports that are left unrestricted. For example, it would probably be a security issue if you were opening port 22 to everywhere, right? Ideally, to have more security around that, you would probably want to open port 22 from a small trusted range of IP addresses, like a VPN connection, for example. Another one of the checks would be your use of IAM. It can look through the policies that you are giving to your users, to your groups and roles, and tell you that perhaps you are giving more permissions than are necessary for that particular use case. It will also look to see if you have enabled multi-factor authentication on the root account. Remember that if you are logging into the console with an email address, then you are logging into the root account. And that root account, we call it the root account because it has essentially root permissions or administrator permissions, and you cannot limit those. So if someone were to gain access to those root credentials, they could really do some damage. In fact, companies have gone out of business. And so it's really important that we take every measure we can to protect those root account credentials, including configuring MFA for the root account. And again, one of those checks of the trusted advisor is to inform you as to whether or not you have done that. Trusted advisor can also look at your EBS volumes and look at the snapshots that you've created and inform you whether or not you have made any of those publicly available, right? So very similar to S3, it could be, it's relatively trivial to make EBS snapshots publicly available to anyone. And so that is something that we certainly would not want to do if that snapshot contained any kind of sensitive data. And the same thing applies to RDS snapshots, right? We could make RDS snapshots publicly available, but only if they didn't include sensitive data, right? So that's one of the 7 core checks. It will also take a look at service limits. So remember, we've mentioned this a number of times before throughout the course that AWS does impose service limits. There are hard limits and soft limits. And so, for example, one of those soft limits, the initial default limit for EC2 instances is 20 instances. Now, in order to go above that, you would have to submit a ticket to Amazon support asking for an increase in that. And there are a number of soft limits like that that can be increased. And so one of the things that Trusted Advisor will do here is look through your account and inform you that you are getting close to that limit. If you have, let's say, a limit of 20 EC2 instances, and now you are at, let's say, 15, 16 instances or so, then the Trusted Advisor can warn you that you are approaching that limit so that you can increase that limit before you have the need, right? Which, and I've been there before. It's not a fun position to be in when you need more than what you're allowed to create, but you're stuck waiting on Amazon to answer your support ticket. So those are the kinds of things that you want to get out ahead of. Now, all of these 7 core checks are available to everyone. If you are paying for business level or enterprise level support, then you gain the full benefits of Trusted Advisor, which includes more than 40 different checks across many different resources and many different types of things going on in your Amazon environment. Again, all of it categorized according to cost savings, security, performance, and fault tolerance. And then you also get the ability to receive notifications. As the trusted advisor finds things, it can notify you, and you gain programmatic access to the trusted advisor. Again, these two things, the full set of 40+ checks and notifications and programmatic access, are only available to those of us who are paying for business level or enterprise level support. If you have basic support, which is included, or you're paying for developer support, then you only gain access to those 7 core checks. And so the trusted advisor, again, is an automated tool that regularly scans your environment and recommends things that you can do to improve that environment. And so it's a good idea when you're using AWS to regularly check with the trusted advisor. Every so often, every day or every other day at least, go to the trusted advisor and see what it has to say. If you see something new, listen to it. Take its word and go and explore ways to mitigate that issue that it is showing you.
Operations and security are certainly not the only teams to benefit from the increased flexibility and agility offered by AWS. Developers also have plenty of tools to use to increase their collaboration, efficiency, and productivity within the software development lifecycle. In this lesson, we will review a number of services related to coding, version control, deployments, and debugging.
Now let's talk about writing code with AWS Cloud 9. With AWS Cloud 9, we gain access to a web-based IDE, which allows us to write code in our browsers. So the beautiful thing about this is that we don't need any special software running locally. We can get access to a very powerful, very beautiful IDE, complete with syntax highlighting and all kinds of other really useful tools right through our browser. And so if we need to switch from one computer to another, we know that we can pick up exactly where we left off, not only with the same IDE, but exactly in the same code, in the same environment. And so Cloud 9 includes an editor, a debugger, a terminal, as well as collaboration tools. So we can access Git repositories. There's a built-in chat system, so that if an entire team is using the Cloud 9 IDE, we can chat with one another, and we can also share our development environments with the entire team. We can also enable remote pair programming. This is a very powerful feature, and a number of development shops rely on pair programming, but as more and more developers start working remotely, then Cloud 9 enables us to pair program remotely, where you have 2 or more developers looking at the same exact code, watching each other make changes without having to first, upload to some kind of remote repository. And so again, with AWS Cloud 9, some of the other features that we have is that it does come pre-configured for serverless development, such as developing for Lambda, complete with SDKs, libraries, plugins. We can also run these development environments, these Cloud 9 environments. They can be run on a managed EC2 instance. So when you go to the Cloud 9 dashboard within the web console, the AWS console, and you create a Cloud 9 IDE environment, you have your choice of running that on an EC2 instance that's essentially managed by Cloud 9, or you could also run that on essentially any Linux-based server, including those on premises. And there is no charge for Cloud 9 itself. So Cloud 9 itself is free. What we pay for would be for, if we were to run this on EC2, we would pay for that, and we would pay for any storage that is used as a result, right? So if we end up storing our code on an EBS volume, then we would pay for that, right? Another nice feature that Cloud 9 provides is a 30-minute auto hibernation. So if you are, if you're in the IDE and you're writing code, but then you need to take a phone call, you need to step to a meeting, go out to lunch, and if you are inactive for 30 minutes, it can automatically put that EC2 instance in a stopped state, allowing you to save money by so that you aren't running the EC2 instance when Cloud9 is not being used. So if you have the need to enable things like remote pair programming, if you want the convenience of a web-based IDE that you can access from any computer at any time, then take a look at AWS Cloud9. Now let's talk about source control with AWS CodeCommit. Now AWS CodeCommit gives us fully managed private Git repositories. This is essentially Amazon's answer to GitHub, right? So if you are using Git and you want something like GitHub but that is more natively integrated with AWS, then a CodeCommit may very well be the answer. And it also works just like GitHub does. It works seamlessly with existing Git tools, right? So if you're using Git on the command line, if you're using other GUIs, such as Tower or other kinds of Git tools, then those will continue to work. The nice thing about CodeCommit as a managed service, instead of running Git on EC2, for example, with CodeCommit, like other Amazon managed services, it is inherently scalable and redundant. The underlying infrastructure and storage is all managed by AWS, right? So we know that when we commit our code to CodeCommit, that there are multiple copies of that code stored in the background, right? So it's, like I say, it's inherently redundant and durable, and access to that is highly scalable. It also integrates very easily with native AWS services, as we will talk more about, such as Code Pipeline, like we saw with Cloud9, and other Amazon services. So CodeCommit also supports, just like GitHub and other Git tools, it supports access over HTTPS as well as SSH. It also supports pull requests. And pull requests, for those of us who have used it, you will know that pull request is a powerful feature that allows a team to do code reviews, so that perhaps one member of a team is doing that code review and suggesting changes be made to that branch before it's actually merged into, development or master or whatever branch you happen to be, be the line of development. And so it also supports post-receive hooks. This is another powerful feature of Git, so that as you do push to that remote repository, or as you, accept pull requests and those are merged into, say, development or master, we could rely on those post-receive hooks to trigger other programmatic automated responses, such as Code Pipeline, allowing us to commit to CodeCommit, and then the act of doing that then kicks off automated testing, automated builds, and automated deployments. So again, if you are currently using Git, if you're using something like GitHub or another Git-based service, but you want it to be more integrated into AWS, then take a look at AWS CodeCommit, and keep in mind that a common pattern is to leverage multiple repositories at multiple services. It could be that your team in general uses something like GitHub, but then in order to get something into production, the process may be that you have a person or an automated system may very well pull it from GitHub and then push that to CodeCommit, which then kicks off a deployment to production. So we will take a closer look at AWS CodeCommit and more details in the upcoming demo.
All right, let's take a look at a demo of working with AWS CodeCommit.
All right, so let's go to CodeCommit. We can type that there, click on CodeCommit. And you'll see we have very quick access to a lot of other related developer tools like code build and code deploy, code pipeline. So we can go ahead and shrink that. You can see in this particular region, we don't have any repositories yet. So let's go ahead and create one. And here, let's just say that we have, you know, a microservice, and it's called the users. All right, so let's just call it the users service. And we'll say here, this is the users service. And we'll go ahead and create that. And now we have a Git repository within AWS. And so we can connect to it through HTTPS. We can connect over SSH, right? And it gives us instructions on how to do that for different operating systems. I would say that HTTPS is probably the easiest. You don't have to worry about having keys. And so the one thing that we need to be aware of with CodeCommit is that before we can use it, before we can actually either clone the repository or initialize one locally and then push to this remote, we have to have users. And so you'll see here it says generate Git credentials, right? So the credentials that we would use for CodeCommit are a little bit different than what we use to log into the console. So if we go back to IAM, here I have that open in another tab. Let's switch to IAM. And so I can get there from, you'll see here that I'm logged in as an IAM user. And that user and password logs me into the AWS Management Console. It will not get me into Git. So this particular repository has its own sort of realm of authentication apart from the AWS console or API. So I can go to, if I open this and go to my security credentials, let me open that in a new tab, and I'll show you that, you know, earlier we saw how we could, you know, manage passwords, manage access keys. We can also go to CodeCommit credentials. So CodeCommit has its own special section here within IAM that allows us to either use SSH keys, and you can see that I do have one. So for some repositories, I'm using an SSH keys. For others, it actually may very well be easier to use HTTPS, because what I found is that like recently I got a new computer and my private key somehow did not, I guess it may have been hidden or in a folder that I forgot, but it didn't get copied over to my new computer. And so now I had the effort of creating a new one and then, you know, importing a new one here. Whereas with HTTPS, it's just a username and a password, and that the encryption is handled by HTTPS rather than my SSH key. So had I used HTTPS, you know, for previous repositories, then that username and password would have come along with my password manager. So that's what I see the benefit of HTTPS is if you need to go and, you know, switch to a new computer where you might not have an SSH key present, you could still have your username and password, right? So we can go ahead and generate Git credentials, and you'll see here that it generates it for us, and I can say, I can go ahead and either copy these or download these. So I'm going to go ahead and download those, and we'll open that with Atom. And then if we see that, there's our username here and our password, right? So I'm going to come back to that. So now let's go back to, we can close that. Let's go back to CodeCommit, and we can find here is the repository URL. I'm not going to clone it because there's really nothing in there. It's an empty repository. What I'm going to do, I already have code. I'm going to copy that and come back to my terminal. And I have some code here in here. You can see I have a little bit of code. I have a Node.js. If I were to vim that, I'll show you. I have just a simple Node.js application here, and not a whole lot going on, but it is code, and it's the very, you know, the very basis of what could become, you know, a full-on service to help manage users, you know, within a collection of microservices. We also have the package JSON. We have a Docker file, and then, you know, later on we would of course be adding more code to this. Okay, so now we will say git init dot, meaning to initialize a new Git repository locally, and before we can add, well, we don't necessarily have to, but what I like to do is go ahead and add the remote. Before we actually commit our code, let's go ahead and add the remote. We'll say git remote add, and I like to name it, I don't really like the word origin. A lot of people will name things, you know, origin, but I like to use, you know, where it is, AWS CodeCommit, because I could have another origin for GitHub or Bitbucket and so on. And so I'm going to say AWS CC, which is the name of that remote, and then I will paste in that URL that we copied, return that. Now I'm going to stage all of my work. I'm going to commit it with a message saying this is the initial import of my code. And now you can see that that X is gone. I don't have any if I say git status, then you know, nothing to commit, but I do have things to push, right? So now I can say git push master AWS CC. Whoops, I had it's the other way around. And now I need the username, so let's go back to that. We'll go ahead and copy the username, paste that, and there we go. We've now pushed code to CodeCommit, and if we come back to the AWS console, we scroll up here, we can shrink that, go back to users, let it refresh, go back here, and now we're seeing code in our repository, right? So again, a very, very, very useful service, especially if you want to keep things completely contained within AWS. Nothing at all wrong with using GitHub. But you know, if you want to keep things perfectly contained, where everything, you know, that everything is within AWS, then CodeCommit is very useful in that regard. It's also useful, you know, even if you use both. I have seen that pattern where, you know, I've seen teams use, you know, this basically the same repository in both GitHub and CodeCommit. In the pattern there that I've seen is where a team might use, you know, the great majority of the team, everyone is pushing code to GitHub, for example, and then say a team lead or a senior member is then, once that code is ready for production, they then push it, you know, very fewer people would have access to the Amazon side. Then they would push it to CodeCommit, which would then kick off things like, you know, code pipeline, code build, and other things. Right? So I would encourage you to continue to look at all of these kinds of automation tools, CodeCommit, code pipeline, CloudFormation. The combination of these things are really, really powerful. And remember, like I said earlier, you know, the only way to truly realize the power of AWS is to leverage automation. And so even you know, you don't have to put you know, applications here in CodeCommit. You could put in your CloudFormation templates, and then by merging or pushing your CloudFormation templates here to CodeCommit, that could kick off code pipeline, which then triggers the CloudFormation engine. All kinds of possibilities, and I would highly encourage you to continue to explore this world of automation.
Now let's talk about continuous integration and continuous delivery with AWS Code Pipeline. AWS Code Pipeline gives us a fully managed continuous delivery service. And so we can use this to help automate testing and building and deploying our code to various places. And so it's important to keep in mind that Code Pipeline itself will not do the tests. Code Pipeline does not build, and it doesn't actually do the deployment. It simply helps coordinate the process of getting code from a repository to something that is doing the test, something that is building, and something that is deploying. So it could be that we have code in CodeCommit or code in S3. We could have code over in GitHub. Code can be in a number of places to begin with. And then Code Pipeline can pull that code from that source and then pass it on to something that is doing the testing in the building. That something could be Jenkins, it could be code build, it could be Lambda. And then from there, once we have an artifact, that artifact could be stored in a number of different places. We could store artifacts in S3. We could store artifacts in the Elastic Container Registry if we're deploying images or containers. And then once that artifact is stored somewhere, Code Pipeline, again, won't do the actual deployment, but it can trigger a service to do the deployment, such as Code Deploy or ECS or so on. And so Code Pipeline integrates with a number of native services, including GitHub, including AWS CodeCommit, Code Build, S3, and Code Deploy, among others. Also Amazon ECS. So again, if we are deploying traditional code to EC2, we might use Code Deploy. If we are deploying containers to ECS or Kubernetes, then we could potentially use Code Pipeline. Now, Code Pipeline can also very easily integrate with third-party tools. Again, I mentioned Jenkins, but we could also integrate with things like Ghost Inspector or RunScope. So if once code is deployed and we want to run more functional or integrative testing against code that's running in some kind of dev or testing environment, then we can use Code Pipeline to initiate those third-party tools to start their tests against that code that's currently running. There are a number of pre-built plugins available, so there are Jenkins plugins for Code Pipeline. Now, the process for Code Pipeline is highly customizable, right? You could have every single application. One of the patterns here is that typically every application has its own pipeline, and you can customize the flow of code and artifacts and processes through that pipeline for each application. And so it could be that some applications do, very simple steps along the way that are all serial. It could be that some applications need numerous steps, and some of them could run in parallel, right? So Code Pipeline supports both serial and parallel operations. And so we can define these pipelines with JSON, and that's another beautiful thing that's related to infrastructure as code. So we can essentially code the pipeline. So it could be that every application includes its own pipeline in its own code base. And we can also apply access controls to Code Pipeline with the identity and access management. And so we can use IAM and the policies that we apply to our users, our groups, and our roles. We can use those to control who has access to Code Pipeline, right? So remember that a key component of continuous integration and continuous delivery is DevSecOps, where you are ensuring that the process of getting code from source to production, that you want to ensure that that process cannot be modified, that the wrong people don't have access to that process, right? And so with Code Pipeline, we as a customer, we get to define the stages of that pipeline. And the stages could be, there's a source stage where code comes from to begin with. There's perhaps a building stage, a testing stage, and a deployment stage, right? And again, like I mentioned before, Code Pipeline does support both serial and parallel operations. It also supports manual approvals, right? So it could be that somewhere along the way during that deployment, perhaps before deploying to production, in order to satisfy change management, maybe you need some kind of paper trail, and maybe you need someone to press a button so that you can satisfy change management, to say, yes, a human approved this particular step, right? So Code Pipeline can be coded and configured to wait on a manual approval. So if you are currently using some type of a pipeline, such as Jenkins pipelines, or maybe you have explored Jenkins pipelines but aren't quite there yet, perhaps you want to take a look at AWS Code Pipeline for performing continuous integration and continuous delivery within AWS. Now let's talk about serverless builds with AWS Code Build. With AWS Code Build, we gain access to a fully managed continuous integration service where we have the ability with Code Build to run tests, to compile source code, to produce artifacts and packages, to actually do the work of testing and building and creating artifacts that will then be deployed, right? And so the nice thing about Code Build, again, being a serverless continuous integration service, is that there is no need to provision or manage our own servers. So just like with Lambda, we write code and we give code to the Lambda service and it just executes it. The same thing with Code Build. We configure Code Build to perform certain actions related to testing and building, and there's no server for us to manage. We simply configure Code Build to do it. And so with Code Build, as we need to build more things, as we need to run more tests, then Code Build will automatically continuously scale. If we have, 2 concurrent tests and builds going on, or 200 concurrent tests and builds happening, Code Build will continuously and automatically scale to accommodate that, right? So like I said, you can process multiple builds concurrently without having to worry about the static nature of limited servers. So back in traditional IT, there's plenty of stories where many organizations were stuck with one build server, and development teams were essentially in line, waiting in line for their builds to happen. And I've heard other stories of organizations being stuck with 1 or 2 test servers, and development teams waiting many hours for their builds to finish, and then waiting hours for their tests to finish. But with Code Build, we don't have those kinds of limitations. Different teams can simply execute their builds independently without having to wait on one another. Now, Code Build does support prepackaged and custom build environments. There are plenty of prepackaged environments, such as different types of Linux environments, Windows environments, and then of course you can create your own custom build environments if you have something very particular that is specific to your application. Now, with Code Build being a serverless environment, very similar to Lambda, where we pay for, per 100 milliseconds, with Code Build, we pay by the minute. And so if we are running build servers, for example, on EC2, then there will come a time when we are paying for idle time, where we are paying for a machine that is running but not actually building anything, unless we take steps to turn that machine off. But with Code Build, we know that the money that we spend on it is being spent on work that is actually done, on builds that are actually being performed, right? And so, again, we pay some fee per minute for the compute that is actually used. There are different build environments, different sizes according to the memory and CPU usage that we need. And the more CPU, the more memory that we use, the more we pay per minute. Now, there are also Jenkins plugins available. So a common pattern that I've seen is where you may use Jenkins to coordinate the job of testing and coordinate the pipeline of getting code from source to its running environment. And one common pattern is where Jenkins does everything, right? Another pattern is where Jenkins offloads the work to slaves. And maybe you have, I've seen organizations that may have, maybe several dozen slaves that it can send those actual test and build jobs to. And so with Code Build, using the Jenkins plugin, you could replace all of those Jenkins slaves with the Code Build service. So instead of being limited to a fixed set of servers, now you're unlimited. Now Jenkins can simply send its tests and its builds to code build as it needs to. And again, code build will continuously scale to support that. So if you are looking for a way to, if you are currently limited in your ability to build and test, then perhaps you want to take a look at AWS Code Build as a way to gain access to continuously scaling serverless environments for running tests and building your packages and creating artifacts. Now let's talk about deployments with AWS Code Deploy. With AWS Code Deploy, we have a fully managed deployment service. So Code Deploy helps us get our final artifact, whatever it is that has been built, to its running environment, be it dev or test or staged, production, you name it, or even across multiple regions if we're running production to a larger, more global audience. And so with Code Deploy, we can deploy our finished code, our artifacts, to Lambda, to EC2. We could also deploy artifacts to on-premises as well. Now, of course, it does require an agent. If you wanted to deploy Code Deploy to EC2 or on-premises, then you would have to ensure that the Code Deploy agent is installed. Now, one of the nice things about Code Deploy is that it eliminates the manual operations of getting that artifact deployed and running in that environment. And as we can imagine, humans, we're fallible creatures, right? We make mistakes. And sometimes you can imagine that, deploying code to production when, many thousands or potentially millions of users are using it, and you can imagine how stressful that would be. And I'm sure that many of us have been in those situations where we are manually deploying code to production. And so we can eliminate that stress. We can eliminate the potential for human error by leveraging something like Code Deploy. And of course, it also supports thousands of EC2 instances. If you have very large fleets of web applications or other types of enterprise applications to which you need to deploy your final artifact, then Code Deploy can support that, right? So if you are currently leveraging some type of a manual deployment, or perhaps you aren't happy with the deployment process that you have, and you want something that's inherently, integrated within AWS, then take a look at AWS Code Deploy. Now let's talk about debugging with AWS X-Ray. AWS X-Ray is a service that allows us or helps us to analyze and debug distributed applications. And not just distributed applications, almost any application, but it's especially useful for microservices, where you have requests coming in to one service and which calls another, and then the response goes back out. And so without something like X-Ray, if you wanted to try to debug an issue that was happening somewhere along that chain of services, then you would need to look in all of these various places. And in that regard, the challenge is that these different applications could be using different log formats. Some may be logging more information than others, but still it would be up to you to pull information from all of these different sources and put it together and try to make sense out of it. But with X-Ray, we gain the ability to do this with one tool in one place. And so we can use X-Ray to gain insights into performance, to help identify root cause of different issues. And so X-Ray is very similar to something like New Relic APM, if you're familiar with that tool, where what you're looking for is you want to see a request go all the way through the chain of events and then the response go back out. And you want to be able to trace that request through the entire application. And then you want to understand, which functions, which different calls are, perhaps contributing to latency Perhaps there are certain functions that are adding more time to the overall latency than others. And you can then use X-ray to help you focus in on those functions and drill down and determine what is it about that function that's making it take so much longer than we thought, or so much longer than other functions. And so with X-ray, we also have the ability to create service maps that help us to understand the relationships between different services and different resources and our functions of our application in real time as they are happening. Currently, AWS X-ray supports Java, Node.js, and .NET, and applications that are deployed just about anywhere within AWS, such as EC2, the Elastic Container Service, and Lambda. So for those of us who are looking to build new applications within AWS or migrate existing applications, especially microservices, and you want a very powerful way of helping you to analyze and debug performance issues and errors within that application, then by all means take a look at AWS X-ray.
Okay, so we have our developers, and they're writing code on their local machines, and they want to get that code from their local environments to some environment, whether it be dev or production, somewhere else, whether those applications are running on EC2 or as Lambda functions or as containers within ECS. They could very well be running on premises as well. And so we might first start by, the developer pushing or merging into a branch within AWS CodeCommit. So remember that CodeCommit gives us private Git repositories. And the very act of doing that could trigger the initiation of a pipeline. And so with code pipeline, we simply specify, the source. Where does our code come from to begin with? In this example, it's CodeCommit, but it could very well be S3 as well. And then, of course, we get to define the different stages. And so we might have testing stages, build stages, and of course, we would have deployment stages. And so with code pipeline and within CI/CD options, we have the ability to use code build to perform our testing and our building. We could also do that with Lambda. If we wanted to do something that perhaps was outside of the scope of code build, then we might use Lambda to do that. Or we could also use Jenkins. And so the nice thing about code pipeline is that it's very flexible. It gives us a lot of options. It doesn't enforce any kind of particular model. And there are also plugins available that make using Jenkins with code pipeline and code build very easy, as well as code deploy and CloudFormation. And so with Jenkins, it could be that code pipeline initiates the pipeline by pulling code in from CodeCommit and then passing it on to whatever is performing the testing or the building. And it could be that Jenkins is performing that, but it's passing off the actual processing of a build or a test to code build, right? So you can see there's a lot of different ways that we could arrange this. So again, there are plugins that allow Jenkins to use code build as its build slaves. And you don't have to do that. You have complete freedom and flexibility to arrange this however you want. And then, of course, once our tests and our builds have passed, once our artifact has been built, then of course that artifact needs to be stored somewhere, and it could very easily be stored in S3. If our artifact is a jar file, a war, or an ear file, if it's a zip file, then we might put it in S3. If our artifact, if what we're deploying is a Docker image, then the image would be published to Amazon ECR, the Elastic Container Registry, which is a sibling service to ECS. And then, of course, in our deployment stage, we also have plenty of options. We could use code deploy. If we're deploying to EC2 or on-premises servers, then we could very easily use code deploy. If we're deploying to Lambda or ECS, then we could see a lot of flexibility and power in using CloudFormation to perform the actual deployment or the updating of an existing CloudFormation stack. And then along the way, as code pipeline initiates, as tests pass and fail, as builds, fail and succeed, as deployments fail and succeed, all of these things are going through a number of different lifecycle events, and all of those events give us information. And we want to collect that information, and we can very easily do that by leveraging Amazon SNS, the simple notification service. And by leveraging SNS, we can channel all of those events and all of that information into, for example, Slack. And that's a really powerful option in allowing a team of developers working. In my experience, teams of developers are often looking at two things. They're looking at their IDE, perhaps on one screen, and they have their Slack channels open on another screen. And so by collecting this information and putting it right in front of the developer, then they can get pretty much real-time insight into exactly what's happening throughout the lifecycle of this pipeline. And if a test fails, the developers are aware of that immediately. They can make changes, commit, remerge, and try it again. And if it passes, they see that. If the build fails, they see that, and they can, again, make changes and try it again. And so a pipeline like this with the ability to receive these notifications, get that information in front of the developer, really allows us to create continuous integration and continuous delivery in a very, very efficient way. And as you can see, it's very flexible as well. We have a lot of options in how we put this together. And we may even have other options here. It could be that third-party tools like Travis CI, Circle CI, they may have plugins that work with code build as well, right? So when it comes to continuous integration and continuous delivery, I would highly recommend that you take a look at what's possible between the combinations of CodeCommit, Code Pipeline, Code Build, Jenkins, CloudFormation, Code Deploy, and all of the other Amazon services.
If you've been in IT or software development long enough, you'll probably recognize some fundamental building blocks that many applications leverage, such as message queuing, sending emails and notifications. In this lesson, we will explore these tools offered by AWS, along with other exciting technologies that ease the development of mobile applications.
Now let's review Amazon Simple Queue Service, or SQS. With Amazon Simple Queue Service, we gain a fully managed queue service. And so there's no instance of any kind of server that we need to provision. Nothing is sitting there idle that we're paying for. There's no software to install. We simply go to the Simple Queue Service and create a queue. And then all of the underlying infrastructure necessary to maintain that queue, including high availability, fault tolerance, durability of messages, is all handled by AWS. And so the system itself scales automatically. With the standard queue, we can scale almost limitlessly. And we can control authorization using the identity and access management specifically for users, groups, or roles. We can also use a resource policy, so we can control usage of the queue at the queue itself. And by doing that, we could use a resource policy to share that queue with another account, being it an account that we own or an account owned by a third party. We could also share the queue to anonymous users if we needed to. SQS also supports server-side encryption. So if you are dealing with messages and data such as personally identifiable information or protected health information, then we can leverage server-side encryption using AES 256 to ensure that those messages are encrypted at rest. Now, with the Simple Queue Service, we have two different types of queues. we have a standard queue and a FIFO queue. With the standard queue, keep in mind that the order is not guaranteed, and it does make a best effort. It makes a best effort to deliver it in order, but it's not guaranteed. It's also an at least once delivery model, meaning that a message, it's possible for a message to be delivered more than once. And so your application would be responsible for any kind of either deduplication or ensuring that your operations are idempotent, meaning that if you end up performing the same process on the same message twice, that you end up with the same result. Now with the standard queue, we get nearly unlimited throughput. There's really nothing for us to do to ensure that the standard queue can scale to just about any throughput level. We can send millions and millions of messages through the standard queue, and again, AWS is responsible for ensuring that it scales. AWS handles all of the infrastructure necessary to make that happen. Now we also have first in, first out queues. So with FIFO queues, the order is guaranteed, and it also follows an exactly once delivery. So there are plenty of applications where you rely on the order absolutely, and many applications where you can't afford to do things twice, right? So you need an exactly once delivery. And so if you need order, if you need exactly once delivery, then take a look at the FIFO queue. And so the difference in throughput between these two is fairly significant. Again, with standard queue, we get nearly unlimited throughput, but with the FIFO queue, we do have an upper limit of about 3,000 messages per second if we are using a batch type of operation. So let's take a look at a diagram here. And so the idea with a queue, I'm sure many of us are familiar with queues, some of us may not be, but in terms of queues and how they can benefit our applications, with this diagram, you can see here that we have some type of an application running on EC2 instances, and those are behind a load balancer. So it could be that users are asking for some kind of work to be done, right? They could be uploading documents, and our application on EC2 is responsible for ingesting those documents. Or it could be that they are asking for some kind of report and then willing to wait for that report to be delivered to them later, right? So either way, what we're looking at here is the first stage of an asynchronous process. And so the idea here is that we don't really want to rely on our backend instances here to perform everything. We want to decouple, for example, if we're ingesting images, we want to decouple image ingestion from image processing, right? We want to decouple a user requesting a report from the report actually being generated. And so the way that we could use this is that within Amazon SQS, within the service, we simply create a queue. And that's all we have to do. We create a queue, we give it a name, and that queue, we get a particular DNS endpoint for that queue. And then our instances sends messages to the queue. And those messages will buffer, they will stack up in the queue. And then our backend instances, here we have backend instances that are responsible for doing the work, whatever that work is. It could be doing some type of an image processing, could be video transcoding, it could be executing some type of report on a large data set that's going to take some time. And so our user has requested it, now they're off doing something else while the report is being generated. And so these systems back here, whatever this is, all it has to do now is poll the queue.
So by polling the queue, it can then receive these messages. Once it receives a message, it can then do the work. Once that work is completed, it then deletes the message from the queue. Now, these back-end instances here could be anything. Doesn't have to be EC2. Those could be Lambda functions. They could be containers running within ECS or EKS. In fact, it doesn't even have to be anything on or within AWS. It could very well be servers, traditional servers running on premises. But the idea here is, again, that we are looking to decouple whatever work is being done back here from whatever work is being done up here, so that if either one is down, if our back end is down, then messages can simply continue to buffer and stack up in the queue. And the back end being down should not bring down our file ingestion. We should still be able to ingest or do the front end work until we're able to get the back end back online. And the converse is true as well. If image ingestion is offline temporarily, then our back end can continue to work through the messages that are already in the queue. And so if you have a need for a queue, if you need the ability to send messages between components like this, if you are looking to decouple different stages of your larger application, then definitely take a look at Amazon Simple Queue Service. Now let's review the Amazon Simple Notification Service, or SNS. Now, with Amazon Simple Notification Service, or SNS, we have the ability to send notifications, and this is done through a publish-subscribe kind of model. These messages are pushed to wherever they're going. There's no need for another system to poll the service. In fact, it can't poll. And so again, these messages are pushed. And so the way SNS works is that we create, within the service, we create topics. And we then subscribe to those topics in a number of different ways. We can subscribe via email. We could choose to get a plain email, a plain text email, or a JSON encoded email. We could subscribe to HTTP or HTTPS endpoints through text message. We could also subscribe simple queue service queues to the simple notification service topics, so that as messages go into simple notification service, that could then push them into a queue. That's a very powerful pattern, especially if you're using multiple queues, right? That pattern is called the fan-out pattern, where one message goes through the simple notification service and then gets sent into multiple queues, so that we can perform perhaps several different operations on the same message. We could also leverage mobile push notifications as well. Now, another important thing to keep in mind about the simple notification service is that the order of messages is not guaranteed. So messages could very well reach wherever they're going out of order, right? So if you do need some kind of order to those messages, then within the message you would have to include some kind of piece of data that indicates that order. It's also worth noting that messages are not stored in SNS, right? So once a message has been sent through the topic and pushed to where it's going, it's gone. You're not going to retrieve it again. If it's been lost in cyberspace, then you'll have to resend it again. Now, HTTP and HTTPS endpoints do have a built-in retry, but that's still different than actually storing the messages. And so Amazon SNS is an important service to take a look at and get to know because it does play a very key role, a very central role in a number of architectures, especially when it comes to monitoring
and alerting you as to issues that may be going on. As you've seen throughout things that we've already talked about, Simple Notification Service is used by a number of other services to inform you of things happening within your environment. So like we've seen earlier on, we can leverage Simple Notification Service with Amazon CloudWatch so that alarms can send notifications. Other services like AWS Config and Code Pipeline and CloudFormation, so that we can receive notifications as changes are made to our environment and as other automated processes move through their life cycle of events. So again, keep in mind that when it comes to notifications, especially notifications about your Amazon environment, Amazon Simple Notification Service, or SNS, is a key service to be not only aware of, but very familiar with. Now let's review the Amazon Simple Email Service. With Amazon Simple Email Service, or SES, we get a service that is ideal for sending bulk emails at scale. So think about sending, tens of thousands, hundreds or thousands, or maybe even millions of emails to potentially millions of customers. And not only sending those emails, but ensuring that they get delivered and tracking the results of that campaign. And so Simple Email Service helps eliminate the complexities of delivering email. So if you've ever tried to do this on your own outside of a service like SES, then you may have come to figure out that it's one thing to send an email. It's another thing to ensure that those emails actually reach the inbox, right? Doing that is a very complex process, mainly due to, validation of the actual address and ensuring that they get through various spam filters through the chain of delivery. And so Simple Email Service can help, takes over the burdens of those complexities so that we don't have to worry about it. And so we can use Simple Email Service to send all kinds of different types of emails. We may send transactional emails. So emails that are essentially a receipt of a particular action. So a user signs up and then we send them a welcome email. A user forgets their password and we send them a reset link. The user purchases something and we send them a receipt. Or we could send marketing emails where we may target a particular segment of our user base and send a particular campaign to that group of customers. Or we may send emails to every customer. And in that regard, we're sending potentially upwards of millions of emails at one time. We might also have social networking types of emails. So a user invites their friends to do something, and so you send out emails to maybe a small group of people based on the actions of one person. Whatever the case may be, the idea here is that we're sending email and we want to ensure that the email actually gets delivered. And we want to track, the status of that delivery. And so we're going to talk about that here in just a minute. And so we can send these emails with an API call. We can send many, many emails with one API call. We can also use SMTP if we wanted to. It just depends on how you want to write your software, the software that is actually sending the email. That's totally up to you. We also get a sandbox environment so that we can develop against an email service without actually sending millions of emails to real people. Now, like I mentioned earlier, we can also track the delivery status. So we would want to know, how many emails were actually made it to the inbox, how many emails were opened, how many were marked as spam, how many bounced because of a bad address, or how many were deleted. All of that kind of information is automatically collected and made available to us by the Simple Email Service. We can also use the Simple Email Service to receive incoming mail. So this is very helpful for handling email programmatically. If you want to enable your users to email images or email particular pieces of data, then we can set up simple email service to receive that incoming mail, and we can have that delivered to an S3 bucket, and then we could also automatically invoke Lambda functions to do some type of an automated processing of that email. Now, when we're using this service, it's really important to be aware of sending limits. So sending limits are really put in place to help ensure that your email doesn't get caught up in spam filters. If we start sending a barrage of email immediately right out of the gate, then downstream services, ISPs and email providers could end up flagging our entire domain as a source of spam. And so we have a number of limits that you should be aware of, and I will refer you to the documentation for the specific numbers, but several of them would be, first, a sending quota. So we do have the maximum number of emails that we are allowed to send in a 24-hour period. We also have the send rate, which is the number of emails that we are sending per second. And those limits, when we first set up simple email service for a particular domain, those limits are set fairly low. And so again, that is for, it's not necessarily for Amazon. Amazon has the ability to send just about any volume. This is really to help us sort of get under the radar of the recipient's email provider. So again, we want to avoid just this massive barrage of emails and then being flagged as a spam source. And so by starting at a lower rate of emails, once those systems begin to trust that we are sending quality email, then those limits will be automatically lifted over time. So again, it is up to you. It's your responsibility to ensure that you are you are adhering to these limits, and that you trusting that over time, as you send quality email, those limits will be lifted. So if you have a need to send transactional emails, to send bulk emails for marketing campaigns, social networking emails, any kind of thing that requires you to send an email, and you need to ensure that it's delivered and then track the status, then take a look at Amazon Simple Email Service. Now let's talk about Amazon Cognito. Now with Amazon Cognito, we have two really useful features. We have Amazon Cognito Identity and Amazon Cognito Sync. Now with Amazon Cognito Identity, this part of the service can integrate with OpenID providers to allow our end users, perhaps they are users of our applications, they can log in with any OpenID provider, such as log in with Twitter, log in with Facebook, or log in with Google, or again, any OpenID provider. And from there, we can create user identity pools. Users will authenticate against that OpenID provider, and then Cognito Identity can help us manage those identities across different platforms and different devices. So if they've logged in with Facebook on their mobile device, and then they go home and log in on their desktop, we can help manage that same user identity. Cognito can also help us to leverage temporary keys, which is considered a security best practice. If you remember back to an earlier lesson when we talked about role-based authentication. And so here the idea is that with temporary keys, by using temporary keys, we can avoid the need to embed long-term keys within the application. And so here, a user, again, they might log in with one of these OpenID providers, and by doing that, they either create a new user identity within the user pool, or refresh an existing one. And then whether they log in from a mobile device or they log in with from a desktop doesn't really matter. Either way, we can leverage Cognito to deliver temporary keys to either the mobile application or the web application, and then wherever that application is running, it can then use those temporary keys to communicate with Amazon services directly. It can communicate, for example, to S3 directly, or to DynamoDB or Lambda or API Gateway directly, without necessarily having to pass through our own back-end APIs. And so that provides a very powerful pattern for allowing us to create, event-driven and asynchronous types of applications. Now, another thing that Amazon Cognito can do is with Amazon Cognito Sync, we can use that to store app data, state, and preferences, and all kinds of other things on particular devices. And then as a user goes from one device to another device, we can have Cognito Sync automatically sync that data between those different devices. And of course, not only can we sync across different devices, but also across operating systems and platforms. We can also leverage Amazon Cognito Sync to work offline. If we're creating some type of document processing system and application, then we could allow our users to work offline. And this is especially useful in a mobile environment where perhaps they are on some type of an unreliable network connection, where perhaps they don't have access to Wi-Fi and their cell reception is maybe in and out. And so perhaps they can continue working, and then once they are back in good signal, or once they are back to Wi-Fi, then sync can continue. And so with work offline, it does store the data in a local SQLite database. And then of course, it works seamlessly, right? So again, if as internet connections come and go, when it's intermittent or even totally absent, Cognito Sync can allow us to work offline and then resync again without the user ever really even knowing, right? So keep Amazon Cognito in mind if you want to leverage, especially for mobile applications or applications that are that have both mobile clients and desktop clients, and you want to allow your users to authenticate against an OpenID provider like Twitter or Facebook, and or you want to enable your users to sync data between different devices in different platforms. Now let's talk about Amazon Pinpoint. Amazon Pinpoint is, in essence, a fully managed multi-channel messaging service. With Pinpoint, we can send emails, SMS text messages, mobile push notifications, and also in-app messages as well. And so an obvious question at this point would be, well, what about simple notification service? I can send text messages and mobile push notifications there as well. What about simple email service? I can use that to send email. And all of that is true. The big difference between Pinpoint and using other services like SNS and SES is that with simple notification service and simple email service, your application would be responsible for managing the audience that the messages are going to, delivery schedules, and the content. And so with Pinpoint, Pinpoint provides a number of built-in tools to help with that. So simple notification service, simple email service, those are great for development teams. Pinpoint is great for development teams, but Pinpoint is also great for marketing teams. And that's really what sets it apart. And so Pinpoint includes a number of powerful built-in marketing tools, such as the ability to create message templates. We can also define delivery schedules. We can define highly targeted segments of our customers within Pinpoint. That way we don't necessarily have to do that within our application. We can also, within Pinpoint, just create and manage full campaigns. Now, to do that with simple notification service and simple email service would require a lot more coordination between marketing and development, and it would require a lot more work on development to put that in code. Whereas with Pinpoint, these kinds of things are already built in, and they can be very easily leveraged by code. Now, Pinpoint also provides some very powerful customer analytics features. In fact, what used to be Amazon Mobile Analytics, all of that functionality is now a part of Amazon Pinpoint. And so we can use these analytics to measure a number of things, such as app revenue and app usage. And so we want the ability to not only send these messages, but to understand how those messages influenced a user using our application. Did they respond to that message by opening our application or going to our website? And so we can use these customer analytics to understand trends in retention and customer behaviors, and these kinds of tools, the SDK is very easy to integrate, and it supports iOS, Android, and also JavaScript. And so we can gain a number of insights across such things as demographics, interest data, activation metrics, and retention metrics as well. So as you can see, Pinpoint gives us a very powerful set of tools to enable marketing to segment our audience and ensure that our messages are reaching the right people. And it also gives developers easy tools to code against that. So if you are currently looking to build new applications on AWS, then I would suggest taking a look at Pinpoint. If you're currently using SNS or simple email service and working with a marketing team, then I would also suggest that both teams take a good look at Amazon Pinpoint.
One of the most important facets of a reliable environment is its security, and AWS offers numerous services and features designed to safeguard systems and data. In this lesson, we will review controlling access to data, encryption, and other services that can secure our environment through automation.
Now let's review AWS organizations. Now, with AWS organizations, we get the ability to manage multiple AWS accounts. And so this is a pattern that may be new to some of us, and so it's a pattern that's common throughout AWS, is the use of multiple accounts. One organization leveraging multiple accounts in order to isolate different resources. Now, you could isolate resources based on business unit, based on department, based on functionality, or based on environment, right? You could have, for small teams, I've seen this plenty in companies that I've worked with, is having an account for different environments, like an account specifically for development resources, a separate account specifically for production resources. And by doing that, we can increase the security of our AWS resources by isolating those resources into different accounts, so that if credentials for one account were compromised, they can't be used to compromise or affect resources in another account. And so with AWS organizations, we gain the ability to more easily and more effectively manage those multiple accounts. And so we can also use organizations to automate the creation of AWS accounts. So for example, if you have a larger organization that adds a new business unit, or perhaps as an organization you acquire another company and you want to pull them in and perhaps create new accounts specifically for their environments, then you can automate the creation of that. You can script that rather than having to do it manually. We can also organize accounts by groups. So again, in larger organizations, you could have, let's say that you have different business units. And perhaps you have, each business unit has its own applications that it's responsible for. And so perhaps you want, for each business unit, you want them to have their own accounts by environment, dev, test, and production, as an example. And so you could create a group per business unit, and then you could create an account per environment and then group those accounts for that business unit. We will see a diagram of this here in just a minute. We can also leverage consolidated billing. So within AWS organizations, we get the ability to simplify billing and payments by consolidating the billing for all of these accounts underneath one account. So we essentially pay one bill in order to satisfy the billing for all of these different accounts. And so again, that's consolidated billing. We also have the ability to apply what we call service control policies. Service control policies say that, for example, if you have, let's say that you have, for your entire business or for a particular business unit, you only want to use AWS services that match a particular level of compliance. So let's say that you only want to use services that are within the scope of PCI level 1. And so you could use service control policies to identify and list all of the services that you know to be within that scope, excluding the ones that are out of scope, and apply that service control policy to a particular account or to a particular group, an organizational unit. And then by doing that, those accounts are only allowed to use the services that are allowed by that service control policy. And so even if a user were to log in as a super admin, they wouldn't be allowed to use that service if it's denied by the service control policy. So let's take a look at a diagram here with AWS organizations. So within AWS organizations, we would create an organization. And we would do that with a particular AWS account using the master credentials, right? So we would log in to our initial, perhaps if we're brand new to Amazon, if we're brand new to AWS, we could log in to our initial account, to the one account that we have created, with an email address and a password, logging in as the master credentials. And then we would, by using that account to create the organization, we create what we call the root of the organization. So this one account is now the owner of the root of that organization. From there, we could then create organizational units. This is a way of grouping those other accounts. So an organizational unit, it could be a subsidiary, it could be a business unit, it could be a department, it could be a team. That's up to you. AWS typically tries to do things in more generic ways so that they can be flexible to your particular use case. And so once we have organizational unit, we may then add or automatically create a new account to be under that organizational unit. And you'll notice here we could create another account under that organizational unit. And you'll see that there is nothing about an account that inherently flags it as being, for development or for production or for anything in particular. All accounts are functionally identical. What we use that account for is totally up to us. If we want to use these two accounts here for different environments or different teams or different types of applications, then that's up to us. Then, of course, we could go and create other organizational units, and from there we may have one account under that. We may even have another organizational unit under that, right? So you can group organizational units underneath one another. And then, of course, we may have other accounts there as well. So as you can see, we have a lot of flexibility in how we group and organize these various accounts. And it's all according to what makes the most sense for your particular business and the way in which you plan to use AWS. And then, of course, we can add service control policies.
And again, service control policies say that we are allowed to use certain services and not allowed to use others, right? So you can control which services are allowed to be used by those accounts. And we can apply service control policies to organizational units. And so in this example here, by applying the service control policy to the organizational unit, it then affects all of the accounts that are under that unit. Now, not only can we apply service control policies to organizational units, we could also apply them directly to AWS accounts, right? And then we may create other service control policies and apply those to other units or other accounts, right? So again, to recap that, when you are approaching AWS for the first time, especially if you are part of a larger organization or even a smaller company, maybe you're a part of a startup, you can still gain the benefits of isolation by using perhaps 2 or 3 accounts, one per environment, dev, test, production, right? In larger organizations, larger enterprises, you may find it necessary to have even more accounts, maybe dozens, and grouped according to business unit, department, subsidiary, and so on. And so again, I would encourage you to think more about leveraging multiple AWS accounts so that you can gain isolation between your resources. You can gain an increased level of security, knowing that if credentials for one account were compromised, they can't, or at least they would be very difficult to use in order to affect resources in another account. So again, when we're looking to leverage multiple accounts and consolidate the billing for those accounts, we would look to AWS organizations. Now let's talk about AWS WAF, or the Web Application Firewall. Now with AWS WAF, we have the ability to perform Layer 7 content filtering. We can run the Web Application Firewall. We can deploy this alongside our CloudFront as part of our CDN solution, or we can run this alongside our application load balancer as well. And so the Web Application Firewall, there's nothing for us to, there's no server, there's no instance for us to manage, there's no software to install. All we do is opt in to using the Web Application Firewall, configure it to work with either our CloudFront distribution or our application load balancer, and from there we simply create and manage the rules that govern what type of requests are allowed or rejected. Right? So again, we can use the Web Application Firewall to inspect the content that's coming in to our web application. And so we can inspect HTTP headers, we can inspect the body, we can inspect URI strings, and we can use this to either block or allow that particular request to happen. And so again, like I said, it does integrate with Amazon CloudFront as well as the application load balancer. And it can help protect help protect our applications against things such as SQL injection, cross-site scripting, and other kinds of malicious behaviors. And so with the Web Application Firewall, we can write rules that can block based on things like IP addresses. We can block based on the presence or absence of particular HTTP headers or body content, right? So for example, you may require a particular header to be included in every request, and if that header is absent, then the Web Application Firewall could simply reject that request right there before it ever even reaches your back-end instances. Or perhaps you are looking for the presence of some kind of malicious header, and if you see that, it's rejected. We could do the same thing to URI strings. Perhaps you are looking for a particular URI string, and maybe you're looking for the presence of it regardless of the value, or maybe you need a specific combination of key and value in the headers or the URI strings. Either way, you can create these kinds of rules, and the Web Application Firewall will then be responsible for
executing those rules and ensuring that requests either are accepted or rejected. We can also use the web application firewall to perform rate limiting. We can do that per client IP, and we also have, Amazon provides us with managed rules. And we have a number of managed rules for things like OWASP, bots, and a number of other common vulnerabilities and exposures. And so looking at a diagram here, you can see that in this particular diagram, we are running in a particular region. Doesn't really matter what region we're running in. We have up here, you can see we have an application load balancer, but in this particular diagram, for this example, we've decided to configure our web application firewall to be deployed with our CloudFront distribution, and so it is deployed out here alongside our edge locations. And so as our users make requests to the edge location, then the web application firewall is inspecting that content as it comes in. That way it can block that content if it's determined to be potentially malicious. We can block it before it ever reaches our load balancer, let alone our backend instances. And so we have a number of threats that may be coming in, right? We have SQL injections, cross-site scripting, we have deserialization attacks or other kinds of flooding attacks that are coming in, and we can use the web application firewall to inspect that content and help protect our system from malicious activity. Now let's talk about AWS Key Management Service, or KMS. Now, AWS KMS, or Key Management Service, gives us a fully managed key management infrastructure. So when we need to protect our data at rest, when we need to encrypt that data and perform server-side encryption, one of the most important aspects to that process is choosing where the keys come from. And so we can leverage many of the services within AWS that perform server-side encryption can pull their encryption keys from KMS. So it's really important that we have a reliable key management infrastructure, because if we lose the keys, we lose the data. So KMS performs three critical things. One, it stores customer master keys. And these customer master keys can be used to perform encryption directly on up to 4,096 bytes, or we could also have KMS generate unique symmetric data keys. And those data keys could be either 128 bits or 256 bits. And then KMS would use the customer master key to encrypt the data key. Hold that thought. We're going to talk more about that in a diagram. We'll walk through how that works in a diagram here in just a moment. Now, all of the encryption is performed, and all of these data keys are generated by hardware security modules. In fact, these security modules are validated against FIPS 140-2, so they are trusted to be very secure. And ultimately, to put it simply, KMS, you could think of it as an API, a multi-tenant API in front of hardware security modules. Now, we as customers, we don't have any access, direct access to the hardware security modules. We interact with the KMS API, which in turn interacts with the hardware security modules, and only AWS has access to the hardware. Now, we can also count on KMS logging key use to CloudTrail. So if we do need to satisfy compliance, if we do need to inspect, what keys were being used by what credentials, then we can look to CloudTrail. Another aspect of the security of KMS is the fact that the customer master key, the cryptographic material that makes the customer master key, never leaves KMS. We always refer to the CMK by ID, and that cryptographic material is always held inside the hardware security module. And KMS also integrates with a number of other Amazon services, right? Just about any service that can perform server-side encryption within AWS can integrate with KMS so that it can retrieve its data keys from KMS. KMS is also certified against a number of very stringent controls, including SOC 1, SOC 2, SOC 3, and PCI DSS Level 1, among others. And so taking a look here, again, if we wanted to leverage KMS to perform encryption, so for example, if I have an application and I need my application to encrypt data, then one, KMS, I would have a customer master key within KMS. And in fact, every account already includes the default KMS or customer master key within KMS. Now you can create additional customer master keys, but there is always a default one. And so if we have an application that needs to perform encryption, what our application would do is make a call to KMS, and if what we're encrypting is larger than 4,096 bytes, then we would ask KMS for a data key. And now, of course, we would get back a plain text data key. And not only do we want a plain text data key, but we would also want an encrypted data key, right? And so keep in mind that the only thing that KMS stores is the customer master key. KMS will generate data keys, but it will not store them. It is up to us to store the data key. So we can have it generate a data key. We can then use the customer master key to encrypt the data key. And so KMS will then give us both the plain text and the encrypted data key. Our application can then use that plain text data key to encrypt our plain text data, and then we end up with encrypted data, right? And so it is then our responsibility to store both the encrypted data and the encrypted data key. And that's very important to keep in mind because, again, if we lose the key, we lose the data. And so this process of using one key to encrypt another key is called envelope encryption. So here we've used one key to encrypt our data. We've used another key to encrypt our plain text data key, right? So again, that's envelope encryption. And that just provides an extra layer of security. It makes things much more difficult to compromise by layering our encryption in that way. So again, where we store the encrypted data key, where we store the encrypted data is totally up to us. We could store the encrypted data in S3 and the encrypted data key anywhere. We could store it in DynamoDB, in RDS, we could store it on premises, so long as we have a reliable way of retrieving that encrypted data key. And then when we need to decrypt the data, this process would go in reverse. We would give the encrypted data key to KMS. KMS would use the master key to decrypt it and give us back a plain text data key that we could use to decrypt our data. And so here, looking at a list of services that integrate with KMS, and again, this is not an exhaustive list. This is just a few examples of services that can perform server-side encryption when using KMS, right? So just as a quick example here, when we use Amazon S3 to perform server-side encryption, we can choose to have S3 get its keys from KMS. And when it does so, it will use a unique data key per object. That way, if somehow, some way that data key were compromised, only that one object would be compromised rather than every object in the bucket. And the same thing applies to Amazon Glacier. If we use Glacier, Glacier does automatically perform server-side encryption. That's not something that we have to opt into. It just happens. And we can leverage KMS, and we can ensure that Glacier is pulling keys from KMS. And when it does so, it uses a unique data key per archive. DynamoDB, Amazon RDS, Amazon EBS, these can also integrate with KMS. In the case of the Elastic Block Store, we would use a unique data key per volume. Amazon EMR can also use data keys to encrypt data in that EMR cluster. Redshift takes it pretty far. Redshift uses a 4-stage envelope encryption. So within Redshift, there are numerous keys that are each encrypting each other down the line. So we have a very secure environment within Redshift. And then SQS, right? We can get unique data keys for our queues so that we can ensure that our messages in that queue are encrypted at rest as well. So if you have a need to perform server-side encryption within AWS and you don't want to manage your own key management infrastructure, and you have the ability to use a multi-tenant API such as KMS, then take a look at the AWS Key Management Service. Now let's talk about AWS Shield. With AWS Shield, we gain access to a distributed denial of service protection service. And so this service can help protect us against common attacks based on layers 3 and 4, so networking level attacks. And some of these attacks might be things like UDP reflection attacks, DNS reflection, NTP reflection, other things like SSL renegotiation, slow LoRa's attacks. And so with AWS Shield, we gain a very powerful, again, DDoS protection service, and this is available for free to everyone, or AWS Shield Standard is available for free to everyone, and there's nothing for us to do. We get the standard level of AWS Shield without really even having to opt into anything. It's already there when we use things like CloudFront, Elastic Load Balancing, VPCs and security groups, and Elastic IPs. And so if we need an additional layer of mitigation and protection, we can subscribe to AWS Shield Advanced. Now, with Advanced, again, we get that additional detection and mitigation against more sophisticated and larger attacks. And we also get near real-time visibility into those attacks so that we can be up to speed as far as, the nature of the attack, what the progress is in helping to mitigate that attack, and so on. We also get DDoS cost protection. So when we apply AWS Shield Advanced to certain things like our load balancers, our Route 53 DNS zones, when we apply Shield Advanced to things like our Elastic IPs and our EC2 instances, our auto-scaled fleet of instances, if any of those services were to scale as a result of that DDoS attack, then we could get service credits for that. Another nice feature of Shield Advanced is that it integrates with the web application firewall. And so we can get automatic rule creation based on what's happening with that DDoS attack. We also gain access to a 24-hour-a-day, 7-day-a-week DDoS response team, and so or what we might call the DRT. And so the DDoS response team can help us mitigate that. They can actively help us mitigate a DDoS attack. They can also write WAF firewall rules for us. Now, it does require a subscription. So AWS Shield Standard is available for free to everyone, but Shield Advanced requires a subscription. And once you subscribe to that, Shield Advanced, it will cover all of the accounts for that organization. You don't have to do it per account, you do it per organization. And so any account that is linked underneath that organization can be protected by Shield Advanced. So let's take a look at this diagram, and you can see here that we're using
CloudFront, we're also using, we have an elastic load balancer. Here we have EC2 instances running our application. And we want, ultimately, we want to prevent these instances from coming down as a result of an attack. And so you can see that all of these, we are leveraging Amazon CloudFront. We have all of those, edge locations all over the globe, right? And AWS Shield is working alongside the AWS WAF. Both of those are working at the edge location. So as this flood of attacks are coming in, some of the benefits here are that, one, because we do have those 100 edge locations, more than 100 edge locations all over the globe, there's a much wider footprint to absorb that attack. The attack is not concentrated right here at the load balancer or on any one EC2 instance. The attack can be absorbed by many machines across those edge locations all over the globe. And so, like I say, a number of those attacks are already mitigated by AWS Shield working alongside CloudFront at the edge location. And then, of course, we can leverage AWS Web Application Firewall to help further mitigate and block requests based on IP and HTTP headers and so on. And then, of course, back here on the load balancer, we would of course have a security group on the load balancer. We would also have security groups around our EC2 instances, and we can use those tools to help mitigate different types of attacks as well, such as UDP reflections and UDP flooding, sign flooding, and so on. Now, CloudFront is really great for HTTP-based applications, applications doing streaming such as RTMP and HLS. CloudFront also supports WebSockets, but it is specifically for TCP-based applications. If we have applications that are not based on TCP, if we have applications that are using things like UDP or SIP, then we cannot use CloudFront. We also cannot use elastic load balancing. So remember that CloudFront and elastic load balancing are both specifically for TCP-based applications. And so for non-TCP-based applications, UDP, SIP, whatever the case may be, then we would need to run an EC2 instance that is directly available from the internet. So in this example, you can see we have an EC2 instance, and we would also, in this region, we would of course have a VPC, and we would have an internet gateway. We would have routing tables that allow this instance to be directly reachable from the internet. And so when we have that, AWS Shield standard is already protecting this EC2 instance against those common infrastructure attacks on layers 3 and 4. So we do get some protection, certain types of UDP reflections and NTP reflections, DNS reflections, those kinds of things. Those common attacks are already mitigated by AWS Shield standard for that instance. If we wanted to leverage AWS Shield Advanced, then we could enable Shield Advanced on an elastic IP address. And of course, that elastic IP address would be attached to the instance or associated with that instance. And so by attaching AWS Shield to the elastic IP address, then we could gain access to Shield Advanced, which would automatically, AWS Shield Advanced will detect the size and type of that EC2 instance and automatically apply predefined mitigation profiles. And then we could also work with the DDoS response team to help create custom mitigation profiles for our particular scenario. So either way, if you're using TCP-based applications behind CloudFront, if you're using UDP or SIP-based applications, on an EC2 publicly available EC2 instance, then we can still get DDoS protection using AWS Shield. So
if your organization is concerned about some kind of DDoS attack, then one, you can rest assured knowing that you already get a notable level of protection with Shield Standard without having to do anything. And then, of course, if you want further protection, if you want that more deeper protection, if you want access to some type of DDoS support team, then take a look at Shield Advanced. Now let's review a few other security services, such as Amazon Macie, Amazon GuardDuty, and Amazon Inspector. Now, Amazon Macie is a service that can automatically discover, classify, and protect sensitive data within AWS. This data could be things such as personally identifiable information, PII, could be protected health information, PHI, could be intellectual property or other types of sensitive information. And Amazon Macie leverages machine learning to automatically learn what types of information are deemed to be sensitive and learns the type of patterns that are happening within your account. Amazon Macie will then proactively inform you as to where that data is stored and how that data is being used. And so Amazon Macie is really useful in those cases where perhaps you do have a larger organization, you have a lot of people using AWS resources, and maybe you have a number of S3 buckets and a lot of data moving around. And as we've seen over the years, we've seen plenty of articles where companies have sort of gotten in trouble because they made sensitive data publicly available, or they made sensitive data, if not publicly available, they made it available to people who should not have had access to it. And so Amazon Macie is a service that can help us discover those kinds of things. Perhaps we inadvertently made a misconfiguration in our policies that allowed sensitive information to be accessed by unauthorized parties. And so again, Amazon Macie is an ideal service to turn on to inform us as to whether or not we do have sensitive information that's being accessed inappropriately. And so Amazon Macie can again proactively alert us to suspicious activity. And it's worth noting that as of the time of this video recording, Amazon Macie currently supports Amazon S3. But according to Amazon's website and documentation, other data stores are being worked on, and so I do expect that Amazon Macie will support other data stores such as DynamoDB or Redshift or so on in the future. But as of the time of this video, we don't have a date on that. Another thing worth noting about Amazon Macie is that it does leverage natural language processing, and it is currently optimized for English. It does support a number of languages, but it's optimized for English. And so I also suspect that other languages will be optimized in the future. But again, as of the time of this video, it's currently optimized only for English. Now with Amazon GuardDuty, we have a fully managed threat detection service. GuardDuty will continuously monitor our environment for malicious or unauthorized behavior, such as attempts to gain access to the API using credentials, compromised credentials, or gaining access to EC2 instances over the network. And so Amazon GuardDuty can automatically, continuously analyze billions of events from a number of different sources, such as CloudTrail. Remember that CloudTrail is the service that records API calls. And so if GuardDuty is seeing a number of API calls that are outside of a normal pattern, then that might indicate some type of malicious activity. It might see that certain credentials are being used for things that they are not normally used for, or that a certain set of credentials are trying different things. Maybe just one attack may be just to try different things to see what's going to be found, right? So those kinds of patterns can be detected by GuardDuty.
GuardDuty can also analyze VPC flow logs. So VPC flow logs are logs that record metadata about network traffic flowing through our VPCs. And so VPC flow logs will contain things like source and destination IPs and ports. It will contain whether or not the protocol, whether it's TCP or UDP, things like that. And so GuardDuty can look at VPC flow logs to try to identify some type of malicious or unauthorized network traffic. GuardDuty will also look at DNS logs. And so we can look at DNS logs from Route 53 to determine, to see if perhaps someone is trying to find subdomains that they shouldn't be accessing, just as one example. And so Amazon GuardDuty can aggregate this kind of threat detection across multiple accounts, right? We don't necessarily have to turn this on for every account. We can turn it on for our organization, and GuardDuty can look at all of our accounts. And another nice thing about GuardDuty is that there is no software to install. There's no agent that needs to be put in place. There's no servers that need to be running. We simply turn GuardDuty on as a service. GuardDuty can also trigger AWS Lambda. So if GuardDuty finds something and it alerts us as to something going on, we can also use that alert to trigger Lambda, and we can pass metadata about that particular incident to Lambda, and then we can use that to programmatically mitigate that particular incident. Perhaps GuardDuty found something in the network that suggested an EC2 instance is compromised. And so we could, as an example, we could use that event to trigger Lambda, and Lambda could then perhaps either remove that EC2 instance or contain that instance on the network by removing security groups so that it is no longer accessible. Now, finally, moving on to Amazon Inspector, we have another automated security assessment service that automatically scans applications for vulnerabilities. And so if we have applications that are deployed to AWS, especially those that are deployed directly to EC2, then Amazon Inspector is an agent-based, API-driven service. So we do require an agent running on the EC2 instance, and that agent can regularly scan software that's installed on that instance and compare that software and compare the configuration of that instance against databases of known vulnerabilities. And so when those assessments occur, Amazon Inspector can give us a detailed list of findings. It can show us that perhaps we are leveraging a library that is known to have some type of a vulnerability. And it will also prioritize those. Some could be critical, some could be high or medium, and so on. And so we get a dashboard of all of those findings, and from there we can go and mitigate those. Perhaps that would mean that we need to simply make a patch to OpenSSL or something like that. And so because it is automated, because it is running right there alongside our applications, we can essentially build that into existing DevOps processes. So perhaps not only are we looking to improve features and performance of our application, but we're also looking to improve security. So perhaps we take findings of Amazon Inspector and we add those requirements to our sprints so that the next release of that software would include patches and updates to existing or dependent libraries. And so again, we can use Amazon Inspector to enforce security standards. Now keep in mind that many of these kinds of services include free trials. Some of them include or require subscriptions. Others are pay-as-you-go according to what's actually being done. So I will refer you to the Amazon website to get details about the pricing, because that changes. By the time this video is published, it could be very different. So as you can see, throughout this module, we've talked about a number of really powerful security features that can help us keep our Amazon accounts and applications and infrastructures highly secure.
Cost savings is perhaps one of the primary drivers of AWS adoption, but in order to realize those cost savings, we need to be fully aware of not just the dollar amounts we pay, but the things we pay for, those options and fine details that actually contribute to costs. In this lesson, we will review the cost models and highlight often overlooked cost contributors for various services, as well as tools we can use to understand and manage those costs.
Now let's take a moment to understand compute costs within AWS. So with EC2, we have several different billing options. You'll see here that we have the on-demand, which is sort of the MSRP. If Amazon says that a particular instance costs a certain amount per hour and we are willing to pay that, then that's what we pay. But if we want to save money on those, then we have the option of either going with a reserved instance or leveraging spot instances. And so we're going to talk in more detail about the difference between reserved and spot here in just a moment. I will let you pause the video and review this chart on your own. So I'm not going to speak to everything here except to point out a couple of things. Really important things is that, one, you'll notice here that in terms of the availability, that with on-demand pricing, availability is not guaranteed. And so keep in mind that AWS is constantly growing their data centers. They are constantly adding more and more compute capacity to their data centers, and their available compute capacity is really, I think, hard for most of us to even imagine. But at any one time, at the time you ask for that instance, that particular size instance, in that particular availability zone, there is a finite capacity. And so it is possible that you could request an EC2 instance, a particular size in a particular availability zone, and the API could come back and say, we are out of capacity for that size instance. Try another AZ or try again later, right? Now, in my decade of using AWS so far, I've only ever seen that happen maybe 3 or 4 times. So it's pretty rare, but it is possible, right? So keep that in mind, that with on-demand, the availability, there is no guarantee that you will actually get the machine that you are asking for. The same is true with spot instances, and we will talk more about spot instances here in just a moment, but for now, spot instances are based on supply and demand. And so when there is a large demand, it may be possible that we just can't get one due to the actual price that we're willing to pay. And we'll take a closer look at that here in just a moment. With reserved instances, you can see here that it is guaranteed under certain conditions. So if during the purchase of a reserved instance, if we opt in to a particular availability zone and we specify a particular availability zone, then part of what we are reserving is capacity in that availability zone so that we do have confidence that we will get the machine when we need it later. So let's take a closer look here at some of these other billing models, starting with reserved instances. Now, reserved instances give us a way of gaining very significant savings versus on-demand, right? Depending on the region that we're in, depending on the size and type of instance that we're talking about, we could see upwards of 75% savings versus on-demand. So the savings, again, is all according to the size and type of EC2 instance in that particular region. Different regions may cost different things. Now, with the reserved instance, we do make a commitment to either 1 or 3 years. And so essentially, we are committing to paying for every hour of every month for that 1 or 3 year term. And that's really the only way that AWS can offer those savings on reserved instances. And so with the reserved instance, we do have the option of making no upfront payment, a partial, or a full upfront payment. And so the more we pay upfront, the more discount we get. And so again, we will pay the hourly fee regardless of use. And so remember, keep in mind that purchasing a reserved instance and launching an instance are two completely different things. Just because you purchase a reserved instance doesn't mean that you actually launch one. And just because you launch one doesn't mean that it qualifies for the reserved instance discount. And so generally, when you purchase a reserved instance, you are making sort of a flag in the billing model. It's sort of a billing reconciliation kind of a model. And so what happens at the end of the month is that AWS will look at the instances that you're running and compare those to the reserved instances that you purchased and apply that reserved instance discount to the instances that were running. But if no instances were running, you will still pay some hourly fee for the reserved instances if you did not make a payment up front. And so again, if you choose to assign an availability zone to that reserved instance, then you can ensure that you will get guaranteed availability because AWS will reserve capacity for you. Reserved instances are generally best for constant applications or things, databases and things that need to be running for long periods of time. The general rule of thumb is that if your instance is running for more than, say, 55% of the month, then you can save money by going to a reserved instance. Anything less than 55% of the month, give or take, you may not really see a cost savings by using reserved instances. So that brings us to spot instances. Spot instances, the fee for those is based on supply and demand. And so again, Amazon has an incredible supply for different size machines in each availability zone. And so at any one time, there could be a greater or lesser demand for a particular size machine. So for example, there could be large organizations doing some kind of monthly reports and leveraging a certain size machine and leveraging thousands of that particular size machine in a particular AZ. And so that significant increase in demand would, of course, lower the supply. And so as the demand rises and the supply goes down, then the fee rises as well. And so by using the spot market, by leveraging spot instances, we could pay potentially a fraction of the on-demand price. And so the way that this works is that when we launch an EC2 instance and we opt in to using spot instances, keep in mind that functionally there's no difference. This is all billing. There's no such thing as an on-demand instance or a spot instance. It's just a matter of how we pay for it and what we pay. And so when we launch an EC2 instance and we opt in to the spot market, we will specify the maximum amount that we are willing to pay per hour for that particular machine. Now, it's important to remember that, again, that the fee that we pay is the current market price. And so if the current market price is, say, 5 cents, and we're willing to pay 10 cents, then as long as that market price is below our maximum spend, we will get the machine and keep the machine. But if the market price goes to 11 cents and we're only willing to pay 10, then AWS can terminate the instance and give it to someone who's willing to spend more money, right? So keep that in mind. The instance can be terminated by AWS. And so spot instances are generally best for some kind of temporary work that can be done quickly, or batch processing, testing and experimentation. I've done this plenty of times. For example, I've been in plenty of situations where I need a particular piece of software to run on say, a small instance, like a T2 small or a T2 medium. But I need, before I can run it in production, I need to compile it. And compiling it may take, a long time on such a small instance due to the limitation of the CPU. And so there's been plenty of times when I've spun up a large machine, a more expensive machine, in order to do that compilation, in order to compile that binary. And in those cases, I chose the spot market so that I could get that large machine at a fraction of the cost. And then once my binary was compiled, I could then create an image out of that and then put it into production on a smaller machine. So testing and experimentation is another use case for the spot instances. Also, other things, like end-of-year billing reports or quarterly sales reports. These kinds of things are typically like temporary work. They can run for a particular period of time and then stop. We don't really need these machines to be running all the time. They're only running for the period of time it takes them to complete that report. And these kinds of things, if the market price were to go above our maximum spend and we lose the machine, then ideally our work, the processes that we're running, are able to tolerate interruption. So our apps really need to tolerate that kind of interruption, and so which means that they are ideally saving regularly and recording some kind of checkpoint so that they can pick up and get back to work when the market price lowers and we're able to get a new machine. And so that brings us to pricing for AWS Lambda. Lambda is also a part of computing, and for Lambda, remember that we will pay a certain fee per gig of memory per 100 milliseconds. So the more memory our application uses, or the more memory we allocate for a function, and the longer that function runs, the more we pay. And so one thing to keep in mind with Lambda is that it's really useful to test that application or test that function and see just how much memory does it really need. You could end up artificially inflating your bill by configuring a function to use 1 gig of memory when your code really only needs, maybe 200 meg, right? So be sure to set the memory requirements of those functions according to what the function really needs. Another thing to keep in mind is that it's possible with Lambda to set an execution timeout. And I've seen organizations just always default to a 5-minute timeout, and then if there's errors in the code continues to run until the timeout. So they're always paying for these long-running 5-minute functions when they could have exited at 1 second and saved over time. That could add up to a lot of money. Also keep in mind that with AWS Lambda, we are paying per 1 million requests. And so every time we invoke a function, every time we call the Amazon API in order to execute that Lambda function, that's considered a request. So if we are doing that millions and millions of times, then that will also contribute to our bill. Right? So it's important that as you move through AWS, one of the things to keep in mind is that for most things in AWS, it's pay as you go, and that's one of the beautiful benefits of the cloud versus traditional IT. And for AWS, or for the cloud in general, it's the trick to saving money in the cloud is to use what you need, right? So it's pay for what you use, but to save money, we want to design our systems to use what we really need. Now let's take a moment to understand storage costs within AWS. Starting with Amazon S3, you can see here in this diagram that we have an EC2 instance that is communicating with an S3 bucket. It's uploading objects, it's downloading objects. We may also be downloading objects from S3 to the internet or transferring them to another region. So when we are using S3, it's really important that we understand the things that will contribute to our bill. So starting with storage, storage does cost per gigabyte per month and is tiered. And so as you store more data and you get into certain levels, into the terabytes and into the tens and hundreds of terabytes and beyond, at certain levels the cost of that storage starts to go down. Now in terms of bandwidth, moving the data in and sending the data out. So we have inbound bandwidth and outbound bandwidth. As far as inbound bandwidth goes, that is always free. It doesn't matter where the data comes from. If it is being uploaded to S3 from EC2 in the same region, if it is being uploaded from on-premises or from our users out there on the internet, it doesn't matter. Inbound bandwidth is free. Outbound bandwidth really depends on where it's going. So outbound bandwidth to the internet or to another region will cost per gig. So remember that transferring data between two different regions is ultimately going over the internet. Now, outgoing bandwidth between S3 and EC2 in the same region is free. So that's an important distinction. So if you have an S3 bucket in one region and an EC2 instance in the same region, then that transfer is free. If you have an S3 bucket in one region and an EC2 instance in another, then that transfer from S3 to EC2 will cost. It will be considered outgoing bandwidth. Another thing to keep in mind is that as we make requests to S3, as we perform those GET requests to download that object, even for, let's just take GET requests for a second. Even if the bandwidth between S3 and the EC2 instance is free, the fact that we are making a GET request means that we will be contributing to our bill for every 1,000 requests. And even if uploading to S3 is free, the bandwidth is free, the fact that we are making put or post requests will all contribute to our bill. So keep that in mind, that just the fact that we are making requests, per 1,000 requests, we will be charged for. Another thing to keep in mind is that we pay a certain amount of money for S3 for the storage that we are actually using. So there's no need to provision storage within S3. We just upload and it's a true pay for what you use. If we upload a gig, we pay for a gig. If we upload a terabyte, we pay for a terabyte, and there's a particular fee for that storage. If we want to lower our costs, remember that we can use lifecycle rules to transition data into different storage classes. So within S3, there are different storage classes that can lower our cost, and then we can also see the greatest cost savings by archiving data to Glacier for long-term storage. So remember that there are oftentimes certain types of data that we need to hold on to for some period of time. It could be 7 years, 10 years, 20, whatever the case may be, according to your compliance needs. And so using those lifecycle rules within S3 is a great way to automatically shift the storage class to something that can save us money in the long term. Now, moving on to Amazon Elastic Block Store, let's review the costs for that. You can see here in this particular diagram that we have an EC2 instance here that is leveraging two different EBS volumes. It has perhaps a small 8 or 20 gig volume for the root volume, and it may have a larger provisioned IOPS for the data volume. And this is a very common pattern where we may use a small volume for the operating system for the root volume and a much larger, more performant volume for data. Remember that the one thing to keep in mind about root volumes is that here on this root volume, if the EC2 instance, if this instance were to be terminated, the default behavior is that this root volume would also be deleted. And so the benefit of putting data on a data volume is that if this EC2 instance is terminated,
then the default behavior is that this data instance here would remain. And so that particular pattern has saved my life many times by allowing me to keep the data. And so as far as charges go, both of those volumes, all EBS volumes, will charge per gig per month of provisioned storage, right? So it doesn't matter what you're actually using. Unlike S3, with EBS, we have to provision a certain amount of storage for that volume before we can use it. And so if we have provisioned, let's say, a terabyte-sized volume, then we will pay for a terabyte, no matter how much data we've actually written to that volume, even if it's empty. Even if all we ever did was format it, we will still pay for the terabyte because that's what we provisioned. And so in this example, our root volume may be just a general purpose SSD, and so all we're paying for is the provisioned volume. But it's common for our data volumes to need more performance. And so in this example, we might use a provisioned IOPS SSD. And so provisioned IOPS SSD, in addition to the storage, will also charge per provisioned IOPS per month. So we have two different charges, a charge for the storage and a charge for the IOPS that we are provisioning. With provisioned IOPS volumes, we can essentially say that we're willing to pay for a guaranteed level of performance. It's also worth remembering that as we take, you'll see here that we are regularly taking snapshots of our data volume, which is a good practice. We want to ensure that even if we lose that volume, if it's inadvertently deleted, then we want to be able to restore that volume from a snapshot. So volume snapshots, remember that though they will also charge for whatever storage we use in S3. And again, that is per gig per month. So the thing about AWS is that for most things, it's pay-as-you-go, pay for what you actually use. But keep in mind that under certain cases, like we saw here with EBS, some things could be pay for what you provision, and that's an important distinction. And so one of the ways to save money with storage, especially with EBS, is to ensure that you are using volumes that are the right size, right? So that there are a number of ways. When we understand all of the things that contribute to our bill, we can be better prepared to design a system to help us save money in the long term. Now let's review a couple of other cost optimization tools. First, let's take a look at the AWS Cost Explorer. And so you can see here in this screenshot of the Cost Explorer, we have the ability to really, as the name suggests, explore our costs over some period of time. And so we can really dive into the, our bill and look at the things that are contributing to our AWS monthly costs. And so you can see here on this screen capture that we have the ability to graph, and of course we can form, this is a stack graph, but we can form other types of charts as well, line and other types. You can also see that we have the ability to look at, here in this example, we're looking at the last 12 months, but we could look at the last 1 month, the last 6 months, and so on. We could also, it allows us to group by various things. Here, this particular chart is grouped by region. And so you can see that right about here, we can highlight this massive spike in our costs. And you can see that somewhere around May of 2017, in the Oregon region, we had a rather significant spike in cost. And then you can also use the Cost Explorer to filter. We could say, well, I want to look at my cost, but I really only want to look at a particular, say, a particular region. Right here, we are including all regions, and we're grouping by region. If I wanted to, I could filter and say, well, only show me a particular service, and then group by region. We could also filter by tag. And so one of the keys to accurate cost allocation is maintaining consistent tags, right? So most AWS resources support tagging, and approaching AWS with a consistent tagging strategy is very important in allowing you to attribute cost accurately. And so what I typically advise people that are just getting started with AWS is that tags are arbitrary, right? Tags, it doesn't really matter what the tag is. If you, for example, if you wanted to attribute cost per environment, then you would have a tag that says environment equals, say, dev, or environment equals development, environment equals prod, or environment equals production. And in that regard, it doesn't matter what you name the tag. It could be env, it could be environment. Doesn't matter what the value is. It could be dev, it could be development, it could be prod or production. Those kinds of things don't really matter. What matters is that you are consistent across the board, across everything. What could cause you some challenges is if, you know, certain people are using one value and one tag, and other teams are using a completely different tag or a completely different value. And so it's important when you're using things like the Cost Explorer and you want an accurate assessment of your costs, and you want to be able to do that by tag and leverage things like cost center, environment, business unit, project, application, and so on. If you want to attribute cost to those kinds of things, then we need to be consistent in our tagging. So as far as cost, we have the Cost Explorer as a way that we can go into the AWS console and really get hands-on exploration of our bill. Another thing that we have access to is the AWS cost and usage reports. So with cost and usage reports, we have the ability to access highly detailed billing information. And so when we turn this on, it's not on by default. So when we opt into this and turn this on, we specify an S3 bucket that we want this information delivered to, and AWS will regularly, several times a day, will upload CSV files to that S3 bucket. And those S3 files can very easily be ingested into Redshift or to QuickSight. And so remember that Redshift is a petabyte scale data warehouse. So we could import our billing into Redshift if we wanted to run queries on it. Or QuickSight is an in-memory analytical engine and a very powerful, very useful dashboard for performing analytics on large data sets in memory. And so if we wanted to explore our costs with other tools besides the Cost Explorer, we could leverage the cost and usage reports to pull them into Redshift, into QuickSight, or we can download them local and use Excel if you wanted to do that as well. With the cost and usage reports, we have usage that is listed for each service. It's listed by region. It's also listed for tags. So again, tags are very important if you want to be able to attribute costs to things that are specific to your organization, such as team, environment, cost center, and so on. We can also aggregate those reports to daily or monthly reports. So if we wanted to look at reports by month, then we can aggregate the cost and usage reports as well. So in terms of cost, now that we've talked about a number of different things throughout this module, again, as a reminder, within AWS, most things are pay for what you use. Very few things are pay for provisioned, but the great majority of things within AWS is pay for what you use. And the trick to saving money within AWS is to use what you really need. And of course, as you can imagine, throughout this course, we have seen a number of diagrams, fairly complex diagrams, where there are numerous moving parts. And you can imagine that as you start to use AWS, deploying numerous applications across numerous environments, for larger organizations, deploying those numerous applications across different business units and different environments, that you could end up with very complex ecosystem within AWS. And so as it grows,
as you grow in size and grow in complexity, it can become a challenge to ensure that you are always using what you really need. And so these tools, the AWS Cost Explorer and the AWS Cost and Usage Reports, can both help you highlight areas or identify areas where you are spending more money than you need to, and in turn highlighting areas where you are using more resources than you really need to. And so throughout this module, talking about cost, we've only scratched the surface. There are much more that we could talk about. And so if you want to understand more about costs of different services, if you want to understand more about techniques that you can use and processes that you can use to save money in your AWS environments, then I would encourage you to take a look at my other video, the AWS Solutions Architect Associate Complete Video Course. The cost optimization section in that video goes a bit deeper into various places as it relates to costs.
So we're coming to the end of our time together, and I want to leave you with some overarching thoughts in regards to Amazon Web Services and a few notes about certification.
Now let's talk about the well-architected framework. The well-architected framework is a collection of 5 white papers. And these white papers provide best practice guidance on building systems within AWS. And this best practice is essentially collected from the experience of not just AWS, but also from the experience of running Amazon.com on AWS. It's also pulled from large Amazon customers such as Netflix, customers that are doing really complex things at really large scales. And so these white papers are sort of broken into 5 pillars. And those 5 pillars are reliability, showing us how to build systems that are reliable and resilient. And reliability talks about high availability and fault tolerance, things, different features, different options that we can use, and different techniques that we can use to achieve and build a reliable system. We also have performance efficiency, and performance efficiency is not just about using the greatest, most powerful EC2 instance all the time. It's about the efficient use of computing and how to maintain that efficiency as our needs change and as the demand on our systems change. And so it's about using the right tool for the right job. And then we have security. Of course, security shows us how to leverage things like different accounts and how to ensure that we're using the right credentials for the right reasons. And it talks about network security and different ways that we can create a secure environment within AWS. We also have cost optimization, which goes into very similar to performance. It's about using the right tools for the right job. Not every application needs to run on, let's say an M5 16 extra large, right? Some applications may run perfectly fine on a T3 small. And so it's about using the right size instance, the right size volumes. It's about using cost optimization tools like we talked about earlier to identify areas where we can save money. And then lastly, we have the 5th pillar is operational excellence. Operational excellence is all about the business processes that we use to implement those 4 other pillars. Operational excellence is about ensuring that we're using the right tools and that we are leveraging automation as much as possible. So remember what I've mentioned earlier, that the only way to truly realize all of the power and benefit of AWS is through automation. And so the operational excellence pillar talks to that. It talks to the business policies and business processes that allow you to take the most advantage of all that Amazon has to offer. So I would highly encourage you to take a look at the well-architected framework. It's available here at the URL on your screen. And if you are wanting to go on beyond just the basics, beyond the fundamentals, and really get into understanding design thinking, then the well-architected framework can really help. And if you want to go on and achieve the Solutions Architect Associate Certification, then the well-architected framework actually forms the basis of the exam. So the well-architected framework, by studying that, you will be studying for the Solutions Architect exam. And if you want to take that route, then I would also highly encourage you to take a look at my video, the Solutions Architect Associate Complete Video Course. And we follow the well-architected framework module by module, really diving into each one of these 5 pillars and exploring a number of concepts as they relate to building and architecting and designing services for AWS. Now let's review some best practices. As you move forward, getting into AWS, as you start thinking about architectures that will go to AWS and be built within AWS, as you start to explore different services, there are a number of best practices to keep in mind to help you ensure that you are building, the most performant, reliable, secure, and cost-effective infrastructure within AWS. First would be, and these are in no particular order, but first, enable scalability. And so scalability allows you to meet demand when you have it. So there could come a time when you have more demand or more work to do than what you did the day before. And so by enabling scalability, by building a system that is elastic, by building a system that can respond to those kinds of changes, and enabling you to scale to meet that rise in demand, then you can ensure that you will be able to meet it, right? So you can imagine that if you have no ability to scale, and then at some point you have more demand than you had previously, then at some point that system may very well experience downtime. The next best practice is to think of our resources as disposable, right? So we're leveraging disposable resources rather than fixed servers. So coming from traditional IT, we had, fixed servers. We spent a lot of money and a lot of effort getting that server in that rack. And we had a particular budget, and we're not going to do anything more with it. We're not going to replace it for another 2 to 5 years, maybe longer, right? So in traditional IT, we had fixed servers, which meant that our processes and our capabilities were also fixed to some degree. With AWS, by leveraging just the nature of on-demand resources means that we can now treat those resources as disposable. And that gives rise to a level of flexibility and agility and efficiency that we never really had with traditional IT. By treating them as disposable, then we have the ability now to create temporary environments, right? We no longer have to force our teams to wait in line to test their applications. Each team can get a temporary environment for that application. When the test is done, throw it away. Disposable resources now frees us to just replace the machine instead of triaging the machine, right? In traditional IT, we would have to remote into that machine and spend a lot of time and effort, essentially babying, treating that machine like our pet and ensuring that it stays alive. But in AWS, we simply, if there's an issue, we terminate it and allow automated processes to bring that machine back to life, doing what it's supposed to do. And if we need that machine in a different state, then we can go back to our machine images, we can go back to configuration management and define and configure that state there. And of course, another best practice is to leverage automation. We want to avoid manual operations as much as possible, right? Remember that humans we make mistakes. We come to work without enough food, sleep. We come to work with, maybe something going on in our lives that is distracting us from the work that we're doing. And as a result, we make mistakes. And those mistakes cost time, they cost money, or they potentially could cause some type of a security issue, right? So by leveraging automation, we can do things more efficiently, and we can do things more cost effectively. We can do things more securely. Another best practice is to leverage loose coupling. Loose coupling, one classic example of loose coupling is instead of two different systems being inherently aware of one another and dependent on one another, we could put a queue in the middle or a load balancer in the middle. That way, by removing the inherent knowledge of those of each other, those systems can then run independently. So ideally, if we have multiple systems, we should be able to have an environment in which one system can be offline without affecting another system, right? That's what loose coupling aims to do, where like by leveraging a queue, for example, one system can publish a message to the queue, another system reads from it. That way, if either one system is down, the other system can continue to run. Another best practice is to prefer services, not servers. And so what this speaks to is the fact that AWS offers a number of fully managed services. So think about simple queue service, simple email service, simple notification service. Think about the relational database service, Elasticache, Redshift, and so on. All of these services are meant for us to offload the operational burdens to AWS. And so by doing that, we can lower our total cost of ownership, because we can have perhaps a smaller team, and then that team is focused on delivering actual differentiated value to our applications rather than being burdened by managing servers. A few more best practices here. First would be choose the right database, right? A number of applications these days are actually making use of several different types of databases, right? It's common for an application to make use of relational databases, NoSQL databases, in-memory cache, and so on, right? So choosing the right database for the right problem is key to ensuring that we're going to get a level of performance and security and durability that we need in that data. Another best practice is to avoid single points of failure. I think that goes without saying. That's something we've probably been familiar with for a long time, but it's important to remind ourselves that even within AWS, it's possible to have single points of failure, right? So like we talked about earlier, it's possible to run an application on one EC2 instance, but by doing so, we have no way of mitigating or tolerating a failure. If that one instance fails, we will experience downtime until it's replaced. And so instead of running an application on one instance, we could run it on 2 or 3 or 20, right? And put them behind a load balancer so that if one fails, we still have the others. And that same pattern applies to a number of things, not just EC2 instances. And then, of course, we want to optimize for cost. One of the main drivers for moving to AWS is to lower our cost. Believe it or not, it's not the number one driver. The number one driver for most organizations is to gain access to a level of flexibility and agility that we never had before. But who wants to spend more money than we need to, right? So as we've seen throughout this course, we have plenty of tools and plenty of options to choose in order to build a system that is reliable, performant, secure, and cost-effective. And of course, when it comes to optimizing, whatever we're optimizing for, this is not something that we do every so often. Optimization for cost or for security or performance or reliability is not something we do every month or every 6 months. It's something that we do every day, and that's one of the another philosophy to adopt when coming to AWS. And that's something that is spoken to quite a bit in the operational excellence pillar of the well-architected framework, that optimization is an ongoing, constant effort. And I can speak from personal experience that in running many different types of workloads in production from many organizations and helping organizations to strategize and plan for the cloud, that this becomes a thing that we do every day. That every day you come to work and go, how can I make this better than it was yesterday? And we have the ability, looking back on all the things that we've talked about, you can see that we have an easy ability to change our minds at any time. If I come in today and I look at the system and I ask, how can I improve this today? How can I make it better than it was yesterday? I don't have to wait for my next budget refresh. I don't have to wait for the next hardware recycle. I can do it today. I can make changes today. No decision that I made so far is set in stone. And then lastly here, a couple of more, is leverage caching. We talked about caching when we covered CloudFront. Remember that with CloudFront we can cache static and dynamic content at the edge location. We also talked about caching with Elasticache. With Elasticache we can cache different types of things such as database result sets in memory. And the whole point of caching is to deliver things to the end user faster. The whole point of caching is to improve the end user's experience by lowering latency, by getting them what they're looking for faster. And then lastly, the last best practice that I'll leave you with is security in layers. And remember that when you think about layers, we could imagine that there are different layers. And I always imagine that there would be the account layer, there would be the network layer, and then perhaps the application layer, right? And so remember that we are operating within a shared responsibility model. And the most important thing in there is for you to be aware of whatever you're using, whatever service you are making use of. It's important for you to be aware of what is your responsibility versus what is Amazon's responsibility. And those things change according to the service that you're using and according to the features that you have opted into, right? And so at the account layer, we have users and groups and roles. We have policies that can control authorization. Within the network layer, we have routing controls to control the flow of traffic to and from the internet or not. We also have different firewall mechanisms like network access control lists. We have security groups that can open and allow different types of traffic on different ports. And then, of course, within your application may make use of temporary credentials in order to access Amazon services, right? So the best practice here is to ensure that you are applying security, the appropriate security features in each of those layers, right? So again, as you move forward, getting to know Amazon Web Services more, as you start to explore these services and build these services, keep these best practices in mind.
The rise of cloud computing is perhaps one of the greatest technical revolutions in my lifetime, and I believe Amazon Web Services is just getting started. My career over the last 9 years has been truly exciting, and I hope the same is true for you in the coming years as well. Thank you so much for joining me in this Amazon Web Services Fundamentals course. The concepts and technologies presented here will likely make even more sense when viewing these videos a second and third time, so I would highly encourage you to do so. From here, I would also encourage you to practice the hands-on labs available for free in the AWS website. As you move forward with your studies of AWS, remember that nothing beats hands-on experience, especially if you are looking to gain a certification. So get out there, build VPCs, launch EC2 instances, explore other services like AWS Lambda, Amazon Kinesis, and Amazon DynamoDB, and enjoy the wonderful world of cloud computing with Amazon Web Services.